So I think we can start. We can wait for another 4 minutes since first session we have some flexibility on oral is not there. Right, ma'am? So he is not joining. Can you hear me? Professor Sunita Srivastava. Can you hear me? Hello?
Yes.
Hello? Hello, ma'am?
Yeah. Yes, Sanjay, I can hear.
Yeah. So I am asking that that on participants on oral is missing, right? So that Chandan Kumar.
No. He confirmed me that he will be able to present.
Okay.
So,
then it looks nice. Okay.
We can follow the schedule as per we had decided before.
Okay. That looks nice. So it's a good news to us. So yeah. So let's go forward so we can start our day 2. So can you see the screen?
Yes, I can. Yes.
Yeah. So I'll quickly give a overview of day 2 and what we did on day 1. Actually, in our department, there are various fields we worked on. Our professor, PhD student, all other together. So astronomy, cosmology, and gravity, experimental high energy physics, theoretical high energy physics, theoretical soft matter physics. So that part is done on day 1. Today we are left up with that experimental soft matter physics, experimental photonics, poster session, experimental condensed matter physics, theoretical condensed matter physics. So without any delay, we will give a quick, last day also we played this video, today just a replay. So I'll play the video directly, not from here. So that sometimes gives the video is not audible, right?
Video was audible, but right now we can't see anything on the screen.
Okay. Let me try. It gives some issues sometimes. So share screen. Then go to video.
Yes, it is there.
Okay, let's go. Yeah. So it's audible, right?
Yes.
Okay.
Physics is one of the most important and fundamental sciences. It tries to answer a wide range of topics such as quantum computing, medicine to gravitational waves. Our colleagues in the department also are trying to answer these questions using a variety of experimental tools and theoretical models.
This department started right at the inception of the institute, and it served the purpose of teaching as well as of very high quality research. In the old days, we started with spectroscopy, condensed matter physics, nuclear physics, elementary particle physics. But over the decades, we have gone on to include nanosciences, elementary particle physics with string theory, cosmology, also biophysics.
The Experimental High Energy Physics Group at IIT Bombay is involved in ALICE and CMX experiment at CERN, designed to study heavy ion collisions and proton-proton collisions at LHC energies. We here are primarily concerned with studying the properties of quark-gluon plasma and heavy ion collisions, which mimics the matter formed at early phases of universe. And we also study PP collisions keeping at a baseline, so it's a very challenging and exciting phase for us, and we are on to our task.
In theoretical condensed matter physics, what we do is to develop and use advanced theory and computational algorithm to understand the behavior and different properties of novel materials. In a nutshell, this basically involves utilizing the concept of quantum mechanics to understand different condensed matter problems at various time and length scales. To name a few, in our department we have expertise working in the area of density functional theory, quantum information theory, strongly correlated electron problems, and non-equilibrium systems.
So the experimental condensed matter physics We explore novel materials which manifest quantum phenomena on a macroscopic scale. So materials such as those which go into hard disks and computer memories, materials which will power tomorrow's solar cells, superconductors which flow electricity without any resistance, topological phases, and so on. We measure properties of materials down to low temperatures, temperatures even lower than that of outer space. So with all this work, we will unravel fundamental physics behind these phenomena.
Nanoscience has emerged as an important area of research as nanomaterials reveal new physics which is different from their bulk counterpart. The Nano Experimental Group here at Department of Physics, IIT Bombay works on exploring the structure-function correlations in such materials. Broadly, the goal is to focus to understand the new physics at nanoscale and pursue projects of technological applications such as nanophotonics, self-assembly, and sub-wavelength imaging.
When a large number of elements interact together, complex properties emerge. Our nature is full of such complexities at every scale. Here in the physics department, we study such emerging complexities. With the help of fundamental physics tools, we try to answer questions such as how DNA packs inside a nucleus, how cells divide, how tissues develop into complex organs, etc. We also study several non-biologically motivated problems. We believe that trying to answer such questions will fundamentally or significantly enhance our understanding of nature.
The area of photonics deals with the science of light and its manipulation. We investigate how interactions of light with matter can be used as tools to solve today's real-world technological problems. For example, spectroscopy is used to analyze materials of different kinds. Nano-optics deals with scaling down technology to very small dimensions, and ultra-fast optics focuses on studying events happening in the atomic and molecular timescales.
The Astronomy, Cosmology and Gravity Group works on black hole physics, early universe cosmology, multi-messenger astronomy, gravitational wave detection, dark energy and galaxies. The group primarily contributed to the detection of gravitational wave by LIGO-Virgo detectors, which received Nobel Prize in 2017. It also did the follow-up observation of the golden binary, which was the neutron star binary system, with the Indian Astrosat mission.
Where does the spin of the proton come from? What gives neutrinos their tiny masses? What is the mysterious dark matter particle that appears to make up most of the universe? Does the top quark play any role in the Higgs mechanism? Are there any as yet undiscovered symmetries of nature that govern the rules that fundamental particles obey? Is string theory the correct description of nature at its most fundamental level? The Theoretical High-Energy Physics Group of IIT Bombay is trying to answer these fundamental questions about our universe.
Answering these questions is expected to result in a better world for all of us.
Our alumni have gone on to occupy very important positions in academia and industry. They have become innovators, professors at major universities, and even administrators.
Doctoral life in physics department is just awesome. With these diverse fields of research and the fact that research scholars are coming from different parts of the country with different regional and cultural backgrounds, we enjoy sharing ideas, philosophy, and opinion diversity.
To an undergraduate like me, the 4 years I've spent in the Department of Physics has been nothing short of awesome. The unparalleled support for exploring, coupled with the well-thought-of and well-maintained facilities, makes us gravitate to the department building. The computer room, the library, and the seminar room become symbols of our existence. The department has been the shining light that has lit up the path ahead for all of us, making us who we are and who we become.
Hello, can you hear me?
Yes, Sanjay, we can hear you.
Yeah. So highlights of day 2 is we have 4 invited speakers: Professor D.K. Satapathy, IIT Madras; Professor C. Narayana, JNCASR, Bangalore; Professor P.S. Anil Kumar, IISC Bangalore; Professor G. Bhaskararan, IMS Chennai. So also we have poster session on in main hall and poster parallel session. That will be just after lunch, poster parallel session, and poster session on is before lunch. So we also have a virtual tour at IIT Bombay afternoon session and then concluding session. So now I hand over the session to Professor Sunita Srivastava for first session of day 2.
Okay. So let me formally welcome everyone, and thank you, Sanjay, for that nice video, especially in this time when we all of us are basically missing the campus and the students the most. So with that, I think I'd like to begin our experimental soft matter session. So as Sanjay told, the first speaker is Professor Dillip. He's associate professor at IIT Madras. And without much further ado, delay, I'd like to hand over the floor to Professor Dillip, and let's listen to the exciting talk that is going to present in front of us. So Professor Dillip, the session is yours now.
Yeah. Thank you. Let me share the screen. It says host disabled attendee screen sharing. Can you please enable that?
I have to make you the host, I think.
You have to enable screen sharing, I guess, because it's not shared. I'm not able to share. Now it's okay.
Are you the host?
Now
so if you are able to, okay, good.
Can you see the full screen?
We can see the full screen. Okay. Perfect.
So, good morning to everybody, and I thank the organizer to give me the chance to speak here to all of you. I think it's a difficult time, but I think you guys are doing very good and keeping the spirit, and I can see that many talks and the scientific event you have put together. I also thank Professor Sunita for her kind invitation, and Sanjay for all the coordination he is doing. So without going further, I would like to start my talk. It's, as we said, it's an experimental soft matter. And what I'm going to talk about is interfacial self-assembly of soft colloids. So my name is Dillip, Kumar Satapathy, and I work at Soft Materials Lab, Department of Physics, IIT Madras. So before I start the talk on interfacial self-assembly of soft colloids, I would like to quickly show you what we do in our lab, the research in our lab. So the research focus at the Soft Materials Lab is mostly revolving around polymers and colloids, which are two important pillars of experimental soft matter. In polymer, we look at the novel properties of polymer in confinement, both polymers under hard confinement in the form of thin films or in two-dimensional slips, and also polymers in form of soft confinement. In addition to that, we also look at the swelling kinetics of polymers when it is exposed to a good solvent, and different kinds of polymer-based sensors for detecting different kinds of gases, humidity, and so on and so forth. And recently, we started working on soft actuators, where in response to a trigger, the polymer membrane creates a mechanical motion. So I have listed down some of these representative publications in those fields from our group. And naturally, we also work on colloids. And in colloids, the main focus is on self-assembly of amphiphilic soft colloids. And another class of important colloids is called associated colloids, which is also known as microemulsions, which is nothing but a mixture of water, oil, and a surfactant, which stabilizes the nanoscopic mixture of water and oil. And we also look at the controlled manipulation of cracks in deposits of colloids. In that case, we see how when a colloidal layer cracks, how the crack nucleates and how the crack propagates. And especially, we are interested in, can we control the crack by some application of external fields, or can we have some specific perturbation in order to achieve a desirable crack pattern? And we also do some applied research, which is mostly the mixture of polymers and colloids, which is another field, which is known as polymer composites, which combines properties from both polymers and colloids to achieve some specific applications or specific properties of the whole composite material. So in that case, we work on thermoelectric polymers for wearable electronics, where the idea is you generate a little bit of energy by utilizing the temperature difference between the human body and the environment, and also look at soft ferroelectrics, where you try to align the dipoles in a polymer membrane, which is an upcoming field and very useful for various applications. With that, I think today's focus or today's talk will be on self-assembly of amphiphilic soft colloids, mostly interface-assisted assembly of amphiphilic colloids is what I'm going to focus on today. And this is my group at IIT Madras. All of them are doing working on different aspects of the projects I have just discussed a little earlier. And the work I'm going to present today is done by Narayana, who was finished a doctoral study and currently at a postdoc at University of Paris, and by Marine. And this interfacial assembly of soft colloids we are doing in close collaboration with Dr. N.G. Baskaran, who is a faculty member at the Chemical Engineering Department, IIT. So now the question is that why soft colloids? What is the meaning of soft colloids, or why are you interested in soft colloids? But before we go to that question, we must look at two important class of materials that constitute the soft materials, is polymers and colloids. As we know, the polymer is nothing but a long chain of molecules, which is made up of things called monomers. And these monomers are small molecular units and connected each other through covalent bonding. So for many physics, understanding of the physics of the polymer, we do not really need to know the chemical nature of these monomers. However, if we can imagine the set of monomers, which is basically consisting of n links, and each link with length b, and they're able to point in any direction in space independent of each other. Basically, the polymer chain can be decomposed to a set of vectors, and by looking at their and considering the polymer chain as a set of vectors, we can actually understand many of their properties, including the structure and dynamics. So, and the other class of material is the colloids, as I told. So colloids are nothing but very small particles dispersed in a solvent, and it's also known as ultra-divided matter, and by various kinds of interactions, starting from charge stabilization to steric stabilization and so on and so forth. This field is very well developed, and we can have stable dispersions of particles in a solvent, and that is known as colloidal dispersions. And the typical size of the colloids are a few nanometers to few microns. One of the importance of colloids is that because its size is microns, it can be easily observable through an optical microscope. However, it is still very small, so that the Brownian dynamics dominates its behavior in the solution. So these two kind of material are having various, if you look at these materials, they demonstrate extreme cases of self-organization in space, spatial organization, and they have a large number of molecular epithelium. In case of polymer, this is a polymeric chain. In case of colloids, they form large colloidal crystals where these big micrometer sized particles arrange themselves to form large crystals. And this is a very rich field of research which allows one to understand various phenomena of condensed matter physics, like melting, crystallization, so on and so forth. The polymers and colloids, they are very different length scales. The length scale of polymer is few nanometers, whereas the length scale of colloids is few micrometers. So there is a very large range of length scales involved in these two materials. And I believe that this flexible linear chains and half-sphere colloids are perhaps the most studied and better understood class of soft materials. And they have very interesting set of properties. In case of polymers, we see, for example, if we apply a stress to a polymeric material and to a colloidal crystal, in both the cases, the stress is transmitted through the material, but however, the mechanism through which the stress is transmitted is very different. For example, it's a linear chain elasticity in case of polymers and Brownian dynamics in case of colloids. So why I'm trying to discuss this is that these polymers and colloids are kind of two different class of materials, but they're self-organized in space and having different length and time scales. And they show a wide range of properties. Now it becomes immediately evident that if we can have some sort of material which combines the property of the polymers as well as colloids. And this class of material is known as the soft colloids. So soft colloids it's an important class of material which combines part of the property of the polymers and part of the property of the colloids. And they have intermediate behavior between short-range polymeric and long-range colloidal interactions. And of course, needless to say, they also have a far richer phase behavior than hard-sphere colloids, we just discussed. And as I mentioned, they show polymer particle equality. So that means they combine the polymeric properties with colloidal mesoscopic characteristics. So they have the colloidal length scale, but the interaction is more or less like polymers. And most importantly, as we discussed, the interaction between these particles are indeed tunable. That is very, very important. In hard-sphere colloid, if it's completely hard-sphere, the tunability of interaction is limited. Although there are some ways to tune the interaction, but here in soft colloids, the interactions between the particles are easily tunable, and they have both the properties of polymers and colloids. So this allows one to construct a large class of problems to be studied by using the soft colloidal particles. That is why we are interested in soft colloids. So I'll just give you a little overview of what is already known or established in soft colloids. If you see, we are going from a soft interaction to hard particles. Hard particles are basically interacting to excluded volume interaction. And the double arrow horizontal line shows that how can we go from hard sphere interaction to soft interaction, going through hard colloidal particles to grafted particles that are grafted with polymer chain, or star polymer particles, or polymers with cross links, and of course linear polymers. So as you can see, there is a range of different things that is already established and investigated, which allows one to go from hard to soft particles. That's not it is not only that, but we can also bring different kinds of complexity into the system that allows one to tune the interaction in terms of both their strength and the range of interaction. One of the way, if you go down vertically, for example, in hard sphere colloids, you can add some polymer chains that brings a different kinds of interaction into the colloidal thing, which is known as diffusion interaction, which is an attractive interaction. And or you can add smaller particles to colloids. Or, for example, in grafted nanoparticles, you can also have the grafted chains cross-linked around. That also allows one to tune the softness or the interaction. Or, of course, we can go to microgels or block copolymer-based systems and grain reamers and polymer-based grain reamers. So these are a class of colloidal particles that is already synthesized and established and studied, and that allows one to a great degree of flexibility in tuning the range and strength of interaction and combining both the colloidal and polymeric particles. But what we are going to interested, or what our group is interested, is on this kind of particle, which is known as the microgel particle. I will explain you what exactly the microgel particles, and then we can discuss how we are using those microgel particles, or how we are exploiting the interface to understand or to achieve the self-assembled structure of microgel particles. So what is a microgel particle? It is a cross-linked polymer-like particle where we have a cross-linking gradient once you go from core to the cell of the particle. So they have a core cell structure, but just remember that the entire the particle is nothing but a block of polymers and with a variable cross-linking density. What do I mean by cross-link? It's basically some physical or chemical bond between the chains. How many different bonds between the chains, that is interchain bonds, or even between different parts of the chains, that is intrachain bonds are there. once we go from core to the cell. So this is the soft microgel particle. It's a schematic representation where you can see a highly cross-linked core. It's surrounded by a less cross-linked cell, which is basically, you can imagine these polymer chains are dangling out from the core outwards. And these particles, because of the density of the polymer on the outside cell is less and they are less cross-linked. So this outside cell is soft and it is deformable. But the cell is very much attached to the core, and the core is also soft, but it is with a different elastic property. It is harder than the cell. This kind of particles are very well known and usually synthesized by a polymer called NIPAM. It's is basically NIPAM plus you take the NIPAM monomers and take a cross-linker, that is BIS, and with a proper polymerization reaction, you can achieve this kind of particles with a variable cross-linking density once you go from the center of the particle to the periphery. So this particle, the diameter of the particle is also tunable. The particles we will be discussing today somewhere between 400 to 700, 800 nanometer diameter. They have a densely packed core and a loosely packed cell. So if you look at the radial monomer density profile, that you look at the density profile of monomers going from center to out from the center to the periphery, you see the monomer density also decreases, which also again confirms the fact. This is the schematic representation of the monomeric density, and this profile is tunable. You can say that how big should be the core and how big should be the cell. What is the elastic property of the core and what is the elastic property of the cell? So and that is controlled by controlling the density of monomers once you go across the particle, and this density of the monomers can be exactly measured by using scattering experiment, for example, by performing neutron scattering, small angle neutron scattering experiment, very well studied in the literature. This polymer-based particles or these microgel particles are having, or the microgel colloids are having another interesting properties, which is that these particles are undergoing a phase transition at a temperature around room temperature, and that is why it is widely heavily investigated for various kinds of applications, including drug development. So I will just quickly explain that what happens. So this polymer has a special affinity towards water. Some of the groups of this polymer present, some of the groups present in the polymer have a special affinity towards water, and they inject water molecules and the polymer sweats. So when this particle is dispersed in water, they absorb the water molecule and the particle goes to swollen state. But as you slowly increase the temperature, then the particle expels water from its core and its cell and it again desweats. So this happens. It's a very sharp transition and happens at a temperature of around 32 to 33 degrees centigrade, and this transition is reversed. It's essentially you can see that something gets swollen and deswollen as we change the temperature, and this is a very good example also to establish the polymer particle value. So you can do a very simple experiment, like you take a small test tube and put some of these particles and a little bit of water and shoot a laser pointer through that, and if it is if the particle is in a swollen state, so it's like it's water light. So almost all of the laser light can transmit through that. But as soon as you start increasing the temperature, as soon as we start increasing the temperature, then the phase segregation happens. The particles become shrunk and then get phase separated from the water phase, and then that makes a torbid solution which scatters most of the light, giving a very rapid decrease in the intensity of the transmitted. So this can be this phase transition in this polymer particulate system can be measured by simply performing a transmission experiment, and this is also reflected if you do one electrical conductivity experiment where you measure the electrical conductivity while changing the temperature, and the electrical conduction also shows an anomaly which is associated with the trapping of ions or releasing of ions by during the phase transition of the. And another important property of these particles are their amphiphilia. So these particles have a very delicate balance between hydrophilic and hydrophobic subunits, or hydrophilic and hydrophobic parts of the chain. They are very delicately balanced, and that imparts an amphiphilic property to the particle, which is very important for this interfacial self-assembly step. And what I mean when I say it's amphiphilic, if I have a mixture of polymers of these particles in a water droplet, for example, these particles will spontaneously migrate to the interface and get absorbed to the interface, because that minimizes the overall energy of the system. And one can actually do one simple experiment and see that. For example, if you measure the surface tension of a drop loaded with these particles, as you can see, as the time progresses, a water droplet remains as it is. But a droplet which is loaded with these microgel particles or uniform particles, the surface tension starts to decrease as more and more particles populate the interface. Why it is happening? Because the particles are amphiphilic in nature. And once the particles are absorbed to the interface, the binding energy is enormous, which can be easily understood, and 10 to the power 6 kBt of the order of that. So they never get detached from the interface. So they remain attached to the interface. And this strong binding energy can be understood by considering the minimization of the total interfacial free energy of the fluid particle system. That means once a particle populates the interface, it replaces the fluid air interface with the particle fluid and particle air interface. So one can do a detailed calculation to show that this absorption is favorable. And just to give you a summary, so for hard sphere colloids, we have excluded volume kind of interaction, and because the particles are not penetrable, whereas for soft microgel particle, the interaction potential the particles can interpenetrate, and the interaction potential takes this form. And this form of the interaction potential has the big advantage that this can be tuned by tuning the core and cell cross-linking density and monomer density and so on and so forth. One can tune the range and strength of this interaction. So now, as I told, these particles are amphiphilic, and they usually populate the interface. So naturally, once the particle go to the interface, in addition to the interaction between the particle which was dominant in the bulk, additional interaction occurs. For example, once the particles are at air-water interface, because both sides of the particle has now two different are in a different dielectric medium, and then that leads to some asymmetry in the charge distribution, and then an additional interaction like dipole interaction arises. And because the particles are absorbed to the interface, they also deform the interface locally, or especially the meniscus. The meniscus comes around the particle at the interface, and that gives rise to capillary interaction. So, because these particles are absorbed at the interface, in addition to their the interactions that is there between the particles, interparticle interaction, they have now subjected to additional interactions because they are amphiphilic and getting absorbed to the interface. Those interactions are also very important to fully, to tune fully the interfacial self-assembly. But apart of that, this microgel particles, what I have shown there is actually true for hard particles as well. There will be, for example, this dipolar interaction is also observed for hard colloidal particles, as well as this capillary interaction is also observed for hard colloidal particles. In addition to that, it offers one more interesting thing, the soft microgel particles. As they go to the interface, they are immediately subjected to the interfacial tension. So because the particle is soft, the interfacial tension would like to stretch the particle, and then the elasticity of the particle, the core of the particle, or the cross-linking between the chains would like to resist that kind of stretch. So what happens in these two competing force, the particle is no more spherical at the interface. It takes a kind of fried egg structure. You can see this nice ACM image where we see that part of the particle is stretched and getting connected at the interface. So it's basically a connected network of particles at the interface. And a detailed simulation study also appeared recently where they say that once the polymeric particle populates the interface, at the plane of the interface, the particle stretches quite a bit. And that stretching happens because of the computation between the soft interfacial tension and the elasticity, internal elasticity of the particle. So what we are discussing here is that, if we have a size of the particle, let's say have some sort of size particles in the bulk, as soon as they populate the interface, they are subjected to new kind of interaction, and also their shape is now distorted at the interface. So because of that, the detailed nature of the interaction potential of the particle is still not fully understood at the interface. However, we most of the time, many of the properties of the system can be explained if we take into account this kind of interactions that we have discussed. And for example, I would like to give you one idea about this change in size of the particle. If we take a microgel particle dispersed in bulk and measure its size by performing a DLS experiment, which is dynamic light scattering, and let's say you get a size of about 700 nanometer, that is what we observed. Once the particle populates the interface of a drop, if you measure the interparticle separation between the particles, and we assume here that the interparticle separation arises because the particles are barely touching each other, or the cells of the particle is barely touching each other. So the interparticle separation, if you can measure and now try to find out the size of the particle, it is actually almost 2 times higher at the interface. So keep in mind that there are two things. This particle diameter that we measure in the bulk is the diameter of the swollen particle. And that is in a completely swollen state, it is 700 nanometer roughly. But when it goes to interface, its size gets completely changed and increased by a factor of 2. But it's not no more a sphere. It's actually a sphere, and then it also extends radially along the plane of the interface. Just keep in mind this ACM picture here, so that will be helpful to understand our study. So these are the kind of particles we fabricate with different cross-linking densities. As you can see in a FM image, you can clearly see the spore and the cell of the particles. You can see the cell is weakly visible in AFM phase images. And by changing the cross-linking density, one can tune the size of the cells. So now I have given you some overview about these microgel particles. Now the rest of the time I will use to show you some of our results on the self-assembly of this microgel. So we are mostly interested on the evaporative self-assembly, which is a very simple experiment where you take a drop of this colloids and put it on a surface and let the fluid evaporate as a function of time. And as soon as the fluid starts to evaporate, we know that the particles in the drop do get deposited in the form of a ring, which is known as a coffee ring. Those of you who do not know this coffee ring, it's formed because the drop is strongly pinched to the solid surface, because the surface has some finite roughness and it pins the drop. And because the droplet is pinned and it has a hemispherical shape due to surface tension, then the evaporation is not homogeneous anymore across the drop surface, and the inhomogeneous evaporation across the drop surface creates an additional flow known as the radial flow in the drop, and that basically takes all the particle to the periphery of the drop and depletes the bulk and the bulk is depleted of the particle, and these particles are actually deposited in the form of a ring. And it is a very well established or well studied problem that the formation of those rings by evaporation of a sessile drop. So we are basically using the same geometry, but what we are doing is we are replacing these hard particles or the polystyrene particles with soft particles. One of the questions of our interest is that we came across a work some time back where they say there is an order to disorder transition, or the authors here reported and proposed a mechanism to understand the order to disorder transition in ring-shaped colloidal states. So they basically perform such an experiment with a sessile drop and then get a deposit, and then they microscopically analyze the ordering of those particles in the deposit. And they found that as you go from the periphery of the deposit towards the interior, it looks like the particles are much better ordered at the periphery, and then at the interior the particles are less ordered. It's basically there's and what they found out that this transition from order to disorder is very abrupt. So there is an ordered phase and suddenly there is a disordered phase. And this happens, this order to disorder transition is confirmed by them or basically observed by them, and they proposed a mechanism saying that why this order to disorder transition happens, and that is related to the temporal singularity of the flow velocity. For example, the way this radial flow happens in the drop, it's not always same as the drop evaporates further and further. And this strength of this radial flow also changes. And then towards the tail end of the evaporation process, there is a Rossauer effect because of the less fluid, and that is responsible for the disorder of that is observed here. But however, you should keep in mind one thing, that the order to disorder transition here is abrupt. There is an order phase, and then there is a disorder phase, and transition is abrupt. And then we just decided to look at this problem by replacing these particles with our soft microgel particles, where the interactions between the particles it's tunable and mostly dominated by the steric repulsion and other kinds of interactions that are at the interface. So the difference between our particle, the microgel particle, is that because the particles will be at the interface, the radial flow is not going to disturb the assembly of the particles. So when we really look at this formation of the ring, actually it is, we didn't see a real coffee ring, but what we see is that a layer of particles a monolayer of particles getting deposited in the form of a ring. This is not the usual coffee ring where you see a multi-particle thick deposit, but here it's a loosely packed monolayer deposit of the particles in the form of a ring. And very interestingly, the width of this ring, as well as the extent of the deposit, can easily be controlled by simply controlling the concentration of particles in the drop. For example, you can see a 1 layer thick ring versus a three layer, not 3 layers, it's a monolayer, but the width of the ring is now 3 particle wide. And then we can change the width of the ring to some extent, and then we could keep tuning the concentration. Once you find that the entire droplet area or the entire drop area is completely covered by this particle. So you basically get a monolayer deposit of particles across the whole drop. Then how do you understand this monolayer deposit, and why do it form? So for example, what we believe is that once you put a drop, the particles are all in the ball, but as the evaporation starts, because the particles are amphiphilic, they are propelling to the interface. And once the particles are at the interface, because of all different sort of interaction, they take up, they arrange themselves at the interface, or they form a self-assembled structure at the interface, and then they remain at the interface as the evaporation proceeds. So if you do a controlled evaporation and so in a specific manner, you should be able to transfer this interfacial assembled particles onto the substrate. And that is getting deposited in the form of a ring. And you can see the hexagonal ordering of the particle is already there in the interface and getting transferred onto the solid substrate at the end of the evaporation. And that gives us kind of monolayer deposits or even monolayer particles. So two important things: there is the interfacial flow which carries the particles towards the ring. But if you tune the concentration in such a way that the entire interface is decorated with the particle, you will get a monolayer. Now, when we look at the monolayer deposit a little more closely, we also see that at the periphery of this monolayer deposit, we have ordered regions or regions with hexagonal order. And as we proceed towards the center region or the interior of the deposit, slowly the deposit becomes disordered. We also see a clear transition from an order to disorder state, and which is even much more clearer if we take a fast Fourier transform or maybe Fourier transform of this thing. You can see this hexagonal symmetry versus the liquid-like structure of the deposit, and this proves that we have a highly ordered region and a highly disordered region. So we have done a very thorough analysis of the entire stain, and we found that by using Voronoi tessellation. And what we observed is that this order to disorder transition in case of soft microgel particles is actually not abrupt, but it is a continuous transition. So the order disorder transition is a continuously changes. As you can see, once we calculate the areal disorder parameter from the Voronoi constructions, one can establish the continuous transition, variation of the or the smooth transition from order to disorder state. The same trend is also observed in case of angular disorder, and the angular disorder is nothing but, if you once you construct the Voronoi tessellations, you look at the angle of hexagons and see how the angle of hexagon is distributed once you go from one edge of the stem to the other edge of the stem. We also see a gradual order to disorder transition when we look at the bond orientational order. What is the reason for this kind of continuous transition? We believe that the particles are highly ordered at the interface, but what happens is that if you measure the what you are seeing here is that the height of the drop and the diameter of the drop measured during the evaporation. So basically, you have a drop sitting on a surface, and you are measuring the height of the drop and the diameter of the drop during evaporation. As you see, the diameter of the drop hardly changes till till the tail end of evaporation, which is of 90 to 95% of the evaporation time. It hardly changes, which basically confirms that the drop is very strongly pinned to the substrate. However, the height keeps decreasing because of the continuous evaporation of the fluid. But at this last stage, suddenly the drop slips from because of this unavailability of fluid. There is a some sort of disturbance in the last stage, and then the drop deepens and the diameter changes. And probably this is not exactly responsible, may be responsible for the whatever disorder we have observed in our report. It's probably possible origin of the disorder. So next, we looked at this system to understand one more problem of this kind of deposits, which is already known. But the origin of that problem we have found out by using soft microbial particles. So origin of this kind of observation was found out by using soft microbial particles, and that is called a depletion zone in coffee stains. When you do this coffee kind of experiments, usually you see there is a ring like a deposit, and then there is a region where there is no particle is present, and so then we have particles in the center. And that is also observed by if you evaporate a drop containing colloids and surfactants. And by using microbial particles, we try to give an explanation that why this kind of zones are forming in porphyrin deposits. So if you look in our deposit also, you will see that there is a particular deposit, and then there is a zone which is depleted of particles, and then you have a continuous deposit in the interior of the zone. And this zone which is depleted of particles is known as a depletion zone. And because this now we are using particles which are larger size, and we can follow the particles when they are at the interface, we could clearly establish that why this kind of depletion zones are formed by doing little careful experiments. So to unravel the origin of these depletion zones, we have done an experiment where we have taken the two kinds of particles, microgel particles with a monolayer concentration and polystyrene particles together in a drop, and we found that the depletion zone is actually dependent. The width of the depletion zone is actually dependent on the concentration of the polystyrene particles. And another important fact is that the depletion zone forms only after a critical time. It doesn't form; it starts to form immediately. Only after 70% evaporation is over, you can see the formation of the depletion zone, and then it slowly widens over the time, and the final width of the depletion zone increases with increasing the initial concentration of the particle. So basically, three observations: depletion zone starts at at a later time in the evaporation experiment, and as the time progresses, it further widens, and it also depends on the concentration of the PS particles. So basically what we have done here, when the people have observed this depletion zone, they used to have surfactant and a mixture of surfactant mixed with a colloidal dispersant. So instead of surfactant, we use microgel particles because they are also amphiphilic in nature. So now we have a colloidal drop loaded with this amphiphilic particles, which act as a particulate surfactant, and which allows us to track their movement at the interface and what the surfactant does. So we have done a experiment by counting the number of these particles at different regions of the drop. For example, how many of these particles are present at the periphery and at the interface. It's basically what I'm talking about is that as the evaporation continues, these microgel particles are decorating the interface, and the interface is almost covered by the microgel particles because we have taken monolayer concentration. But as the evaporation continues, the PS particles also starts to get absorbed to the interface. But the concentration of these PS particles at the interface are very different than the periphery and the apex. And because of that, there is a surface tension gradient between the apex and the periphery. And at some point during the evaporation, that surface tension gradient becomes strong enough to create another sort of Marangoni flow, which gets the particles inwards and creating a depletion zone. And we have shown here that by measuring the number of particles, that the onset of the formation of the depletion zone actually matches very well with the maximum difference between the number of particles, or basically you can translate it to further to say that with the maximum difference in the surface energies at different point, or maximum difference in the surface tension between the apex and the periphery. So when the depletion zone onsets, is the number of particles at the periphery and at the apex is actually maximum. It correlates very well with the onset of the depletion, or the formation of the onset of the formation of the depletion zone. So we have this radial capillary flow which brings the particles outwards, and then at some point when the interfacial tension sets in because of the differential absorption of PS particle at the interface, the Marangoni flow sets in, and that brings the particles inside. So that's all about the origin of this kind of depletion zone that we observe. And then we have also further used these particles to understand the how to inhibit the formation of porphyrins in this kind of porphyrin formation. I just would like to know how much time I have.
Yeah, we have around 5 more minutes, 5 to 6 minutes. Yeah.
So this because these particles are getting absorbed to the interface, so this creates a particulate skin layer at the interface, and it can also completely suppress the formation of porphyrins in colloidal evaporation experiments. So that we have shown here that if you have only a PS particle drop, it forms a nice porphyrin. But if PS particle drop is loaded with piniform microgels, it suppresses the formation of the porphyrin. And this can again be understood. So this can again be understood by taking into account the evolution of viscoelasticity at this interface, and basically the interface transforms from the viscous to viscoelastic in nature as the evaporation proceeds because of the presence of these particles, and that inhibits the formation of the porphyrin. I will make this, and we have again done a detailed analysis with passive microevolution experiment to find out how this evolution of interface, how the viscoelasticity evolves at the particle level. Now, another interesting thing I would like to discuss about the binary mixture of the soft colloids. So we know that these colloids, when they are dispersed at the interface, they form beautiful crystals. So we know that when there is a polydispersity associated with colloids, then this polydispersity is not favorable for the crystallization, and it disrupts the crystal formation at the interface. But here what we are showing is that if we have taken 2 different kinds of microgel particles, for example, in this case we have taken 2 different kinds of particles with almost 25% difference in their diameter. And when you look at this self-assembly of these particles for the monodispersed versus bidispersed case, we see that in both the cases, they form order structures or organized structures at the interface. For example, when you have mixture of two sort of particles, you can see that it doesn't really affect the crystallinity unlike hard particles, but indeed the soft particles, even if they are different size, they can, because of the softness of the particle or because of the compliance of the corona or compliance of the cell, they adjust into the existing hexagonal lattice. So you have a crystal with 2 different sizes of the particles. So as you can see, the vortex, they are again forming an hexagonal ordering, but the vortices of the hexagon is occupied by the particles of both sides. So this is another interesting thing, because and again related to the softness of the interaction and the softness of the cells of this particle, so that they can easily accommodate themselves into an existing hexagonal lattice at the interface. And if we see this ordering of this kind of bidisperse particles, we don't see a very clear order to disorder transition. Rather, it remains equally ordered, or it can see equally disordered throughout the deposit. And finally, I would like to conclude with this piece of work, where we have shown that if you have a evaporation, I just discussed that if we evaporate these particles in a sessile drop geometry, you see this ordered crystalline regions, followed by a disordered region once you go inside the drop. But if we do the slow evaporation means, if you do evaporation at a very low humidity, very high humidity, so that very low evaporation rates, we have shown that the microstructure of the deposit is drastically different. So you see the formation of cells in the deposit, and wherever the particles are there, they are forming extremely ordered structure. So we can say the formation of cell-like tessellations across the deposit when we simply tune the evaporation time. So what we are doing is that we are essentially tuning the evaporation time, keeping everything else fixed. And you can see that if the evaporation is very slow on the saturated humidity conditions, then this kind of cells are forming in the deposit. And then we have done an analysis of those cells, and it basically shows that these cells are completely random. There is no such ordering of these cells, or there is no claim that the cells are bigger near the periphery or smaller at the center. So they have very random size distribution and random shapes. So now the question is that how does this evaporation time affect the formation of cells? Well, if we keep increasing the humidity to 90% also, it forms a kind of monolayer deposit. However, if you only go to saturated humidity conditions, it forms the cell-like tessellation norms. So now, what is the origin of this formation of the cells? We have seen that actually when the particles are absorbed at the interface, and then they are staying at the interface for a prolonged duration of time, at some point this kind of cells do form at the interface, and then finally they are getting transferred onto the substrate. And the question is that why this kind of cells are forming at the interface when the interface is homogeneously covered with the particles. We don't know exactly the answer to that, but what we believe is that as the particles are staying at the interface for a prolonged duration of time, but the evaporation is still slowly progressing, there is a slow increase in the density of the particles. And at some point, this slight rearrangement or increase in density of the particles at the interface triggers a phase separation at the interface, which gives to particle-rich and particle-free regions, which is essentially, one can think of it as a interfacial de-wetting kind of experiment. You have a particulate film, and it's there at the interface, and then there is slight change in fluctuations in this particulate film. And under certain conditions, it triggers a complete phase separation between the particles. So it's like interfacial sphenoidal decomposition or interfacial de-wetting that happens. But then once we transfer this layer onto a solid substrate, one can see these cells beautifully, and the particles, wherever they are deposited, they are very highly ordered. So in conclusion, I would like to say that we have used this amphiphilic soft microbial particles with tunable interaction to show that we can see this the order-disorder transition can be observed in this kind of deposits, and one can also see this monolayer deposits formed over a wide area by suitably tuning the concentration of the particle and the interparticle interaction, and by tailoring the evaporation kinetics of the droplet, we can do this local destructuring of the particles along the interface, which forms cell-like deposit patterns. And by doing this, by again using the soft microbial particles at the interface, one can also suppress the formation of proteins for hard particles. And it also allows us to understand the formation of depletion zones. And finally, we saw that this binary mixture of these particles has a very different behavior than the hard colloidal particles. And I'd like to acknowledge this funding we have received from various agencies. And I'd like to thank you all for your attention and would be happy to take any questions if there is any. Thank you.
Thank you, Professor Dillip, for a very exciting talk and also finishing in time. So now the room is open for questions. If we have any questions, I'll be happy to give a chance. I don't see any question in the chat room. If there are any questions, please raise your hand, or you can rather unmute yourself and ask. Looks like there are not any questions from the students. So if there are no questions, I have actually two questions if I can ask. So the first part of the question is about the depletion region that you talked about, right? Very interesting piece of work. So I was wondering that if you, let's say, you said you have a composition of a hard particle, kind of a hard particle and a soft particle, and that's what drives the formation of the depletion region because they go at the interface. I was wondering if it has been experimented whether if you don't have these particles which are softer in nature or they don't go at the interface, whether this kind of phenomena will still be possible to occur.
No, if it is only polystyrene particles, for example, it's hard particles, they will only form a coffee ring. But whenever there is a mixture, they give rise to some sort of depletion zone. So it has already reported, let's say, for hematite particles, which also populate the interface, or the mixture of surfactant with hard particles. So you need to have a mixture to form this depletion zone. But what we have shown here is that we have shown that what is the mechanism, exact mechanism behind the depletion zone, and how the onset of the depletion zone correlates with the maximum absorption or maximum difference in the number of particles at the periphery versus the apex. So there is a strong correlation when the depletion zone starts to form and
So you don't expect the depletion zone to occur if there is like it's not a mixture, it is a single particle system, then it's like after your thing, it should not form. Okay, the second question that I have is about the later part where you showed the cell-like morphology, which you said that it depends on the humidity and stuff.
Yeah.
So that's very interesting. So there is I don't know if is there a mechanism where you can completely deplete the coffee layer by changing the humidity of the system, like evaporation kinetics, and not get the coffee ring and just see this kind of fractal or this random like a deposition on the droplet?
Can you repeat? I didn't understand the first part. I mean, what?
Okay, so the cell-like system that you discussed, so there also there is a formation of coffee ring followed by this kind of like empty regions and then the deposition of particle, right?
There is no ring. See, this is the monolayer concept. So it actually stays at the interface. So in a regular case, you would see this whole layer should be transferred onto the substrate. But now because they are staying at the interface for a longer time because of the very slow evaporation process, so this triggers a phase separation already at the interface. So the homogeneous.
I see. So I missed the part that there is no ring.
So that forms the we exactly don't know the reason for that, but it's some sort of decomposition, spinoidal decomposition at the interface or debating at the interface, because everything happens at the interface only and then finally gets transferred to the substrate.
Okay, thank you very much. So if there is, let's check the chat room once again. So yeah, there is no more questions. I'd like to thank Professor Dillip on behalf of everyone from my side. And then we'll move to the next speaker. I think it's by the students. Anuj Chabra will present the next talk. So Anuj?
Should I start sharing the screen?
Yeah, you can start sharing the screen.
Everyone can see the screen?
Yes, we're able to look at your screen. So Anuj, you have total 15 minutes. I'll give you a silent warning, like 2 or 3 minutes when the time is about to end. We'll leave a couple of minutes if there are any questions.
Okay.
Okay, let's begin.
Good morning, everyone. I am here to talk about the electrostatic interactions in the polyelectrolyte blush on a spherical surface. So these are the contents of my talk. I will briefly talk about the introduction part, and then I will talk about the experimental details, mainly about the self-assembly and the small angle X-ray scattering, from which we try to, using this instrument, we try to understand our results. And then there will be a results and discussion part where I will talk about the two things: effect of the multivalent salt, and the another part is the ion bridging effect. And then I will try to conclude my talk. So polyelectrolyte polymers are the polymers which has some kind of a charge on them. So it can be positive charge, negative charge, which depends upon the system. And depending upon this, the structure of these polyelectrolyte changes. So in this work, they try to understand this effect via change of the pH and the salt on the absorption of amphoteric polyelectrolyte. So they observe that the structure is also changing with the increase of the salt concentration, but it also depends upon the pH of the system. And another effect is when these polyelectrolytes can be attached on a or grafted on a planar surface, this can lead to another kind of an effect uh, depending upon the morphology of the system. So if we add the monovalent or a divalent salt, these shows some different effects. So this is another example of a polyelectrolyte. So this is a micelle-like structure. We call it as a star polyelectrolyte or a branch polyelectrolyte, in which the polyelectrolytes are attached to a single point. Another kind of a structure is a spherical brush, on which the polyelectrolyte brushes are grafted on a spherical surface. So the motivation of this work is to understand the effect of the divalent or the monovalent ions, or the valency of the salt, on these polyelectrolyte brushes when these are attached on a spherical surface. So to understand this effect, we used a self-assembled structure in which we use the polyelectrolyte as a DNA polyelectrolyte. We use this because DNAs can have 4 types of bases: A, T, G, and C. So these can form Watson-Crick base pairing, which are very stable. So we use this property to form a self-assembled structure. What we do is we have two different nanoparticles with different DNAs attached on them, and A and B. So the outer part of this DNA strands have can form the Watson-Crick base pairing, and the inner part is the single strand DNA. So we try to understand using this to what will be the effect of the divalent or the monovalent salt. So 3 systems have been formed: the system A, system B, and system C. System A has the total number of monomers till here at 30, and the system B has 50, and system C has 65 number of bases. The outer part has a 15 number of bases, so which can form the Watson-Crick base pairing, and we can design this to form some self-assembled structure forming BCC or FCC crystal. So to understand this effect, we use a small angle X-ray scattering source. A small angle X-ray scattering source, one gives this equation gives the scattering intensity, which has the P of Q and the S of Q. P of Q gives the form factor, and S of Q gives the structure factor. Form factor gives the interparticle correlation, whereas the structure factor gives the intraparticle correlation. So as we can see that with the increase of the salt concentration, there is a peak shift in the scattering density, structure factor. This peak shift indicates that there is some phenomena which is happening, and which in the crystals, and the crystal size is decreasing. From this we can calculate the brush length depending upon the crystals. So these are the BCC crystals. So depending upon the system, we can calculate the nearest particle size, and from which we can calculate the brush length. So here is a calculation of the brush length with the introduction of the salt. So you and with the this is the change in the brush length with the increase of the salt concentration. Alpha gives the power law analysis for this. So two types of salt have been introduced, NaCl and MgCl2, so to the self-assembled structure. So we can observe that firstly, that the slope, this alpha values are different for the NaCl and MgCl2 Mg12 system. For also with these values approximately double to that of the NaCl. So basically we can assume that there is some charge screening is happening in NaCl, but in MgCl2 case there is some another effect which comes into play. So to further to understand the effect of this, we use the modified version of the Dowd-Cotton model. So Dowd-Cotton model initially was for a star-like polyelectrolyte, which I explained in the introduction, that that these modify which does not include the effect of the sorry does not include the effect of the spherical surface. So to include the effect of the charge of the spherical surface, this equation has been modified by the another author, Hariharan, and that where h is the brush height of the system, r is the radius of the nanoparticle, n is the number of bases. So we have used three different systems, so number of bases will also differ. Alpha A is the monomer size, K is the proportionality constant, and sigma is the density of the number of monomers. So sigma for our system is 0.228. So which gives approximately 60 to 70 number of DNA strands on a single nanoparticle size of a 10 nanometer of 5 nanometer radius. So this is the modified equation, and we observe that with the increase of the we observed that this equation fits to our data, giving that there is some additional effects which come into play for the MgCl2 system. So to understand this, there is another in this work, and they try to simulate the double strand DNAs and introduce the NaCl and MgCl2. So for NaCl, they observed that these two DNA strands were not maintaining this, were not as stable as compared to the MgCl2. So even at a very high salt concentration, the chain length was, the interparticle distance was not stable. You can see with the increase of time, there has been some fluctuation. But for MgCl2, even at a very low salt concentration, these double strand DNAs were closer to each other and maintained that for almost the whole time of the simulation. And for at a very high salt concentration, they almost come closer to each other and do not move apart. So so there is some additional effect which comes into play for the MgCl2. So this effect is ion bridging. So you can observe that at a very low salt concentration, these are almost in the extended region. But as we increase the salt concentration, you can see that these Mg2 plus ions can form a bridge between these two chains. So this can lead to a faster collapse in the system. And in this work, they also observed that with the increase of the salt, with the introduction of the MgCl2 ions, these two can bridge between the two DNA chains, with leading to an intra DNA ion bridging. This is chain bridging. So further to quantify this effect, we use this equation to understand this, where delta H is the brush height for the NaCl minus the brush length for the MgCl2, and from this we can calculate the ion bridge. We can calculate the saturation values. So this saturation value is when this equation reaches the 99% of this equation. So we also observed that for system A, which has the least number of monomers, this saturation value comes out earlier compared to the compared to the polyelectrolyte, which is higher number of monomers. So we can assume that in this region, there is some ion bridging effect, and after which this this whole thing is dominated by the charge screening effect. Initially, it is dominated by the ion bridging effect, and also it depends upon the number of monomers. So to further to understand this effect, we used a different particle size. So if we increase the particle size, then there will be a decrease in the, and keep the number of the chains on a particle same, then there will be a decrease in the grafting density. So this can lead to a decrease in the chain length. But we also observed that as we increase the uh, ionic strength for the system, to a certain extent we see 0.25, the slope which was similar to that of the 10 nanometer particle system. But after a certain value, we see that there is a decrease in the slope, which is similar to that of the NaCl. So initially, our assumption can be correct that initially there is an ion bridging, and after a certain value, this ion bridging saturates, and uh, we reaches a charge screening if we reaches a region where the charge screening is dominated. And since also this particle radius, this brush length is very small, we can also say that after a certain point, these uh, these are pinned to the spherical surface. These polyelectrolyte DNA chains are pinned to a spherical surface, leading to a faster decrease, leading to a slower decrease in the chain length. So this is a comparison of the brush length in different conditions. So here for the bulk, and this is for a planar system, and this is for a spherical brush. Uh, this values for monovalent system comes up for our system also comes out to be in this range only, and for the divalent this comes out to be in this range. So I would conclude this by saying that for NaCl and MgCl2, we see there are two different effects which come into play. For NaCl, charge screening is the dominating factor, but for the MgCl2, ion bridging is the dominating factor for at a low salt concentration. And after a certain point, these chains are pinned to the surface, and there is not much decrease, and the charge screening is dominated at this factor. Also, if we increase the particle radius, these DNA chains will not be if we decrease the particle radius, these DNA chain, because of the electrostatic repulsion between the monomers, these will be in the extended state. But for a 15 nanometer particle or a higher radius particle, these DNA chains will be much more collapsed and will be closer to the surface, leading to a decrease in the particle size, decrease in the decrease in the chain length of the polyelectrolyte. Thank you. Any questions if anyone have?
Okay, thank you, Anuj, for your talk. If there are any questions, then I'd like to take it. So I don't see any questions from the audience.
Clarification actually.
Yes.
It's a good talk. I want to know, in one of the slide, I don't remember now, you showed that this magnesium ion is bridging the interaction between two parts of the chain. I wonder, I think maybe not this one. Can you explain a little bit more? You say there is an ion which, that slide.
Next slide. So what happened? So this one?
Yeah. Yeah,
so what happens is for the NgCl2 ions, because of the higher charge valency, these ion can bridge between the two phosphate backbones. So here you can see there is one particle and there is one particle. So these can bridge between these two chains, leading to a compact structure of the DNA chains.
But that can also happen at other sites, right? Why it is specific to those sites, or it can happen anywhere?
So it can happen at these sites only, I think, because phosphate MgCl2 ions will bridge between the phosphate backbones because the phosphate have a charge on them in the DNA chains.
Okay, thank you.
Okay, thank you, Anil. Since there are not any more questions, I'd like to thank you on behalf of the audience, and let's clap for Anil. And with this, I will like to invite the next speaker, Dr. Chandan Kumar. He is a postdoc in the department and he's going to talk about self-assembly of anisotropic nanoparticles at air-water interface. However, I don't see Chandan in the Zoom room. So, Sanjay?
Actually, he is here. He told that he is here. I don't know. Maybe some other account he is here. We need to call.
Yeah, because I
Chandan,
don't.
are you here? Can you hear me? Actually, I called him. He told he is inside of Zoom window. I am also not seeing.
I don't see his name here.
Yeah, yeah. Sometimes people enter with other name, other account. I don't know. Let me call. I'll call.
Yeah. So, Chandan, are you there? Chandan, we can't hear you. Can you please check if you muted yourself?
Hello, what's happening with Chandan Kumar?
Someone has the screen. So,
Hello. Please rename. मैं rename कर देता हूँ. वो
I am trying to unmute him from here. He is muted.
Yeah, मैं rename भी कर देता हूँ. Actually, some other name. Chandan Kumar. Yeah, right. Go ahead.
Chandan, you're muted. Can you please unmute yourself? I am not...
You can also do.
Hello.
Yes. Okay. Yeah, we can hear you now. Also.
Okay. Thank you.
Chandan, we are running a little late since of this technical issue. So you have about 13 minutes to finish this. Okay. So
Okay, ma'am. Okay, ma'am. Thank you. Good morning, everyone. I thank the organizers for giving me opportunity to share my ongoing research on self-assembly of anisotropic nanoparticle lipid bilayer composite at the air-water interface. Hello. So here is the outline of my talk. I'll briefly introduce my subject line and followed by experimental method which I have used for this to carry out my experiment, and then I discuss result, which is basically from static and dynamic measurements, and then I'll conclude my talk. So variety of materials such as paste, emulsion, suspension, colloids, slurry, paints. Uh, they are in their intrinsic form. They are not in their natural form. They are not uh, suitable for for industrial usage, and for which we need to manipulate its viscoelastic parameter. So depending on its concentration, it can show a variety of shades such as sol, gel, and glass. And all these materials are broadly hello. Can you listen? Hello?
And then we are able to listen to you, but there is some background noise.
No, someone from this organizer calling me. That's why.
Oh, is it? Okay. Okay, let's
Huh.
continue.
So, rheological behavior of such materials are highly challenging uh, because of involvement of so many controlling parameters. Specifically, talking about time dependence, where structure evolve over time, and situation becomes intriguing because of specific interactions between involved means involving molecules. And understanding of this rheological behavior of soft glassy materials are important because it can have variety of application include which I have listed above. So materials involved for this study were two different lipids we have taken to form stable bilayer at the air water interface. These molecules, these lipids molecule were DMPC and DMTAP, and its molecular weights are listed here. And third, we have taken leponite. Leponite is a well-known material, a clay particle, which is very its phase behavior and its gelation property is well established in literature, especially in 3 dimension. But there are very few studies which has been carried in 2 dimension. So our main motive is to study gelation kinetics of leponite at in 2 dimension confinement. So to form a 2D assembly of leponite, what we do is we spread a mixture of DMPC DM tap, in which DM tap is a charged molecule which attracts leponite towards interface, and leponite is injected in this subphase, and over time what happens because of electrostatic interaction, these leponite particles uh, come and absorb at the air water interface and form a 2D assembly of leponite, oh, which we can uh, characterize through various uh, experiments, basically the static and dynamic measurement, as well as to study structure. We have taken we have transferred these monolayers and characterized its studied its morphological characteristics using AFM. So I'll go to results, which is separate, means, this, separated in as a static as well as dynamic measurements. So first, static measurements are basically time independent measurements. Here there is no involvement of time, and whereas dynamic measurements we have involvement of time, and structure evolve, this property evolve over time. So that this surface pressure mean molecular area of these two lipids which we have taken is compared here along with its uh, static modulus property. So here you can see both, means there is slight variation in their mean molecular area. This DM tap having somewhere around 100, where angstrom square, whereas DM tap, uh, this lift off area is somewhere around 108, 110. So comparing this static modulus, we can very well see that this static modulus of DM tap is lower than DMPC. So for this character, among these two lipids, DM tap is softer than DMPC. So these here we have compared the mixture one. In this the first figure A, here DM tap composition has been, is mentioned here, 0.1. This molar concentration in DM tap is very less here, whereas in this case we have higher concentration of DM tap. So we don't see when there is less concentration of DM tap, we don't see any shift even in when we have injected leponite in the subphase, whereas when you have higher concentration of DM tap at the air water interface, we clearly see a shift in mean molecular area. And in addition to this one, when there is less concentration of DM tap in the mixture, we have if an effective softening of this modulus. This previous slide in which we have seen this this individual modulus of individual component is somewhere around 80 and 100, whereas this mixture of in mixture we hardly see it reaches around 75. So there is an effective uh, softening effect which is which occurs when you mix these two lipid. Also, when you add leponite to subphase, we have further softening effect seen in this one. So we can clearly say that for a for system in which DM tap concentration is less, we have dual softening, one softening effect, one from lipid mixture, and second one is lipid introduced due to leponite in the substance. Whereas on increasing this, on the other hand, when leponite is 100%, we 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 see an effective increase in this static modulus because because this because of adsorption of hard leponite particle at the air water interface. So access gives spin energy. This basically tells you about the nature of interaction occurring between the components and what happens over when we add leponite in the surface. So you can see this black one listed here is the ideal one, which which was uh, which was calculated using this linear relation of mole fraction and mean molecular area. So difference of these two, this experimental minus ideal one will give you access, and this is making use of this factor. We can calculate Gibbs free energy using this relation, where A is mean molecular area, X is mole fraction, and Na is Avogadro number. So you can see so when we as I have told in first slide, so when you add mix two lipids, so there is effective softening. So see here, these domains are vanishing here. This kind of softening is because of lipid mixture, whereas these domains break into pieces when you add leponite. So this side, on your right hand side, whatever you are seeing is your leponite, this softening due to introduction of leponite, whereas left side, the softening due to lipid mixture. Also, when you have this one uh, uh, increasing concentration of DM tap, you have increasing adsorption density of leponite nanoparticle. So from analysis of these AFM images, we have calculated this diameter as well as absorption density of AFM images of dimension 1 into 1. Why this one? Because these nanoparticles are clearly visible in this window, whereas for a larger screen, it is mid-side. You can clearly make out, but its periphery is distinguishing lipids with nanoparticle will be difficult. So coming to dynamic measurements, so here we have studied this one step relaxation process, where after reaching a certain pressure, you give a sudden stress strain of 10%, and after which you track its relaxation behavior over time. So figure A is difference of this one, uh, this delta pi, whereas figure B is this one, uh, variation over time. So that's what is shown here. In absence of leponite in subphase, we don't see any drastic change. Whereas once you have leponite added to subphase, you clearly see there is drastic change because of introduction of leponite, and this altogether alters the stress profile of the binary mixture. And because of introduction of this one, leponite in the subphase, it arrests this dynamics of this one. Because of this one, you see this reduction in relaxation time. Oscillating barrier experiment. In this experiment, this leponite, this assembly of leponite and lipid mixture is given periodic strain, and response was measured, and ratio of the amplitude of stress divided by strain will give you modulus of dilation modulus, and a phase factor through which you can decouple its real as well as imaginary part. So here you can see when we have less concentration of DM tab, we drastically see any this modulus are this magnitude of modulus are very low, whereas on on the other hand, when your concentration of a DM tab was high, yeah, and with leponite in subphase, you see very drastic change in these modulus values. And these modulus, comparing these modulus uh, with existing literature, these these uh, uh, these are characteristic of gelation, whereas lower concentration of DM tab gives you glassy phase, basically glassy phase. This whole picture can be understood using this picture. So when you have less electrostatic interaction or no electrostatic interaction, you basically this final result is particulated soul, whereas on the other hand, when electrostatic interaction is high, you get gel. So to conclude my talk, addition of DM tab DMPC lead to softening in static modulus, attractive interaction between DMPC and DM tab. When this was interpreted from this Gibbs free energy experiment, absorption density increases. Absorption density of leponite increases when we have higher DM tab. And dynamic measurement, high stress in leponite reacted samples, and evidences of gelation when you have higher DM tab in the concentration. Thank you. If you have any question, you can ask. Thank you for listening.
Okay. Thank you, Chandan, for your talk. Since we are already running out of time, I think we'll stop the session. And thanks again. And thanks again to all the speakers of this session on behalf of the audience. So I hand over the room to Sanjay now.
Yeah, thank you, Professor Sunita Srivastav, session chair this session. So can you just quickly stop the sharing, Chandan Kumar? Or
Yes,
let
it is already shared. Hello.
no, I am saying stop the sharing.
Okay.
Yeah, so you might have seen that chat box. I announced earlier in advance that we will have a quick photo session, group photo session. So those who are like, please on your video. So we will have a quick photo session. So our HOD sir suggested last day as we missed that thing. So today we will have several times. So please on your video. So Mr. Shangshakto and also Monica, please take the screenshot once all are coming. So please come up within 1 minute. So we also running late. Actually, we need to hand over the session to next. So anybody is joining? Okay, let's wait for 1-2 minutes.
There's no one in the waiting room.
Okay, no, I can't see anyone. So if I see, I can quickly do that. Professor KG Suresh, you are here. So please on your video. HOD sir. Yeah, thank you. So, Shangshakta, there is a 2 screen. You can see right on and 2. So please go from on to 2. 2 screen. I think you need to go on first, take a screenshot, go to second, take a screenshot. It
Sanjay,
might be
I am
live.
ready for the photo session.
Yeah, yeah.
Baskaran, do you see me?
Anybody is coming? If coming, please drop a message. So otherwise we can go ahead. Yeah, it's coming. So, Professor Aptavalom.
Yes, sir. How are you?
No, I am Sanjay speaking. Please on your video.
Yeah.
So we are having photo session. So please on your video if you like. Shangshakta, you don't want to on your video?
No, there will be many screenshot sessions, so maybe I will on my video in one of the sessions, not right now.
Sure. It's okay. So let's go ahead. Both of you take some screenshot. Shangshakta and Monica. So there will be independent backup.
Okay.
Hi, please.
So ready?
Yeah, ready.
Yeah, done from my part.
Monica. Done? It's done? Please unmute and tell that it's done or not.
Hello. Yeah, it's done.
Okay. So without any delay, so our next session is experimental photonics. I hand over the session to Professor B. Jagatap, session chair of photonics session.
Hello, welcome to the session 6 of SYMPHY. And we have a very distinguished speaker in this session. That is Professor Chandrabas Narayana. Is from JNCASR, Bangalore. This audience does not need introduction to this audience. Although for this younger members of the family, I would like to give a short introduction. He has been a part of chemistry and physics of material unit of JNCASR since 1998 and currently is the chairman of the unit. He has several honors to his credit, including the fellowships of Royal Society of Chemistry, National Academy of Sciences, and Indian Academy of Sciences, and is also a member of the editorial advisory board of Journal of Applied Physics. The topic of his presentation is High Pressure and Raman Spectroscopy Reveal New Topological Crystalline Phases. Welcome, Professor Narayan, to SYMPHY 2020, and I invite you to begin your presentation.
Thank you, Professor Jagtab. It's really an honor to be part of this SYMPHY 2020, and there have been very many distinguished speakers in this complete program, and it is humbling to be part of such a august set of speakers. I would like to especially thank Sanjay for being the main reason why I was actually able to join this, and he has been following it up very extensively and trying to make sure everything goes smooth. And we did have a trial a day before, and it went very well. Now, I would like to make some small prelude to this talk. Basically, I'm going to be starting from basics, and the experts, I would like them to pardon me for being too much basic, so that the audience, which is actually diverse, as Sanjay had told me, would be able to follow this talk. Now, I'm going to share my screen, and I hope I am able to be seen by everybody.
Yeah, it's fine.
Yes, it's fine.
I'm going into the presentation mode. Did it come? Is it in the presentation mode?
Yes.
Yeah, okay. So let me put the pointer on, laser pointer. Yeah, so that's that. Okay, so the whole idea behind this particular talk is to say that there are three different aspects which I'm actually touching upon under the photonics. Actually, Raman spectroscopy comes under photonics, but I'm actually using another tool which is called the high pressure physics, which is very, very important in the study of materials or study of physics itself. It has actually brought in a huge number of new phenomena which have come through physics. And of course, all of us know that in 2016, this particular topic got Nobel Prize also, topological insulator. So I will start with a brief introduction to the topological insulator for the beginners, and then go on to say why I am using Raman and high pressure, and then go on to say some examples and show how it actually works in this particular system. To begin with, before I start, all of us know classical Hall effect, that whenever you pass an electric field and if you apply a magnetic field perpendicular to it in a semiconducting system, you can actually create electric field, and that electric field actually produces charge deposition, and hence a Hall voltage is created, and you get Hall current, Hall voltage, and also Hall resistance. This has been taught to us from right from 11th standard onwards. But very interestingly, after some time, people started looking at systems which are very, very thin. So when we go into a very thin film, that means in the Z direction, you do not have any possibility of electrons to move. And in such a situation, if suppose we apply a magnetic field, what we observe is a very, very interesting behavior that is called the quantum Hall effect. Basically, the conductivity or the resistivity actually shows quantizations in the system. The reason is that as soon as you apply magnetic field, your electrons being quantum numbers actually get quantized, the electric field. And as you increase the magnetic field, you start pushing one after another through the Fermi surface to create a quantum phenomena, and you will get increase in current. And this is what is called the quantum field effect, quantum Hall effect. Now, when we actually apply magnetic field on an electron in a classical way, it will actually produce cyclotrons. And these cyclotrons will actually be circulating like this, so there won't be any currents flowing. But what happens, because this is a quantum system, when it comes to an edge effect, as soon as the electron reaches this edge, because of the time reversal, the momentum actually gets reversed. And the momentum reverses and it starts producing a movement in this direction. And it completes these movements and it comes out. So the electron starts moving in this edge at the edge states. And this produces edge current. And because electron moves only in one direction because of a particular magnetic field, you actually have a surface state which is created. And this is what is responsible for this quantum Hall effect. And this got also a Nobel Prize in that time of this system. So basically what happens is it is quantizing the electrons, and it actually produces E square by H as the quantum number for this conductance, and that increases with magnetic field, and this number is Chern number, and that is actually is the topological invariant number which is used in the case of this in quantum Hall effect. But interestingly, when we come to a topological insulator, before that, I would like to say that this is an example of topological phase transition, where we are taking a cup which is actually having all the surfaces, and this hole is the hole retained in the donut also. So you can go from a cup to donut without actually breaking any surface. This is called a topological transition. This is the transition we are talking about. Similarly, in case of quantum systems. Now, in the case of quantum systems, where we have upspin and downspin associated with magnetic, with electrons, and if suppose you have a spin orbit coupling, then it produces a magnetic field. And when it produces a magnetic field, so intrinsically there is a magnetic field, the spin up and spin down electrons actually start behaving differently to the spin orbit. So as in the case of quantum Hall effect, I said at the edge state, because of time reversal, the spin up may go in this direction and the spin down may go in this direction. So basically there are two different types of currents which are produced in the surface when you have a two-dimensional topological insulator. So here the difference is between the quantum Hall effect, where you had an external magnetic field, you are actually having a spin orbit coupling producing the magnetic field, producing depending on the spin of the electron, we can actually have the currents either in this direction or the other direction, and the net current will be depend on if these are unequal, then that is the direction of the current which you will be seeing. And here you will start seeing surface states which have two types of surface states. One is because of the upspin, another one is because of the downspin. So in the bulk it is an insulator, but at the surface it is actually you are having a conduction state. So it is conducting in the surface and bulk. Now in three-dimensional, it will look like this, that it will be surfaces which will be conducting along this direction and this direction. So you will have surface currents in 3 dimension. And this is the Brillouin zone. And around the Brillouin zone, you will have the Dirac cone and the helical polarization of the electrons present in the system. So when we actually look at, we can transform something from a trivial insulator, which is actually having a band gap, to a Dirac semi-metal, which is actually having a Dirac cone, where the electrons actually behave ballistically. You can see this is actually a hyperbola or parabola, and here it is straight line. So electron goes ballistic. In a Dirac semi-metal, the electrons move ballistically. And in the case of a topological insulator, there is a bulk. It is actually supposed to be an insulator. But as you go there, you actually develop surface states where the electrons can be ballistic. So now we produce upspin and downspin electrons, and no upspin electron can become a downspin electron at any given time. So that is, you produce surface states which are dissipation-less current. Now, if you can control one of these electrons, then you can act by using a ferromagnetic system or something, you can actually populate one type of electrons, then you can actually have spintronic systems created. And that's why this is very, very important. And people are interested in room temperature systems. Now, the best way to find out whether you have a topological insulator phase is by something called angle resolved photo emission spectroscopy, which basically is you send in X-rays, which are actually of high energy. You can knock off the electrons at different momentum vectors, and you take this energy sensitive device, which actually is dependent on the radius of this will depend on the electrons which are coming with the particular kinetic energy and charge, and it will actually produce different points the detection. And this will tell us what is the energy, kinetic energy of the system, as well as the number of emitted electrons in the system. And that gives me the energy dispersion and the Fermi surface. This is the way actually we can directly envisage the Fermi surface as well as electron dispersion. An example of that is this way. So this is your K versus E, and you can actually find out how exactly the electrons are distributed in the different wave vectors, and you can actually find out all the electronic density of states of the system. This is the direct way. One of the biggest challenges in this is that you have to have a sample which is freshly cleaved, and you should be having all, it should be at ultra high vacuum. This is the only way we can actually find out the electronic states exactly. And this is a big challenge. It can be done only on a freshly cleaved samples. Now, when we are actually having samples with an environment around it, which will be what I will be discussing, it is very difficult to do ARPAS. So there is no way we can actually find out directly the energy states of the electron itself at different momentum vectors. So we need to use indirect methods, and that's where I bring in Raman spectroscopy. So quick tutorial on what is Raman spectroscopy. Basically, it's a light matter interaction. So major things which happen is transmission, then reflection, and luminescence, and absorption. These are the four major things which happen in your system. But these are the major systems, but one of the things which is the reason why we see each other is because of the elastic scattering. That means when light falls on the material, it scatters the light in all directions, which is different from reflection. And this scattered light is the reason why we see each other. And we actually do not have any change in the energy of the light. And that is why it's called elastic scattering. But along with that, you also have shifted frequencies. This is called inelastic scattering, just like inelastic collision. There is a change in energy, and that change in energy is related to certain properties of the material, and that is what I'm going to discuss. To prove that it does happen, here is the elastic scattering of light. You are putting blue light, and the light is coming in all directions. You can see this is a transparent liquid. If it was not doing any, it is only doing transmission and reflection, you cannot get it at 90 degrees. The reason why we see it as white light is because it is highly intense and your camera is saturated. And that is the reason why it is looking white, but it is actually the blue light coming in 90 degrees to it. So this is the elastic scattering of light in all directions from the liquid. Now, if I filter out the elastic scattering, you can see that elastic scattering from the dust particle is removed, and I can see there is shifted frequency. And that means this is the Raman scattering, which we can actually directly see without any problem. So basically, the problem is that if you have elastic scattering, that is no change in the energy, then the Raman scattering is a very weak phenomena. You can see that 1 in 10 to the power of 7 photons elastically scattered is inelastically scattered. So it's a very, very weak phenomena. But it's a very useful tool because you have Avogadro number, and Avogadro number actually beats this, and we can actually see with high sensitive detectors, we can see this Raman scattering. And that's why it's used. And in general, Raman scattering can happen because of rotational degrees of freedom of a molecule or vibrational degrees of freedom, and also electronic states. These three are the different components of Raman, and they come at different energy scales. So you can see this is due to the rotation, this is due to the vibration, and this is due to the electronic transition. So all of these have different energy scales, and that is what we are doing. Today, we will be only concentrating on vibrational contribution to the Raman. So in general, vibration is very, very unique depending on the molecules. And here is an example of HF and HCl. You can see that the difference is in between F and Cl is major difference is the mass. And you can see as the lighter the element is, you can actually see it is much more energetic. And that is normal. And that is why this energy, which is given in centimeter inverse, and a conversion factor for energy is given here, 8,000 centimeter inverse is roughly 1 eV. And this is about 500 milli-electron volts. And this is about 300 milli-electron volts. So you can see as the mass increases, you will have energy decrease. And here is a water molecule which is non-linear, and I have specifically taken non-linear. So you can see this is symmetric stretching, this is asymmetric stretching, and this is symmetric bending. Any molecule in the form of water molecule AB2, and that molecule would actually have only these vibrations, and the energy will be different for each of them depending on their mass and the spring constant associated with it. As in the number of molecules increase, number of vibrational states increase, but it doesn't have directly, there are interesting behaviors when you increase the number of atoms. Here it is symmetric stretching, asymmetric stretching, symmetric bending, and asymmetric bending. And any AB3 molecule will have these kinds of vibrations which have the same structure. So it is very easy to see that vibrations are directly a fingerprint of the molecule. I have increased the number of elements in this. There are 7 elements and number of vibrations increase. But you can see that the number of vibrations increase, but it doesn't increase substantially because this molecule is very, very symmetric. The more symmetric the molecule, the less number of vibrations will be there. So a symmetry of the molecule can be found out if I replace one of the F by Cl, this number of vibrations will increase because the directions in which we look at difference will be seen in the vibrations. And that is why you will have degeneracies lifted, and that is how you can actually find out whether a molecule is symmetric or asymmetric. Now, why does the light interact with matter? Because you all know that if you take a molecule as a diatomic molecule as 2 balls with a spring, where the spring is the bond stiffness and mass is the mass of the electrons, then the frequency is given by simple harmonic oscillator as root k by m, 1 by 2 pi root k by m, and m is actually the reduced mass. And that is what is given here. So this is what gives you, as mass increases, the frequency decreases. As spring constant increases, that means bond stiffness increases, you will have higher frequency. So this is how a classical system would look like. But when you actually put in electric field, which is coming from the electromagnetic radiation, this electric field can be given as time dependent and space dependent. And now electric field can be a cosine or a sine or a x to the power e to the power of I kx kind of a system. That is how you have represented. So it is an oscillating function. And since electromagnetic radiations happen to be traveling with velocity of light, whereas the molecules are moving with velocities which are very, very small. So at any given point of time when the light is interacting, you do not have any change in this position. And that's why we ignore this point, and you can actually see that E is equal to cos omega t in future I will be using. But what happens when you have an electric field? Because the molecules are charged, you have positive charges due to the nucleus, and electrons are negatively charged. As soon as you put an electric field, the electric field will shift the charges. And naturally, nucleus is very heavy, so it is electrons which will move maximum, and instantaneously you will have a dipole created. Now, this dipole is actually the induced polarization, causes an induced polarization, and this induced polarization is directly proportional to the electric field which actually created it, and it depends on the polarizability. And this polarizability is the polarizability of the electron here. And now this is an oscillating function. So this dipole is an oscillating dipole, and if nothing, this is a constant, this will actually have the same frequency as the frequency of the exciting light, and this is the elastic scattering. Because any oscillating dipole produces electromagnetic radiation. This has been taught to you from 12th standard onwards, that any oscillating dipole will produce electromagnetic radiation, and the frequency of that will be this. And this is what is the elastic scattering. But in fact, the electric dipole, that is polarizability, is not a constant. The reason is because if you have a vibration, the electron will have to move with the vibration. Hence, the polarizability will be a function of this vibration. And this vibration has a coordinate, which is because simple harmonic oscillator, and this coordinate is oscillating. So there is a frequency associated with it. And now, because this is very, very small oscillations, you can actually expand the alpha as a Taylor series. So it is alpha naught plus dou alpha by dou q at q is equal to equilibrium times q plus dou 2 alpha by dou q square at q is equal to equilibrium into q square plus and higher terms. Since q is very, very small, I am ignoring the higher terms. But if q is small, but E is very large, I have to actually look at higher terms also. This is the second order, and this is the third order, in fact, when you go to q cube terms. So this is the first order Raman, which we are talking about. So I will stick to first order, and I will substitute back all the values here. And suddenly I see my oscillating dipole is actually having one frequency of the excitation, but it also is a frequency of the vibration as well as electric field, both of them. And you know that in a trigonometry, cos A into cos B is written as cos A plus B and cos A minus B. Suddenly you see your dipole is oscillating with three different frequencies. One is omega L minus omega M, and omega L plus omega M. This is the Stokes-Raman, and this is the anti-Stokes-Raman. And this is how every vibration will produce two different types of frequencies, and these will be actually unique for a particular vibration itself. And the selection rule is, if this dou alpha by dou q happens to be 0, this is Raman inactive. And if this is non-zero at equilibrium, then it is actually Raman active. So this is how we can actually see when you are compressing the molecule, the electrons are compressed here, and that means the polarizability is very less, and hence alpha is small. And when it expands, the polarizability is higher. So it is actually a monotonic function with the oscillation of the molecule. And hence, the slope at x is equal to 0 will be non-zero, and hence it is a Raman active mode. And this is how both diatomic molecules will have Raman active modes. The moment you have a molecule, linear molecule, when it is expanding, you are again same situation. The electrons, when they are compressed, the polarizability is less. When the electron is expanding, polarizability is high. So hence, this is Raman active. But when you are actually compressing in one direction and expanding in another direction, so the polarizability is higher in one direction than when it is in equilibrium, and the in reverse happens. So it is like a parabola. And now if you take a slope, it is 0. So it is Raman inactive. Similarly, for bending, it is also Raman inactive because it is actually polarizability is forming a parabola, and at the equilibrium, it is 0. And this is what happens. And now you can see in water molecule, you can see that the dipole is actually causing alpha is actually non-zero at every equilibrium position. So all the modes are Raman active modes also in this case. Now, this was easy. We never use quantum mechanics at all. And we can see that this is very easy to understand Raman scattering. But the problem is that this is the quantity which tells you the intensity of the Raman line. And this intensity happens to be same for Stokes and anti-Stokes. But if I actually take the real anti-Stokes and Stokes-Raman, I find that the Stokes-Raman is much more intense compared to the anti-Stokes-Raman. This is because of the factor that you actually have a Bose-Einstein's factor in it, and that is where the quantum mechanics needs to come in. And you can see that the intensity ratio for a 400 centimeter inverse is 0.01 time. That means Stokes is very, very intense compared to the anti-Stokes. So this is where the quantum mechanics comes, and that is basically the dou alpha by dou q term in quantum mechanics is a perturbation theorem. You don't have to worry about this. I'm just going to go through the physical picture of it, when light falls on it, the electron absorbs, and electron goes to an excited state. Here, I have written it as virtual state because as an excited molecule, your eigenstates can actually cause a linear combination of it. And those states will be available for the light to actually access, the electron to access. And these are called the virtual states. And since these are very short-lived, they come down instantaneously, creating elastic scattering. Now, once they are excited, they can also, because of a strong electron-phonon coupling, they can actually create a vibration state. And once they create a vibration state, they lose energy and they come down. And this is the Stokes-Raman, redshifted. Now, the reverse is also true. An excited vibration state can give energy to the electron. When it comes down, it gives you blue shifted, and that is actually called this anti-Stokes. Now, from our knowledge of the population of these states, ground state is always maximum populated compared to the excited states. So this transition will be much less compared to this, and hence Stokes-Raman is always very strong. Now, why do we actually use Raman for electronic transitions? Because we were talking about topological insulators, electronic transition, because whenever this Raman scattering happens, you are actually having an electron-phonon term. And this electron-phonon term is very, very strongly coupling between the electron and the phonon. And that is the reason why any change in the electronic states can be picked up by Raman. This is how Raman actually did the experiments. Today, we can actually make simple Raman spectrometers by actually taking a laser, which is like the laser pointer which we have, and you can actually pass it through a sample and collect it through a fiber and disperse it and take a camera and take a shot. And you can see this is the elastic scattering, and these are the Raman scattering. And if I actually digitize the data, you can actually see the Raman scattering present. So it is so simple to actually make it, and that's why now a lot of use of Raman is seen. And this is a simple system we have developed in our lab to just do Raman scattering from any sample in the system. Now the question today is, can we actually have a phase transition created by taking an insulator and then create a topological insulator? This is called the topological quantum phase transition. This is because we can actually tune the spin orbit coupling, and the time reversal symmetry exists, and that gives you the edge states. That is the surface states in the system. Now, theoretically, how do we find out whether it is a quantum phase transition? That is done by the fact that you have something called the topological invariant state Z2, which if it changes from 0 to 1, what is a topological invariance Z2? It is basically calculating all the points where there is a time reversal invariant momenta points. These kinds of invariant momenta points are there, and that each of them is given by -1 to the power of u. And if it happens to be 1, then it is topological insulator. If it happens to be 0, then it happens to be topological, it's a trivial insulator. And for this, you need two things to happen. One is the band inversion. That means the characteristic of at the momenta point where the inversion takes place, the valence band characteristic is given to the conduction band. Conduction band characteristic is given to the valence band. That is the band inversion. And also you need the parity of the bands to change. And these two, if it is satisfied, then only you have a topological insulator phase. And now this can be created by spin orbit coupling. And spin orbit coupling is very, very strong when you have heavy metals. So in general, these kinds of materials, bismuth, tellurium iodide, bismuth, tellurium bromide, antimony, selenide, all of these are heavy materials, and they have very strong spin orbit coupling. Now this can cause them to have room temperature. You can actually, at ambient conditions, they will be a topological insulator. But if I want to find out, there is a possibility by doping, if I can actually create a new material, then strain is the best way to apply, and strain is nothing but pressure. And you know that pressure is nothing but force per unit area. And force per unit area is actually given as gigapascals. And to understand what is 1 gigapascal, which is equal to 10,000 atmosphere, I just take this example. If if an elephant is squatting on all four legs, elephant is weighing 5 tons, it actually produces 5 megapascals. Whereas a lady who is 60 kgs stands on a stiletto, which is basically about few centimeters square, and that gives you 6 megapascals. So that means an elephant squatting is much less pressure compared to a lady standing on a stiletto. And now to know what is a gigapascal, if you make that elephant to stand on that stiletto, you will find that 5 tons standing on a stiletto will produce 1 gigapascal. This is how you can understand figuratively how much is 1 gigapascal. And in 1 gigapascal, you can actually change electronic structures itself. So the pressure is a very, very clean perturbing agent, and it can produce quite a lot of pressure, change in the system, and that can change bond length, volume, hybridization, and increase in electron structure. And this is very easy to do because you can take diamonds which are very hard, which do not they are transparent to most of the electromagnetic radiations, and if you put a gasket material with a hole, you can see the hole is there and a sample inside, you can pass electromagnetic radiation and you can do most of the measurements, and Raman is one of them you can do. If you put a ruby in there, you can also do the pressure calibration, because ruby fluorescence is highly dependent on the pressure, and that can give you what is the in situ pressure. This is the vision of how the sample will look like, how the rubies would look like, and you actually put a pressure transmitting medium, which is like methanol, ethanol 4:1, which actually gives you hydrostatic pressures up to 10 GPa. So this is what we have been using to do most of our high pressure experiments. One example I will actually take here, and this is thallium bismuth sulfide. The reason we took it is thallium bismuth sulfide is a insulator, trivial insulator. But if you start doping selenium, as I said, it is actually a spin orbit coupling material because high Z material, you start seeing the band gap reduces. But at exactly around 0.6, you start seeing that you have created surface states, which means it has become a topological insulator. And we know that thallium bismuth selenide is room temperature, ambient conditions topological insulator. So what we have done is we have increased the spin orbit coupling, and we have created from a trivial insulator to a material which is topological transition. Now, this is possible also with pressure, because when you increase the pressure, you are also increasing the spin orbit coupling. So this is why we wanted to do it. And the reason why we use Raman and X-ray is that X-ray tells me if there is any structural transition. If there is no structural transition, that means the material is in the same electronic state. But if you have a structural transition, that means it is not the same electronic state. And that is why we would actually like to do X-rays. But also X-ray gives me charge density distribution, and that actually changes with pressure. And that can actually be also a good hint for looking at it. And Raman actually gives you this electron phonon coupling, which basically is related to both the frequency and its line widths. I will explain that in a minute. So here is the ambient structure of the material by X-ray. And as you increase the pressure up to 4 GPa, we can see that there is no change in the structure. But as soon as you increase the pressure beyond 4 GPa, you start seeing new peaks appearing. That shows that there is a phase transition. That means we do not actually consider any pressures above 4 GPa for our studies to see if we are actually having a topological transition. Now, when we do Raman, the only two Raman active modes associated with it is A1G and EG. And today we can do calculations and we can know the kind of vibrations which are associated with EG. EG is a doubly degenerate mode, and AG is the stretching mode along the C direction. Now, when we actually apply pressure, you also see from Raman that the Raman spectra changes after 4 GPa. You can see, but if you release the pressure, you can see it comes back to the ambient conditions. So that is a reversible structural transition. let us look at only the 4 GPa transition. So we are not going to look at the structural transition. Up to 4 GPa, we are plotting frequency versus frequency of the Raman line versus pressure, as well as we will actually plot width of the Raman line with the pressure. If there is no structural transition, no electronic transition, anisotropy in the crystal and phonon-phonon coupling, the phonon behavior is linear behavior. That means it will actually go as a straight line. But any change in the straight line shows there is a phase transition in the system. And you can see here clearly a single line cannot fit the peak. And if you are bold enough, you can also say that there is a transition around here. The reason I say that is because if I actually plot full width at the half maxima of the Raman line, you actually have 2 transitions in this system. And that is very, very clearly seen in both the cases. And that is why I actually say there is a transition in these 2 places. And that means these are not structural in nature. So it has to be electronic in origin. So this has to be electronic. But Raman can tell you only that it is an electronic in origin, but it cannot say it is topological. For this, we need to actually do calculations. And when we do calculations, we did it with Umesh Wagmare and his student. And what we did is we did the electronic density of states. And we find that at gamma point here, and also at F point, we are going to see as you increase the strain pressure, you see that there is a band overlap happening. You can see the band overlaps happen. And here is a band overlap, and there is another one around F point. And these are the 2 up to 4 GPa. We have actually done this band overlap. And when we plot the pressure versus band gap, you see that at gamma point and at your F point, you actually see that we have created 2 possible transitions. And this is the band overlap. Now we calculate the conduction band and valence band densities. As you go from a gamma point, you see a reversal of the conduction band, valence band nature. And that means there is a band inversion happening here. And again, when you go to the F point, there is a reverse band inversion. And that is why it actually drops back. And now you can see that there is a Z is equal to 0. And Z is equal to 1, which is creating a topological insulator phase. And now it comes back to an insulator phase. Now, when you have 2 points actually going, you actually have to look at the churn number. And the churn number tells you that it is even number. And that is why it is a topological crystalline insulator phase. It's an insulator phase, but it is a topological crystalline insulator phase. This is what is the scene. Now, quickly in 2 minutes, I will actually show you another example where the motivation comes from a calculation where we have taken titanium telluride, and it is a tetragonal system. And when you actually calculate at 3 different points, gamma point, A point, and L point, you actually see band inversion in the system. And it was very interesting to see that the band gaps actually pass through this. And in pressure, it is actually showing that there are topological insulator phase, and it is a cyclic condition. And they do not find any phase transition in the system. And that is why they predicted that multiple quantum phase transitions can be possible. So it became a very interesting system. But when we actually did the X-ray, we found that at around 8 GPa, the material actually undergoes a phase transition, which is very, very closely related structures. And when we actually looked at the literature, in any case, when we look at isostructural system, we also found that iridium telluride actually undergoes around 7.7 GPa, a structural transition from a tetragonal system to a monoclinic system. And that means we cannot have any data after this because the electronic structure is completely different. So we will concentrate up to 8 GPa only. Now, when we look at the C/A ratio of this system, there are 2 transitions which we observe, one at 2 GPa and another at 4 GPa. And we see the structural transition actually happens at this point. This is because this is a layered system. And so the C and AB are actually anisotropic. And when you start applying pressure, there is a change in the electron densities around it. And that is what gives you a C/A ratio at this point. So there is a charge density fluctuations around it. Now, when we look at the Raman, we find that it is also a tetragonal system, so it should have 2 Raman active modes. But to our surprise, we see 3 Raman modes. But the central mode is very interesting. We will talk about it quickly. That is called the zone folding mode. That is when you have a periodicity broken, then you will actually have Brillouin zone actually halved, and then you create new bands around the system. And this is called the zone folding. And how did we verify this? Because if you take a single crystal, very large single crystal, you have only 2 peaks. But when you take a multi-layer system, exfoliated film, you actually get this zone folding mode. So this is how we actually found out that. Now, when we do the Raman measurements and plot Raman frequency and the FWHM, you actually see changes happening around 2 GPa and 4 GPa in both the cases. And that means we have actually, from the X-ray and Raman and from the calculations, we have seen that there are 2 transitions happening. One is the topological transition, and then it goes into a trivial insulator. But since there is a phase transition, we cannot actually talk about another cycling happening in the system. And this is how we verified the system. Why does this actually go into a phase transition? So one of the things which we looked at it is that we actually looked at the tellurium distance between them. It is ionic when it is at ambient conditions. As you start applying pressure, you start seeing that this tellurium actually starts having covalency built up. So it is becoming quasi 3-dimensional in this region. And that is also the reason C/A ratio doesn't actually change much. So the anisotropy in the system is lost, and that is what happens. And because it cannot sustain for a longer time, it has to undergo a phase transition in the system. And that's the reason why it happens. So basically, now I'll conclude by saying that I thank all my collaborators, basically Umesh and Sopan and Kanchana for the theory, and Sebastian and Kanishka for the samples, as well as Karmakar for some transport measurements which we did, and also thank DST for Electra Petra for the X-ray diffraction studies which I performed. Thank you very much. These are the students who actually helped me in doing all my experiments, and they are the reason why I am able to present this. And this work was completely done by Rajaji, who is actually currently in Harvard doing his postdoc there. Thank you very much for your kind attention, and I would be happy to answer any questions.
Thank you very much, Professor Narayan. The presentation is open for questions, discussions, comments. I don't see any comment in the chat box.
I have a question.
Yeah, please.
Baskaran.
Yes.
Yeah.
Chandrabas, it was a wonderful talk.
Thank you. Thank you, sir.
My question is about the last compound that you talked about, 1T PITE2.
Yes.
You know the sister compound PISU2 exhibits excitonic phase transition, exciton condensation.
Right.
So are you also sensing that in your pressure when you do the...
And I have not done titanium selenide yet. We have not done that because the band gap is slightly higher compared to the tellurium system. Tellurium system is 0.26 or 0.4, which is very important for our topological transition, because the band gap is little larger. It becomes difficult for us to actually make the band overlap happen. So that's why we didn't do it. But in the titanium telluride, we didn't. In the pressure experiments, we have not seen any observation of this from the Raman point of view. But it would be very interesting to look at from the transport behavior. So we couldn't do the transport in our case, but that is one thing which we would be very much interested in looking at, transport with respect to pressure. That is when we can actually see what exactly you are pointing out. That can be seen in the transport measurements, because we can see with temperature variation as well as pressure, we can actually see whether that is having these new electronic behaviors, which we can actually elucidate very easily.
Thank you, Chandrabas.
Thank you. Thank you so much.
Any more questions? Comments? Yeah, I have a small question. See, ARPS is the best system, as you said.
Yes.
And there are systems where you can synthesize the material and get the ARPS.
Yes.
Right?
Yes.
So what's the distinctive advantage? I mean, I have not understood.
Oh, actually,
surface contamination, will they not matter in the Raman spectroscopy?
Okay, so let me tell you, if you are actually wanting to exactly calculate the phonon dispersion for any system, even for an ARPS experiment for any system, you need to freshly cleave the system inside an ultra high vacuum.
Yes.
So, and also it should not be relaxed. The moment it relaxes, that means if you have cleaved it and left it for about a day or so, your electronic structure will change. So ARPS is only possible to be done with the high, ultra high vacuum, as well as with your system being freshly cleaved. That means it is not relaxed yet. But when we are doing a pressure experiment, you cannot apply a pressure without a fluid around it. If you have a fluid around it, you cannot create a vacuum. So ARPS is impossible to do. It is impossible to do ARPS because you cannot actually cleave inside a high pressure cell, and neither can, let us say if you are able to do an argon etching, but argon cannot enter inside through the diamond. It is impossible to do a etching. So you cannot actually create a new surface and relaxed surface, and you can actually not measure any of these measurements inside a high pressure cell. So that is the reason we need an indirect method. So we are using indirect method. Now, the advantage is electron-phonon coupling will exist irrespective of whether the sample is, because the electronic states are always existing. So that will always interact with the phonon. And any changes in the electron-phonon coupling tells me that it is actually an electronic transition. And once it is an electronic transition, I do a calculation. Because of the calculation, I know what kind of electronic transition it is. That is how I verify. So it's an indirect method. So I first find out whether there is a structural transition or not, because the moment your structure changes, electronic density of states changes. So I cannot talk about the same electronic state which I started with. So I actually do a structural transition study. That means whether the system remains in the same structure, and then look for electronic transition, then do a calculation. All three of them together give me what ARPS would have given me. Exactly what ARPS would have given me, I would have got it. And that is why I am proposing that this is the easy way. Now, why do I do these experiments? Because when I am applying pressure, I am actually introducing strain. I can introduce strain by doping. So if I know, if I can dope the system with the right kind of elements, I can actually create at ambient conditions the same kind of a condition, the pressure system. So I am actually doing a chemical doping experiment by pressure. So actually, that is what is the simile. So basically, this gives me an idea that these materials, if I dope with the right element at ambient conditions, they would be topological insulators. That's the idea.
Thank you. The Anil Kumar has raised his hand. Yeah, please go ahead.
Yeah, Mr. Chandrabas, very nice talk. I want to have one information. You use a medium when you apply this pressure for this hydrostatic purpose. So is there any documented, work on how this medium affects the surface states? See, for example, when you have cleaving in an ultra-high vacuum, you see that, as time progresses, the surface state gets affected. Now we are dipping it in a medium. So is there any, studies on the influence of the medium on the surface states in this kind of materials?
In this particular case, we have not done any exclusive experiments to show that surface states are affected by the medium. But from my experience, Raman is very, very sensitive to any changes which is happening in the system. Now, the system which I am working with, my penetration depth of the laser is very, very less. It's a few lambdas. So I am actually looking at the Raman spectra of the thin layer on the top itself of the system. And hence, because at ambient conditions outside without the medium, when I do the Raman, and when I do the Raman within the system, I do not see any change in the frequency. If I don't see any change in the frequency, which gives me confidence that the medium is not actually interacting with the system. So this is one of the things which we have verified, because the same sample we do without the medium and with the medium, and check whether, because this is what we need to do when we are doing high pressure, that we have got the same sample inside. So without the medium, we actually take the spectra inside the cell, and with the medium, we take the spectra. And since this is an opaque sample, you are actually penetrating only few lambdas inside. And that is why we know that there is no effect of the on the Raman. And since there is no effect on the Raman, there won't be any electronics transitions happening in the system also. This is how we are verified.
Yeah, thank you. Thank you.
Can I ask one question, sir?
Yeah,
sure.
I have a trivial question because I don't know the field very well. So you said that for topological insulators,
yes,
the band inversion is a requirement. So I'm just wondering that what enables in those materials this band inversion? Is it the structure of the material enables the band inversion? Or how?
Okay, very good question. Actually, what we have seen is that many of the systems which have tetragonal systems with high spin orbit coupling. Basically, one of the major thing which is required is spin orbit coupling. Very strong spin orbit coupling should be there in the system. So that is why most of the systems are tellurium, celerium, bismuth, those kinds of systems are what is mostly used. And they are layered. They need to be layered because you are 2D topological insulators. Because 3D, very rarely we are able to actually see too much of effect of the 3D effects. So it has to be thin film kind of a thing. But instead of thin film, what we are taking is layered material. And layered materials generally, if the interlayer is van der Waal interactions, then it becomes basically the electronic structures are actually controlled by the layer itself. And these are the two things which are actually required for the band. And also the band gap of the bulk should be very much closer to 0.2, 0.3 EV. That is the kind of EV which, or below that, should be the EV. Then you actually develop these surface states. And these are the ones which are actually good candidates for topological insulator systems. And that's how we found that most of the best examples are bismuth selenides and those kinds of systems. Actually, I am sure Anil is going to touch upon some of these systems where he actually does strains in the system or introduces certain defects or certain things in the system to actually create topological states in the system. So, but I don't know whether he's going to talk about that. But he is one person who actually makes materials, thin film materials, and does a lot of such tailoring of the topological states. And that is how you do it. So basic criteria is the structure is very important. And the second thing is that high Z material should be there in the system for spin orbit curve.
Thank you. Thank you.
Since the talk has generated so much of interest, I am ready to give a few more minutes for asking questions. Are there any more questions? From the student community? Well, if there are no more questions, let's thank Professor Narayana for an excellent presentation. And I really enjoyed your presentation on the Raman effect. I think I should borrow your slides for my...
Yeah. Thank you, sir. Thank you. Thank you so much, Professor Jagtap. It is wonderful again to meet you here online. And it has been wonderful when I came there, also met you. Thank you very much. And Sanjay, thank you very much for this opportunity. Thank you.
Okay. The next presentation in this session is by Gangadhar SB. And title of his presentation is Unprecedentedly High Conduction of Triplet Excitons in Molecular Solids. May I now request Mr. Gangadhar?
Yes, sir. Oh, let me share the slides.
Yep.
So I'm audible, right?
Yes, you are.
Yeah. Just okay. So, good morning all. So today I will be presenting some of my recent data. Like the title is Super Transport of the Dark Exciton in the Polymer Semiconductor Solids. So, just a second, it's not moving. Okay, so outline of my talk is first I will give a small introduction to the organic LEDs and the motivation of the work and experimental techniques I used, and finally results and the summary. So why these organic LEDs? Because we already have the inorganic and the perovskites and all, but what is the small advantages over those things? The first thing is these are very thinner, lighter and flexible, because these are like generally the organic polymers. Okay, so conjugated polymers, this can give the facility for making it very thin. And the secondly, these things don't need a backlighting of like a LCD, because these are like the material itself are emissive and can cover the whole range of visible region, and can be made in larger sizes, because these can be done in operation as well as the solution process, where the spin coating and the inkjet method and all. And always these have the good field of view, and most importantly these are faster response time, than it can work in even gigahertz uh, frequencies. And some of the examples you can see here, the Samsung transparent displays they launched, and most importantly I can say the Sony TV here of the thickness of just 3 mm, including all the electronics. So these are few of the some just like important inventions. And here I'm talking like just want to show what are these materials, how it looks like. These are the polymers here. Just for some examples of solar cell and LED materials, some of the classified into small molecules and polymers according to their size and structure. So just want to show you how this LED generally works. So this is the general structure of the LED, which has the main emissive layer here. And for this emissive layer, of course, we have to give the input energy, that is electrical energy, to inject the charge carriers, hole and electrons. We have the other layers in both the side, anode, cathode, with some injection layers also. This is a simple structure. Of course, we have some more layers like blocking layers and transport layers and all. This is a simple one. So once we inject the electrons using like by applying the voltage, so electrons and holes from the cathode and anode respectively. So once it injects to the material, and it start travels through material because of the electric field. And once it meets the electron at the higher state and the holes at the ground state, if it meets on same molecule or the neighboring molecule, it can make a pair of electron and hole, the bind state of electron and hole. And these molecules don't have the free electrons, because these organic molecules have the very low dielectric constant. Because of that, there is a Coulombic interaction between hole and electron always. This bind state of electron and hole is called the exciton. So these are completely exciton materials, not the free charge carriers. So once this exciton forms, and this will recombine, and that will give the energy. So that energy corresponds to the band energy of like band gap of the material. And this is the glowing LEDs fabricated in our lab. So first, and then I told you this is the, like completely about the dark excitons. Excitons, I told you it's a bind state of electron and hole. But in these excitons, there are two types again, the singlets and triplets. So, but that depends on the spin orientations. For example, this is the typical structure of my energy level diagram of the material. Of course, there's a ground state that's always singlet, because anti-parallel always. So once I excite the sample using like example, I will take optical excitation using some laser. I will excite the sample, and one electron go to the higher energy state. And how this is aligning the spin. Generally, this is anti-parallel. We know that singlet, but after this excitation, some of the singlets, the excited electron can come to the triplets. How the triplets is actually, that is the parallel spin alignment. So we know that the in quantum mechanics we learn the anti-parallel spin singlet can have the multiplicity 1, when the triplets have 3, -1, 0, and +1. So, but and again the different transition, like once it excites the S1 state, it can come to ground state immediately using it can give the light, that is photoluminescence, prompt emission. But and again the disadvantage is there is no the T1 to S0 transition is not allowed. This is spin forbidden, and we are losing these triplets here. So this is the main reason where we are losing the efficiency of the LEDs. So, but the efficiency of the LEDs, I can give this formula like there are 4 factors: charge balance, outcoupling, and the PLQI. Apart from these two, there is one more important factor, that is KIS, that is the singlet formation ratio. For example, if I give to the device like 100 electrons and 100 holes, it can make 100 excitons now. But out of 100 excitons, how many are triplets? How many are triplets? According to the spin multiplicity, 25 are singlet, 75 are the triplets, because this is the multiplicity is 3. But triplets don't give the radiation easily, because here the transition is T1 to S0 state is, it needs the spin flipping. For that we need the very good spin orbit coupling, and generally spin orbit coupling in these materials is really low because we don't have high Z materials. But of course we have the electrons on nucleus, so because of that we can get the hyperfine coupling. So that small hyperfine coupling is sufficient to make these transfers like S1 to T1. This is possible. So now we are getting the triplets, but there are some other methods. Of course we can get these triplets as a radiative indirectly. That is one of the example is the triplet annihilation. This is the process. Like 2 triplets can combine, that will give the one higher triplet state. Once it goes to the intermediate T star, from that I can come to the singlet again because of the hyperfine coupling. Once it comes here, of course this one can emit easily. So now there is a process, inter-system crossing, TTA, and then this transition. So this takes a little bit time. This is a slow process. So again I will get the emission, but after some time. So I can see the TR EL of here. Like I will excite the sample with the electrical pulse of small time, then there is no excitation, but still I can see the emission with up to like 0.1 millisecond. So this all emission is because of the TTA, means I'm converting these dark excitons into emissive singlets. So in this way we can actually harvest the triplets also, because these are very important because otherwise the efficiency limits to just 25%. So I can use the remaining 75% triplets also in this way. So this is just I want to highlight why we need triplets, why the triplets are very important. So for that, in the whole, like in the next slides, just I'm going to talk about this triplets. Okay. So most of the, so in most of the materials, this triplets is really very localized. Generally, the reports you can see here, the diffusion coefficient of the triplets in the polymers is really low, in the order of 10⁻⁻⁶, -5 maximum centimeter square per second. But there are some materials, pentacene, pyridine, tetracene, these are small molecules and have a good order structure. So there you can see even 10⁻⁴ and 3 centimeter square per second. But generally, okay, if you compare these numbers with the inorganic and perovskites, these are really low numbers. And again, these numbers are enough to reach most of the applications. And parallelly, there is no harm in improving further, because once the triplet becomes more delocalized, and I can see a very good TTA, because TTA needs a very good triplet density and again a good triplet transport. So in next things what I'm going to study is, okay, in some of the materials can give even in the polymers I can see the very good numbers of triplet diffusion. So I will tell which I will select one of that material, and I'm actually experimentally studying this triplet diffusion coefficient in parallel and anti-parallel, like perpendicular directions. Like what is that direction I'm saying? For example, this is my substrate G, and these are the polymers, just typical polymer FABT, and just one FABT polymer, just I will represent from this rectangle. Okay, it can align in any direction, like G, H, I here. Okay, but generally, since these are very long chains, it is very difficult to stand vertically. It can form G or H structure in the schematic. But in the simplicity for time being, just I will take G structure. Okay, these are in the parallel to the substrate. In this one, there are two ways, like triplet can transfer perpendicular to this one, that is the pi stacking. This arrow is showing the pi stacking direction, or within the plane, that is lateral direction. So I will study using two different experimental technique. I'm calculating what is this triplet diffusion in parallel and transverse direction. So the first experiment is the angle resolved delayed electroluminescence. For this one, I used one reported optical model, the KSW et al. So in 2007. So in this paper, what they have done in this work, so the optically, this is completely geometrical optics now. Of course, this is I can show the device structure. This is emissive layer. The gray one is the emissive layer. Within this emissive layer, the dipoles are actually, I can keep anywhere in between, from this bottom electrode to the top electrode. But what they have done in this work, if the dipole is lying at the bottom completely, how the angle resolved emission is actually the angle resolved emission, means what is the intensity at different angles. I can measure it experimentally also. Okay, so this is in this model they are correlating how the angle resolved emission is depends on the dipole position inside the material. So if I have the angle resolved emission outside, so I can calculate the position of the dipoles using this model. So I use the same one, So this is my experimental setup. This is my device, and there is a glowing pixel. So what I will do, this is polarized converging lens, and I can collect the emission. So this whole setup can rotate from 0 to 180 now. So I can collect intensity at a different angle. So that will finally give the ARDL, angle result, but I'm collecting a different time delays because triplets are giving the emission after some time. So that's why I want the emission at some delay time and in all the angles. So I can get this experimentally. So I could see this. For example, you can see this schematic here. So once I inject the charge carriers, electron and hole, so electron and hole will distribute. That's a gray color shows the distribution of electron and hole. So where the overlaps, there is the excitons. So that excitons might be singlet and triplets, but I will consider only triplets here. So initially the triplet distribution is this. You can see the bluish color. If the triplet distribution is this way, how the angle looks like. So this I can simulate using the optical model. Okay, because I have the experimental ARDL and I can simulate the how the distribution actually looks like inside, but at a different delays. Okay, so with the delay, what will happen because of triplet diffusion? Triplets will diffuse towards the other end, so it makes the broader recombination zone. And the similar way, what happens outside? What will happening? The ARDL shape is actually changing. Of course, with time, intensity will decrease. I'm not talking about the intensity now. I will just normalize it with respect to intensity, but how the shape looks like, whether it is shrinking or broadening, those things I will check. So here is the experimental and simulated data. This is experimental, the first row. I did for 2 different thickness because there are many reports on this F8BT material. This is F8BT polymer. So if I were to mention, the material name is F8BT, polyfluorine based polymer. So there are many reports here. The actual efficiency is actually crossing the theoretical limit because of this TTA. So just interested in this to calculate this triplet, what's happening with the triplets here. So this is experimental data for thin and thick, and this is the ARDL, just this in polar, but I use the Cartesian just to see the small changes. Okay, at a different time, delay time, I could see the ARDL, there is small change even in the thin and thick. Similarly, using the optical model, I could see the same kind of changes, but here there's no time things. Okay, okay. So with different recombination zone, how the ARDL is changing. So by combining these two, experimental and simulated data, with recombination zone, my ARDL is also changing in this fashion. My shrinking and broadening, and experimentally also with different delays, shrinking and broadening. This is a very well matched even in thin and thick. So now I can correlate this recombination zone with the time. So the recombination zone, change in the recombination zone is actually denoted as a L, and my delay time is T. So using the 1D diffusion relation, so I can calculate the D values. So here you can see the number, it is reaching 10⁻³ This is really high as compared to the other polymers. So this is in vertical region. This is just to check the validation of my optical model. So I just compare with the other literature. Yeah, it is very well matching with my previous ARDL. And this is another experiment, AL imaging. Here, to probe the triplet in lateral directions. So this is experimental setup. So once I excite with the sample, this is my sample and zoom position, you can see laser excitation, and I'll excite the sample with very small time. The small space, the spots. So it will emit the light, and I can collect that emission back using CCD camera. Here you can see the once I excite the sample, and I can see the glowing in the spot because of triplet diffusion. So these are the typical images at a different delays, like 30 nanosecond, 504 microsecond delays. So you can see the growing in the spot. This is because of the triplets, and I can say only triplets because these are delayed fluorescence. There is no singlet because singlets will die within just 2-3 nanosecond in this material. So the D values, you can see the grow, FWHM is increasing with time. And by these two, I can using the 2D diffusion relation, I can see the D values of 10⁻⁴ region in lateral directions. So this is, but what's happening? Why it is actually the reason for this good number? I will just concentrate on the effective activation energy. Of course, you can see the very sharp rise in the absorption and decrease in the FWHM of the PL. That suggests the direct evidence for the very good packing of the materials, because it is getting more crystalline. I don't say it is perfectly crystalline, but getting order, because polymers are amorphous. But if there is some good packing of the polymer strain and ordering, that can increases the transport property. And the direct evidence is from Markers theory, I can calculate the triplet transport activation energy, what is the energy required to hop to the next state, like from one molecule to other molecule, if we want to transfer, what is the energy it needs? So that's the activation energy. Here I can do activation energy plus sigma. That sigma indicates the disorder in the materials. Okay, so including these two parameters, I will just calculate the effective activation energy because those two parameters control the transfer. So those values using the low temperature measurement, the delayed PL versus temperature. So I can see the effective activation is very low, like 21 MeV, which is comparable with the thermal energy available. Like room temperature thermal energy is around 24-25 millielectron volts. So it's comparable with that thermal energy. So the room temperature thermal energy is sufficient to hop to the next step. That's why this, because of this very good packing of the material, and that shows a very low activation energy, makes the triplets are more delocalized in these materials. So we are doing further study on these structural studies and all. This is just like the diffusion part we study. So the conclusive mark, like, yeah, these are the numbers and which are very comparable with our small molecules, not in like very few polymers show these materials. That depends on again the experimental technique we are using. But generally I can say it is reaching the 10⁻³ Sorry, I missed one, I think the number here. And the secondly, yeah, these are the conclusive mark, and there is one small isotropy I can see with thin versus thick. Oh, and that I can study using polarized PL and all. I have like some other data for that. Because of time constraint, just I will stop here. And I'd like to acknowledge my colleagues Mukwaida and Nakul for constructive input for this work, and my professor Dinesh Kabra for the guidance, and my whole group. Thank you.
Thank you, Gangadhar. The presentation is open for comments, discussion. We can have short comments, a couple of minutes. Well, I have one curiosity question.
Yes, sir.
What would be the limit for this diffusion coefficient? You obtained something like 10⁻³ that order, right?
Yes, sir.
So what would be the theoretical limit for such constants?
Like, sir, that depends on, like, it is actually varying. Even some of the materials can show up to 10⁻⁻1, like 0.1 and 1 also, like in like greater than 1 also. That depends on like some of the materials. The polymers generally.
No. When the materials means, what is that property that you are really looking at, which determines
the structural property? For example, polymers are amorphous. But if I go to the small molecules like P3ST or some other OLED small molecules, there I can see a very good crystalline structure of the materials. So if the order is really good, then I can go till like 0.1 or 1 centimeter square per second. But those things are really difficult in the polymer, since these are very long chain materials and very difficult to get the packing and the crystalline property. So, but still, if I use some, like in this material, what we are doing, we are using very aggregated solution. It's really like a 50 to 60 mg per ml, that like a kind of gel. So this kind of solutions, if I spin coat for like for thousands of speed and Anil for 1 hour, that gives a very good polymer chain packing. But generally, I can't restrict to the number, like it's only maximum this much. Of course, we can improve it by the processing conditions.
Okay. Thank you, Mr. Gangadhar. Now we go over to the next presentation. That is by Urvashi Bothra. And title of her presentation is Correlation of Nanomorphology, Structural and Spectroscopic Studies in Organic Solar Cells.
Am I audible?
Oh, yes, you may begin.
Okay. Thank you, Professor Jagtap. Hello everyone. Myself Urvashi Bothra, and today I am giving talk on correlation of nanomorphology with structural and spectroscopic studies in organic solar cells. The outline of my talk is introduction of organic photovoltaics, importance of morphology in organic photovoltaics, followed by experiments, results, and then conclusion. So organic solar cells are the devices which produces power when light is absorbed by the active material, which is actually formed by carbon-based materials. Recently, they have achieved efficiency of around 18%. They can be fabricated on flex substrates. They have high specific power because of their lightweight as well as transparent in nature. So these are their properties which keeps them apart from the conventional other solar cells. They are in the line of installation, and these are few of the examples of their installation as well as their use in space applications. And So the figure over here shows the energy diagram as well as the device architecture of a conventional organic solar cell. So when light is shown on the organic solar cell, it passes through the transparent conducting oxide through the whole transport layer, and then it is absorbed by either the donor or the accepted material. Due to the low dielectric constant of these materials, instead of forming the free charge carriers, they form excitons. Now, the excitons need some kind of driving force to be dissociated. Therefore, they diffuse to the interface. They basically diffuse and try to find an interface where they can be separated. The diffusion length of these excitons are around 10 to 15 nanometer. So, if they find an interface, then they form CT state, which is charge transfer complex. Otherwise, they can recombine either radiatively or non-radiatively and decay. So after the formation of CT state, the free charges are created, and then they are collected by the respective electrodes. So from there, we know that because of the limitation of the exciton diffusion length, we need a kind of morphology which has donor acceptor kind of systems within the exciton diffusion length. So basically, we can have a morphology which is the bulk heterojunction morphology, as can be seen in this figure, which has interpenetrating network of donor as well as acceptor material. It should have optimized interfacial area such that the CT states can be formed, as well as efficient exciton dissociation can take place. And at the same time, we want the material domains should be pure for the efficient charge separation to happen, and to basically stop the any kind of geminate recombination in them. So over here we can see that we need a combination of amorphous as well as crystalline phases in our bulk heterojunction morphology. So the amorphous phase can help for the charge generation to happen, and the crystalline phase will help in the charge transport to happen. And therefore we want the area to be somewhere in between, such that we can have both the properties. Now, in order to improve the morphology, there are various processes, because these materials are spin coated. The morphology can be modulated by solvent selection, thermal annealing, solvent annealing, and many other processes. Over here in my talk, I'll be talking about the solvent additive, and it was first used in 2008 by Lee et al. So here I show one example, basically two examples of how the diiodooctane, which is a solvent additive, is used to change the morphology of a donor acceptor system. So here the donor material is PCP-DTBT, which is a polymer, and the acceptor material is PCBM, which is a full ring. Now, the blends are formed by combining the donor as well as the acceptor material. So we can see that without addition of the DIO, which is a solvent additive which has high boiling point of 332 degrees centigrade and which selectively dissolves in PCBM, we can see that without it, we have a very intermixed and amorphous kind of morphology. However, on addition of this, we can see that there are aggregated domains for the donor as well as the acceptor material, which helps to improve the charge transport and thus the efficiency. If we look at another example, when we only change the polymer, so such that we change it from this to PTB7, due to the different chemical structure, the morphology without DIO has large aggregated domains of PCBM, and on addition of DIO, we can see that there is totally reversal of the morphology which we saw in the previous case. So we can see that the domains basically break down, and we can see a finer morphology. So therefore, the objective of this work is basically to correlate different bulk heterojunction morphology with device performances via doing the charge transfer as well as the charge transport studies. So in this slide, we can see the process of making the device, which shows all the processes and the device characterizations which are done, as well as the film characterizations which are done over here. So firstly, as mentioned in the objective, we need to basically fabricate the films with different morphology. So for this, we have taken the system PTB7 PCBM, and we have added different volume percent of DIO, the solvent additive, from 0%, 3%, and 20%. As can be seen in AFM, which is atomic force microscopy, we can see that the morphology is very much different in these three cases. In the first case, we have a roughness of around 5.8 nanometer due to the aggregated domains. On adding DIO of 3%, the roughness decreases due to the intermixed morphology, and on adding 20% of DIO, again the roughness increases to 15.3 nanometer. Looking at nanomorphology, again, we did TEM of for these three materials, and yeah, we got the similar results. However, for 20% DIO, if we look at the higher magnification images, apart from just the spatial variations which occur due to the roughness, we can see that there are few fine structures also present in these films. In order to understand and to quantify the domain size in all these three different nanomorphologies, RSOX, which is resonant soft X-ray scattering, was also performed with the help of Elliott-Gant, and we were able to quantify the domain size in all these three cases. So if we see for 0% DIO, the domain size is around 250 nanometer, which is quite high compared to our exciton diffusion lens. On adding 3% DIO, we have the domain size, which is around 40 nanometer, which is quite related to the optimum domain size required. And in the case of 20% DIU, we saw a hierarchical morphology, which is consisted of the spatial variation leading to 750 nanometer, and then there were fine structures of around 125 nanometer, and then there were very fine domains as well, which was around 40 nanometer. Thus, in order to see if these different morphologies actually has some impact on the devices, we have made the organic solar cells as well. So, comparing these three cases, we can see that on adding 3% of DIO, the efficiency changes from 2% to 7.7%. So, there was a drastic increase in the efficiency due to the increase in the GSC as well as the increase in the fill factor. However, on adding further amount of DIO, which is 20%, the efficiency decreased slightly due to the decrease in the JSC, and this can be seen from the external quantum efficiency as well. Now, we saw that the changes in morphology leads to changes in the device performance, but what are the factors which are actually affecting it? As we saw that charge transfer as well as the charge transport both plays a very important role. In order to see the effect of charge transfer, we have done the spectroscopic studies. So over here, the photoluminescence of the blends are done with different DIO concentrations. For 0% DIO, we can see that the photoluminescence is highest, and it resembles the photoluminescence of pure PCBM. So this is because we can see from the TEM images that the domain size is very high as compared to the exciton diffusion length, and thus the exciton form does not actually reach the donor acceptor interface, and it decays radiatively. On adding 3% DIO, we have a very fine morphology. That means more donor acceptor interfaces and PL quenching increases. On further adding the DIO, we can see that the photoluminescence from the PCBM, it basically decreases. This means that the mixed morphology is even finer over there, and the pure materials are and the pure domains of PCBM are less. However, at the same time, we can see that there's an increase in the relative photoluminescence from the PTB7 side in the case of 20% DIU, which is due to the aggregation of DIU, aggregation of PTB7. Now, in order to see the charge transport lengths and the effect of DIU and the scanning photocurrent microscopy. So this setup was made in our lab only, and so in this experiment we we shine a focus light on our device, and the device is on a scanning stage which can be moved in X or Y direction, and the current collected through it is collected by lock-in amplifier, which is now from this schematic we can see that when a light is shown at the active area of the device, then over here it can be collected by the ITO as well as the silver, that is both the electrodes. However, if we move out of the active area, then only one of the charge will be collected, that is electron is collected by ITO, but the whole has to travel laterally and then it will be collected by the silver. So this is this happens because of a phenomena of lateral photovoltaic effect, and we can see a scanning photocurrent profile like this. Now this is the reason when we are totally out of the active area device, and this can be fitted by a mono exponential decay, and thus we can find our whole transport as well as electron transport length. And the electron transport length increases on adding 3% of DIO, which is due to the breakdown of PCM domains, which helps in efficient charge transport. And on adding DIO from 3 to 20%, the whole transport length increases due to the polymer aggregation. Therefore, in conclusion, we have basically tailored the morphology of PTP7 PCPM blend by varying the DIO concentration, and we were able to actually reveal the morphology in all these three cases of 0%, 3%, and 20%. And then we were able to correlate the device performance by investigating the charge transfer as well as the charge transport properties. Thank you. If you have any questions, let me know.
Thank you, Uroshi. The presentation is open for discussion. Any questions? You can have some quick questions. Yes. Well, in your last slide, I have not followed one small thing, that when you go from 3 to 20% DIO,
yes.
Okay,
yes.
Your transport length hardly changes, right? 184, 181.
Yes, in the case of electrons.
Yes.
Yes. However, if we look at the whole transport length,
yes,
it changes.
That changes. I mean, how do you explain this?
Yeah, okay. So the effect of DIO, as I said, that it is a solvent additive which selectively dissolves in one of the material. So over here, the material is PCBM in which it dissolves. So from 0 to 3% on adding DIO, the PCBM domains basically breaks down, and that is why there is an increase in the transport length. When we go from 3% to 20%, because PTP7 does not dissolve in DIO very much, it actually forms aggregates, and the aggregation of the polymers helps in the transport length. So that is why there is increase in the whole transport length.
Okay. Thank you very much, Urvashi, for a very nice presentation. And that brings us to the end of this session. We had three very interesting talks, and although we overshot the time, it was worth it. Let me thank, on behalf of the physics department and the organizers of SYMPHY, thank all the speakers in this session, and over to Sanjay.
Thanks to Professor B. Jagatav, Session Chair, Photonics, and all the speakers of last session. So we are running late, so I will quickly hand over to the Professor Shubhobroto Dhar and Raghunath Chilakot. So now we have a poster session, part on. There is another part 2, that is parallel session. So that will be just after lunch. Time is 1:45 p.m. to 2:15. So 30 minutes for parallel session. So now we have a part on. So each will get 5 minutes. Sir, session chair will tell in details. Hand over.
Hello, I am Shubhobroto Dhar. So Raghu, you are here?
I am here, Shubhobroto.
Oh, okay. So,
hi, everyone.
Okay. I think we have to follow the same order, right? The order in which you have sent the posters, right, Sanjay?
Yes, sir. Yeah.
Okay. And everybody will get 5 minutes time.
Yes, right, sir. So actually, right. So actually, they are asking to share their slides. If they have good internet, let them to do that. So, and if have some issues, so you can quickly share. Okay.
Okay. So that sharing.
One question: should we have separate time for discussions after every presentation, or is it?
Yeah, 2 minutes. So you both can ask the question. It's kind of competition. So both can ask question, and for audience there is a parallel session, so they can move to parallel session after lunch. Open for 30 minutes each individual.
Okay. So this time only presentation, right?
Yes, right. So you both of you can ask on question. So that's also fine. Looks okay.
I see. So no audience question here, right?
No audience question. Yeah.
Okay. So Raghu, should we start?
Yeah, we can start. Yes. Do you have the list?
I have the list.
Okay.
So first talk will be, or first presentation will for 5 minutes by Arjun Unnikrishnan. So he is from IISC Tribandrum. Arjun, are you here?
Yeah, hi. Yeah. Can you hear me?
Yeah, yes.
Yeah.
Yes, Arjun. Yes.
So I'm sharing the screen. You are able to see the screen also, right?
Not yet.
It's coming.
Okay, just a minute.
Yes. Now we can.
You are seen, huh?
Yeah.
Okay.
Could you please increase the size a bit?
Yeah, just a minute.
So sorry for interruption. So please go to full screen and then scroll it down. Whoever is having portrait, and so that's landscape we recommended, but some people also have some portrait. Please do that, scroll down. So make it visible to audience, please. Okay.
Okay. So now it's full screen, right? You're able to see. Yeah. Okay. So I'm Arjun Unikrishnan. So the title of my talk is Simplest Ground State in Spin-half Alternating Chain Compound, Sodium Vanadium Arsenic Oxide. So this is a spin gap system with a singlet ground state. Actually, if two half spins are coupled together, it can effectively act as a spin 0 or spin 1 state. So if the spin 0 state is the singlet ground state and spin 1 state is the excited triple state. So such kind of systems will show a gap in the excitation spectra. So this AgVOSO4 is a well-known compound which shows a spin gap. And in this kind of systems, by applying field, we can realize Bose-Einstein condensation kind of phenomena. So it's a good tool to experimentally realize the phenomena like Bose-Einstein condensation. So the structure of this compound is alternating chains running into mutually perpendicular directions in AB plane. You can see these blue lines. So this is alternating in strength, and there is coupling in the third direction also, which is very weak. So this creates a frustrated loop in the system. So one is antiferromagnetic interaction, one is ferromagnetic interaction, and there is 3 antiferromagnetic interaction. So simultaneously, all the interactions cannot be satisfied by the system, which creates a frustration. And we went for magnetic susceptibility measurements to get a picture on the ground state of the system. So where we found that there is no long range ordering down to lowest temperature, but there is a at the low temperature region, there is a upturn which is coming because of the slight paramagnetic impurity present in the sample, which is not able to be detected by XRE. So we try to subtract this paramagnetic contribution, and after subtracting, you can see the green color. So this is the expected behavior for a spin gap system, where the magnetization should exponentially decay towards 0. So to get the value of spin gap, we went for we try to fit different fitting models on the magnetization data, and the gap is estimated to be nearly 20 Kelvin, and the critical field of gap closing is nearly 16 Tesla. So we confirmed that from the high field magnetization studies also, where we can see that the magnetization is 0 up to that gap closing, and after that it started increasing the magnetization value. We confirm this singlet ground state behavior. Here in the magnetization, the susceptibility data, we are getting a Curie impurity contribution. But to get a picture without having this impurity contribution, we went for the NMR studies. And the NMR data also we fitted using the low temperature region of the NMR data. We fitted using the 1D model and 3D model. And there we found that when we are accounting the 3D interaction, we are getting the reliable value of the spin gap. That says that in the low temperature region of this system, we cannot exclude the 3-dimensional interaction. It is there, it is not negligible. And this 3D, the presence or the action of the 3D interaction is confirmed from the spin lattice relaxation studies also. There also we estimated the spin gap and critical field of gap closing. All these measured values or the estimated values are consistent. And we made a comparison of this AgBOSO4 with the sodium vanadilyl arsenate with the AgBOSO4, which is a previously reported compound. And we found that this sodium analog compound is more close to 1D. That means the perpendicular interaction between the chains are less compared to silver analog. So that's why the sodium, the silver, it is stronger. That's why the silver, we are getting a small value of gap, and the gap is getting increased in the sodium analog because of this reduced value of the interchain interaction. So the conclusion is like this is an alternate chain compound, but the 3D interaction cannot be neglected. But it is more close to 1D compared to the previously reported AgBOSO4. And this, from the comparison of these compounds, we understood that the presence of 3D interaction reduces the spin gap considerably. And this kind of reduced value systems with reduced spin gap are potential because we can realize the field-induced effects like Bose-Einstein condensation, thermoanalytic liquid, magnetization plateau, different kind, like this kind of different phenomena. Thank you.
Thank you, Arjun. So I have one small question.
Yeah.
So you talked about this J parallel and J perpendicular interaction. You were saying that this particular material has it is 1D type spin chain.
Yeah.
So because J parallel is more than J perpendicular. At the same time, you're also talking about 3D interaction, right? Which is spin gap, right?
Yeah.
So what is this 3D interaction? What does it mean?
Yeah, actually in this, the structure of this compound, you can see the middle figure. There you can see that blue line is the alternating chains. Okay. So these alternating chains are coupled between to a different chain using another coupling. That is shown in the green color line. You can see the green color line. Huh?
Okay.
And there is another line also which is shown a dotted line, orange color of line. That is also another interaction. So there will be different interaction. The chains are also coupled.
Okay, so you are saying that interactions are there, but they are much.
But they are weak. They are weak actually.
Okay,
the strongest interaction is along the chain.
Those interactions are necessary in order to decrease the spin gap.
Spin
right?
gap, yeah. If it is a dimer, if it is a perfect dimer, the spin gap will be very high. It will be equivalent to, it will be equivalent to the exchange coupling itself. If there is inter-dimer interactions or interchain interaction, it can further reduce the spin gap.
So when and then you are talking about that at some critical magnetic field where a system goes to the triplet state. So
Yeah,
the
triplet state will split into 3 because of the Zeeman splitting, and the lowest triplet state will overlap with the ground state.
Okay.
So that is
I have
equivalent.
a question here. So if you are here, you are not considering the effect of magnetic field on the.
Yeah, because of the magnetic field only, this Zeeman splitting will happen in this triplet state, and it will overlap with the ground state. At a critical value of the field only, this will happen.
But the magnetic field is not affecting the spin gap.
Yeah, magnetic field will linearly reduce the spin gap. So at a particular value of the critical field only, gap is completely closed. Okay. So if we are getting 16 Tesla, the gap will be completely getting closed.
Okay. Thanks.
Thank you.
So I have a very general question. So can you briefly explain why this particular compound and why it is useful? Why you're choosing this particular compound and why it is useful for any sort of applications?
Yeah, actually, this Bose-Einstein condensation usually people realize using cold atomic gases, and controlling the number density, the boson density, it is a little tricky in that aspects. So here, actually, using the quantum magnets, you can easily realize the Bose-Einstein condensation. This a triplet state overlapping with the ground state is equivalent to Bose-Einstein condensation. So the behavior of the Bose-Einstein condensation, you can study using this type of quantum magnets. So the silver vanadium arsenic AgBO-ASO4 is previously reported to have this Bose-Einstein condensation. So we were trying to replace the silver ion with the sodium so that the lattice size will be reducing, so that the interaction may be stronger. So what will be happening with the gap, and what will be the interesting thing in the material that the actual plan is to get a phase diagram of this type of compound so that we can explore the Bose-Einstein condensation kind of behavior.
Okay, thank you.
Thank you.
Okay. So next presentation will be by Mrinmoy Roy. So he is our student.
Hello.
Okay.
Am I?
I'm Mrinmoy. Please.
Am I audible?
Yeah. Yeah. Sure.
Yeah. Okay. 1 minute, sir. Hello.
Yes.
My poster can be seen.
Yes.
Yes, we do. We do see your poster.
So, good afternoon. I am Mrinmoy, and today I will present my poster as titled as Photo-induced quasi 2D to 3D phase transformation of organic halide perovskite nanoplatelets. So first, let me introduce what I mean by quasi 2D or 3D perovskite 3D perovskite platelets. So if you see this structure, this blue one has two layered octahedra. So perovskite is a continuous pattern of octahedras, which is this green colored system. So when we reduce the thickness of the octahedra, it starts behaving differently. So what we study here, so as we reduce the thickness of the octahedra, so they show different type of optical property, and we found that as we reduce when we shine the light on this reduced octahedra, they try to move to the 3D side. That is that this thickness of the octahedra starts getting increased. So what we do, we try to synthesis this.
Mrinmoy, can you go to full screen mode?
Okay, sir. This is okay.
Oh, but then it is.
In the previous one was better.
Previous one was better.
I can zoom it. Or
yeah, that would be nice if you can zoom it. Yes, that's better.
Right now I can move it a little bit up and down.
Yeah, this is fine.
Okay. So if you see, this is two-layered thick octahedra system. This is
your voice, your volume has to be enhanced.
Hello.
Yeah. Now it's fine.
Yes.
Yes, please.
So this is two-layered thick octahedra system. This is not. This is a 5-layered thick octahedra system. If you increase the thickness of the octahedra to the infinitely, then it is known as the 3D perovskite. If you have a single layer of octahedra, that is known as the 2D perovskite. So we try to do is systematically reduce the thickness of the octahedra to reach this 2-layered thick octahedra, which known as the quasi 2D perovskite. It is not 2D, this is not 3D, this is quasi 2D perovskite. So what we do, so we synthesize these quasi 2D octahedra systems systematically, and we shine light upon them. So as we shine light upon them, we see the change in the FWHM of those nanoparticles. So as we shine light, they starts the FWHM of these nanoparticles getting decreased. So there is a change in the structure. So we in similar manner we study the optical properties. That is,
I'm sorry, I'm not an expert. So what is FWHM?
So full width half maxima of this.
Okay.
Of these X-ray peaks.
All right.
So as the size increases, this is inversely proportional to the size of the crystalline size of the nanoparticles. So as the crystalline size increases, this full width half maxima decreases. So this indicates that there is something change in the structure. So we study the similarly optical properties of these nanoparticles, and what we see. So first, this is with continuously shining light. So this is a 325 nanometer laser continuously shining on the samples. So which is a systematic change in the optical absorption data. So first it has a optic absorption around 440 nanometer, and it starts shifting towards 520 nanometer side. Similarly, in the emission spectra, there is a continuous change in the emission spectra. So at first this emission spectra was around similarly 440 nanometer, and it shifts to the with at 520 nanometer. This is the this is the color of the sample diluted in toluene. To to understand this, there is a change in the color. So it was a blue.
You have to be quick. You have to be quick. You have only 1 minute left.
Okay. So the thing is, if we deconvoluted this whole absorption or emission spectra, we've seen that there is a continuous change in the band gap as well as continuous change in the emission spectra. So we found that as we increase the shine the light, the thickness of the perovskites, that is this is n equal to, matlab thickness is 2, this is thickness is 3, this is thickness is 4, and this is thickness is 5, and each thickness corresponds to the different emission peak. So as we continuously shine light, this thickness is continuously getting increased, and this feature we can see in this deconvoluted emission spectra. So after 3 hours of continuous shining, the quasi 2D perovskite, that is 2-layered thick perovskite, converted into the 5-layered and higher thick perovskite nanoparticles. So to understand why this to understand this, we also systematically synthesize calculated the theoretical band gap of this different layer thick perovskite, which was done by Aftab sir and his student called name is Vikram. He done the calculation, and we match our experimental band gap value and theoretical band gap value, which are matches quite well. But there is a different if we plot this, compare this with the Brush equation, which talks about in terms of effective mass approximation, we found that for n equal octahedra number 2, it doesn't matches with the Brush equation. Rest of the matches well. The reason behind this two-layered octahedra has a strong binding energy. This binding energy reduces the reduces the actual band gap compared to the 3D structure, because 2D structure has a large binding energy comparing to the 3D structure. That's why this mismatch is happening. And the possible reason what we have understand, this is because of when we shine light, this ion migration take place from the octahedra. This ion migration when this small ions are methylammonium ions. This starts migrating from one side to another side. That leads to the and with the surface cappings are also moving. This both surface capping and ion migration leads to the formation of 3D perovskite. So the main thing,
I think we can conclude now. Okay, it's already.
So I'm concluding why we are looking this structure, because if we make this 2-layer thick perovskite, that is this blue perovskite, and we shine light upon it. In the evolution of time, this blue LED, this material is for purpose of the LED application. So this blue LED can be converted into the green LED, which is not desirable. So we need to think upon this type of do this type of applications with this kind of quasi 2D perovskite nanoparticles. Thank you.
Okay, thank you.
Thank you.
So just one quick question. So just to understand, meaning you use light to
excite.
That is one thing. You also, in order to prepare thinner perovskite layers,
Okay.
You use light, right? How it is done?
This is chemically by synthesizing different condition, applying different condition.
And these are all nanoparticles, right?
These are all nanoparticles.
What
yes,
is the lateral size of those nanoparticles that
So-
you have nowhere mentioned?
So the lateral thickness I try to measure by AFM, but I can tell you that thickness is around this if you see this thickness, this one octahedra is
No,
5.
that is fine. That is the thickness. I am talking about the lateral dimension. Laterally, how big these nanoparticles are?
This is around 40 to 50 nanometer.
50 nanometer.
Yes.
And this band gap formula, what you are using here,
Yes.
that is for, so what this is in the nanoparticle regime, right? This strong confinement regime, or
Yes.
equation number 1.
Yes, this is brass.
So that considers that your particle is a spherical particle, right?
So that's why it is not matching with our system.
So then it is completely wrong, right? This particular formula will not be used here.
No. This sir, can you repeat? So this band gap is calculated with the tau's value, and we cross check this band gap value with the brass equation. So we and found that our band gap value doesn't matches with the brass equation.
And that is obvious, right?
Yes. So this is a complete different system, like 3D confinement to 1D confinement. This confinement is vertical confinement. The lateral there is no lateral confinement.
Okay.
This is one-dimensional confinement.
Okay. Thank you. Raghu, if you want.
Okay, I have no questions. No, I'm fine.
Thank you, Mimra.
Thank you.
The next person is Vikas Chandrabas.
Yes, sir. Yes, I am here.
Please.
So let me share my screen. Is it visible?
Not
only
fully.
partly. Oh yeah, now
it is fine.
Okay. So hello everyone. So I am Vikas. So here we used a recently developed yet non-conventional technique, that is electrolytic gating, to modulate the charge carrier density of a metallic film. And we know that metal has a much more larger charge carrier density than any semiconductor. And this type of modulation is not possible by using any sort of conventional technique. So by using this electrolytic gating technique, we can actually play with the carrier density of a metallic system. So now the question is why this is not possible by using any conventional technique, and the answer will be because of its very lower capacitance value, and there will be a electric breakdown of the gate insulator. So to overcome that problems, we actually replace this gate insulator by using an ionic liquid as gate insulator. So in this type of structure, in this type of ideal capacitance, it has a very much larger capacitance. So why so? Let me talk about in detail. So this is a schematic behavior of our device, and this is original device. So this is channel, it could be a metal channel, and these are ionic liquid and gate. And this combination we know that behaves like a capacitor, having capacitance C equal to epsilon naught K by T, and capacitance is inversely proportional to thickness. So if we apply any gate voltage, then the ions present inside the ionic liquid, they self-organize to form a electric double layer. So you can see here there is a electric double layer, and here there is a electric double layer near the electrode and electrolyte interface. And this thickness is very much less, roughly of the order of 1 nanometer. Since T is of the 1 nanometer of order, it is very less value, so capacitance is very high value. Since capacitance has very high value, so with a small operational voltage or gate voltage, we can actually achieve a significant amount of charge carrier density in this type of system. Then we calculated, or people in literature, we can find that by using a solid state gate, we can actually achieve up to 10⁻13 centimeter square of carriers. Whereas this number can be extended if we are using any type of ionic liquid as gate insulator. And in other way, if we are dealing with 10⁻15 per centimeter square material, then 1000 volt is needed if you are using a solid state gate, if we want to achieve any, if we want to observe any changes. Whereas with 1 voltage, that is very less amount of voltage, we can actually see a significant observation changes in observation of this type of system. So Then in this type, if you are dealing with this type of system, there are a few things you need to take care of. First thing is this ionic liquid you are using are hygroscopic in nature. So if any small amount of water or moisture present over there, then it can rapidly decrease this chemical stability window of this ionic liquid. And this chemical stability window says how at maximum how much voltage we can apply to this system before there is a breakdown. So to remove that moisture and water, we made a vacuum annealer in our lab, and after put this is main device. So this is channel and gate, and after lithography and metallation is done, we put ionic liquid on the top of that, and then we baked it at 120 degrees centigrade for 48 hours at high vacuum to remove any sort of moisture present over there. And this process is very much crucial to deal with this type of measurement. Then we tried to see whether there is actually a capacitance is forming over there or not. Then we tried to measure the resistance response. We tried to measure the resistance response at positive and negative gate voltage, and we can clearly see.
Because could you please increase the size of your poster a bit, that area?
Yeah. Is it visible? Okay.
Yes, yes.
So here we can see there is a properly increasing and decaying capacitance behavior, like what capacitor behaves. So there is a capacitance is forming near the electrolyte and electrode interface. Fine. Then we measure the carrier density by Hall measurement with two device size concentration. So one is with gate to channel ratio 1:1, and with another this one with 10:1. Then we see that with 1:1 device there is a significant changes, but this was actually not reproducible, and hence this is not reliable. Then we tried with another Hall bar, that is 10:1 ratio gate to channel ratio area, and we see now there is a proper trend of modulation with positive gate voltage, and there is some sort of hysteresis. So with when we go from positive to negative gate voltage, the curve will decrease. So by using this technique, we generally we are dealing with the metallic system to see any changes. And then we try to probe different properties of the ionic liquid. So what exactly happening to the ionic liquid when we are going to the low temperature? Then we see that at nearly 180 degree Kelvin, so there is a sudden increase in resistance. And this increases resistance because of at very lower temperature, the ionic liquid get freezed and it is getting immobile. So there is a sudden increase in resistance. And this temperature is called glass transition temperature of the ionic liquid. And this increasing resistance can be understood also by a simpler model. As you can see, there is a source and drain. Here, this is the channel, and there is a parallel path of current which is forming through the ionic liquid. But when we are lowering the temperature 180 degree Kelvin, this path get cut off. So there is a sudden increasing resistance. And now whatever resistance we are getting, this is solely coming from the sample. Okay, so it works properly. Then we use this method with a zinc oxide Hall bar. Then also we are actually able to see a modulation of resistance, and also there is a changes in current with different gate voltage. So in conclusion, I would like to mention that it is essential to increase the carrier density to see various phenomena like gate-induced superconductivity, metal to insulator transition, and people actually achieved this gate superconductivity, gate-induced or metal to insulator transition by using this technique. Also, a few months back, first time in the history, people see a magnetic state from a completely diamagnetic substance. So it is a very potential technique to control the surface states of the system. And why we are using this, why we use metal film, and the idea is to, in upcoming days, we are going to use this in a degenerate semiconductor, and which a degenerate semiconductor is having the carrier density slightly less than metallic system, but of the order of metallic system. So it's a very potential technique to observe various condensed matter phenomena in upcoming days. Thank you.
Thank you, Bikash. So can I start with the this thing? So can you very briefly explain what is electrolytic gating and why it is interesting?
Okay, so first, why people have been using the solid state gate in let's say 10 years or 20 years before. But the problem with solid state gate is it has very low capacitance. So with that capacitance value, we cannot achieve much more larger carrier density than 10⁻13 order. we cannot go beyond maximum, we cannot go beyond of this value. But with electricity getting, we can actually go to this limit because it has a very high capacitance value. And so with a less voltage, we can achieve this order of changes. And order of changes is important to see phenomena like get induced superconductivity. Can we achieve with this? Yes, sir. So, so particularly, we can observe a changes in metallic system, which is not possible by using any solid gate.
Hi, Vikas. One question: when you go below the glass transition temperature, suddenly resistance increases. That is what you are showing. So that resistance is the resistance of what? Of the channel, right? Red color.
Yes, sir. Okay, so this is resistance of the channel. Yes, sir. Exactly.
The resistance of the channel. Now,
yes, sir.
The question is, so why it is increasing? Meaning, so your
sir, at when we are lowering the temperature, so the ions get freezed completely at 180 Kelvin. So whatever the ions are playing the role, so they are getting immobile in this point.
So then why the resistance is increasing?
Okay, sir. Okay, so this can be understood by, you can see this model, sir. This is source and the channel normally. So there is a shunt is forming through the ionic liquid. Means there is a conduction which is through the ionic liquid is there is a conduction. But at this temperature, this conduction get cut off, or this path get cut off. So whatever resistance then coming, it's only from the sample or from the channel.
Okay. So that's why it is increasing.
Yes, sir.
Okay. Thank you.
Thank
you. Okay. So next presentation is by Bhavna.
Yes, sir.
Bhavna is our student here.
Hello, sir.
Hello.
I'm sharing my screen.
Please.
My screen is seen?
Yes, please.
Okay. So hello everyone, I'm Bhavna, and in this poster we work towards a synthesis for an alternative of hybrid lead-based perovskites, and as we all know that hybrid lead-based perovskites have given promising results when it comes to photovoltaic devices, where the efficiency achieved by these perovskites has reached the value of approximately 25%. So basically, the motivation of this present work lies in the problem which researchers are facing with these perovskites. First one is the harmful lead content which is present in this perovskite, and second is the instability which is provided with this which is there, instability issues which is there in ambient conditions. Now, in order to address these problems, we replace lead with gold, and by spontaneous anion exchange reaction in CsAuCl4, we synthesized CS2Au2I6 via hydroiodic acid treatment. Now, if we see the color change, then the compound that is CsAuCl4, it is yellow in color, and when we treat the compound with HI, the color changes to black. Now, if we visualize the crystal structure of this compound, as shown here, we can see that there is a disproportionation in the valency of the gold. That is, there is a presence of Au+1 as well as Au+3 networks. Now, these two networks sit alternatively to give this compound a 3D structure. This kind of valency is also been verified using the XPS, that is X-ray photo emission spectroscopy, where Au4F spectra, it shows the contribution from 4F 7/2 as well as 4F 5/2, which splits in both of these contributions split into Au+1 as well as Au+3 components, hence giving the valency of Au to be +1 as well as +3. This kind of valency, this kind of disproportionation in the valency results to give this compound a 3-dimensional structure. Now, if we talk about the fundamental absorption properties, we did go for the optical properties, and we find out that the band gap changes from 2.36 electron volt to approximately 1.1 electron volt when CsAuCl4 is treated with HI. Now, if we see the spectra for CS2Au2I6, then we can say that in this compound, an interesting feature of band gap is there, which is the formation of an intermediate band between the valence band and the conduction band. This intermediate band is formed because of the anti-bonding hybridization of Au3 plus dx square minus y square and IP orbital. This kind of hybridization results in the reduced band gap, that is 1.1 electron volt. This band gap is very helpful if we talk about the use of this material in photovoltaic devices. Apart from this optical band gap, if the next major thing which we need to take care is the stability of these compounds. Now, the compound was kept in ambient conditions of Mumbai. As we all know that the temperature is very humid, and it can humidity can go up to 65%, and that humid conditions under those humid conditions, the compound was very stable, and we can find that there is no such appearance of any extra peaks even after 6 months. So we can say that the compound is highly stable. And if we talk about the heat endurance of this compound, then the compound was subjected to heat to temperature, and the temperature was varied from room temperature to 200 degrees Celsius, and we can see that the compound is stable up to 140 degrees Celsius, after which there are some additional peaks which are coming and can be corresponding to CSI. That is because at a temperature of 160 degrees Celsius and above, gold chloride or gold halide that was inside the structure starts to decompose and it evaporates. So we can say that the compound CS2Au2I6 is very much stable for more than 6 months and can endure heat up to 140 degrees Celsius. In conclusion, we can say that we have tackled the issue of toxicity from lead-based halide perovskite, and we know that the optical properties are very promising for this compound, that is CS2Au2I6, which gives a very ideal direct band gap of 1.1 electron volt and is ultra stable in the ambient conditions. These properties are very much useful when we talk about using this material in photovoltaic applications. Thank you.
Okay. So it's over?
Yes, sir.
Okay. Thank you so much finishing it on time. So can I ask one small question I have?
Yes, sir.
Regarding some clarification, like whatever you are talking about, so you have, it has to be justified by some theoretical calculation. Did you do that calculation? So that particular
theoretical calculations about the structure or
yes.
the yes, sir.
Structure
it is,
as well as the electronic properties.
Actually, sir,
and the band gap.
Yes, sir. There are literatures. Actually, there are no experimental proof right now, but theoretically, yes, there are some literatures which are available, which shows that the compound is formed. Actually, the compound is formed in around 1930s, but it was just for the John Taylor distortions or the superconductivity, but nobody has explored it for the optical for its optical properties, right? So the structure was there, but optical properties were first studied in 2018 by a group called by a person called
anyway, so that value is matching with your value?
Yes, sir. Yes, sir.
The band gap value?
Yes, sir. It was approximately 1.2 electron volt. Ours is coming to be 1.1 electron volt.
Okay, thank you.
Hi, Bhavana. One quick question. So, just to understand, so the new thing that you did here is that you did this halide treatment for this thing, right? Is that correct?
Yes, sir.
Yes, sir. Then everything else follows. Okay. Thank you. Yeah, that's all.
Thank you, sir.
Thank you. So next presentation is from Vinod Kumar from our department. Vinod, are you here? Vinod is okay. Bhavna, you have to unshare.
Yes, sir. Yes.
Yeah. Vinod Kumar is here. Okay. Then we'll go to the next one. Kuljit Kaur. Yes, please, Kuljit. So you have to unmute. You have to unmute. Yeah.
Hello.
Yes, please.
Am I audible, sir?
Yes.
Yes, please share your screen.
Screen is visible.
It's coming, I think. Yeah.
Okay. Is it visible, sir?
Yes, yes.
Yes, it
yes,
is visible.
please.
Okay. Yeah. So hello everybody, I'm Kuljit Kaur. So I am going to discuss about quantum phase transition with the realistic superconducting qubit, which is a dissipative system, and it shows the dissipative phase transition in a very strong dissipation limit. So here I am saying that the strong dissipation, so which is experimentally is not easy to achieve, and people are trying to get this limit with the various type of arrangement. And recently there is an experiment by Xavier et al. Where they achieved the ultra strong coupling limit by using superconducting qubit, which I am showing here the setup. So here they use a transmon qubit, which is shown in the red color, which is coupled to other qubits, other squid arrangements, which is shown in the blue, which is depicted as a bath. So, and here they achieve this ultra strong coupling limit, and we based on this experimental setup, we write the Hamiltonian by using the Lagrangian formulation, as I'm showing in equation 1. So the circuit has 2 degrees of freedom, charge and phase, and we can write the Lagrangian corresponding to phi and phi dot here. And by now performing by Legendre transformation and quantization of the operators phi, we can write the Hamiltonian as I'm showing in equation 2, which is my complete Hamiltonian that we studied. So the equation 2 has 3 parts. The first is the Hamiltonian is corresponding to the Josephson junction Hamiltonian, which is the superconducting qubit part. Here the EC is the energy corresponding to charging energy, and EJ is the Josephson energy term. The second is the bath term, which depicts the bath of N modes, K modes, and the third one is showing the interaction between the qubit and the bath. The coupling between the bath is given by the ohmic spectral density function alpha here, which is I'm showing in equation 3. So we solve this Hamiltonian using the variational method as well as NRG, which I am skipping here because of time constraint. I also want to introduce here the 2 limits of HJ, which is a superconducting qubit. So the superconducting qubit, the HJ has 2 limits on the basis of the strength of Josephson energy as well as coupling a charge energy term. So first one is the Cooper pair box region when EJ by EC is much less than 1. So in this limit, the system is behave as a effective 2-level system. And the other limit is when we have this reception energy, which is much greater than charging energy. So here the system is called a transmon Wijm, and it behaves as an N-level system. So we studied this system, and what we see that there is a phase transition, which I'm showing here, that in this system there is a phase transition from a delocalized phase to localized phase, which I'm showing with using the order parameter, which is n cap. So this n cap is a operator like a population inversion operator, which is 0 when the system is in delocalized phase and non-zero when the system goes to localized phase. So what we got is that when EJ by EC is is in a Cooper pair box region, there is a phase transition from NN0, which is showing here in a yellow, to a localized phase. However, in the other region, there is a no phase transition. Okay? So the system will remain in a localized phase within the stability limit. So this stability limit also it is also emerged from our Hamiltonian, which is we are plotting here in a second figure. This is because the relation between there is a dependence of EC on the value of alpha, which I am here showing that alpha has some upper bound by 2 EC by omega c. So for a particular value of EJ, if I am going to increase EC, so there is always a line where after that the system becomes unstable. Okay? And that instability line is showing in the phase diagram here. So what we got is that in a delocalized phase, the system when system remains in a stable region, then there is a no phase transition. The physics of these two different regions can be understood by calculating the 0-point fluctuations, which we do in a second figure here I'm showing. So the 0-point fluctuations are given by phi square, but since my Hamiltonian doesn't have phi square, is not defined here, so we calculate it by calculating the Josephson tunneling energy, which is cos phi average. So we calculated this cos phi for the two regions here. So in the first region, I'm showing the data with the transmon region. So when we are in a transmon region, then we see that cos phi is increasing with the dissipation strength, which shows that there is a suppression of phase fluctuation. However, in the other region, when we are in a Cooper pair box region, when we increase the dissipation, then there is a decrease in cos phi, which shows that the charge is now getting freezed here, or there is a suppression of charge fluctuation, and phase fluctuations are highest in this. So there is a crossover from the behavior of phase fluctuation from one region to the other region, which we showed here in the third figure, where we are plotting cos phi versus EJ by EC. So what we here see is that there is a crossover at a value of EJ by EC equal to 1, which is I'm showing here. EJ by EC equal to 1, which is a non-trivial, trivial to understand. So here with this, I want to conclude that the poster is that the superconducting qubit doesn't have a phase transition when it is in a Cooper pair box region, and there is a no phase transition when it is in a transmon region. And the physics is behind this is the localization, that in a one region is the phase localized region and the other region is the charge localized region. Thank you.
Okay, thank you.
Thank you.
Yeah, please.
Kuljit, you started saying that it's a dissipative system. So can you say what makes this a dissipative system? What is the origin of this dissipation?
So the dissipation is because I have a cube. So there you can think that it is a qubit, okay, which is a system, and now there is an involvement which is depicted with the harmonic oscillator, and there is an interaction which is I'm showing with the third term here.
So the interaction brings the dissipation.
Yes, the interaction being the yes, it's the dissipation.
Thank you. Yeah.
Hi. So what is the meaning of this delocalized and localized states? So what phase, right? You talked about delocalized. What is getting delocalized here?
Yeah, so by delocalized phase here, I'm meaning that charge is getting delocalized. Okay, so there is always the states where there is a superposition of charge. So I get as an average, I'm saying 0. And when I'm saying that localized phase, the system is locked to one charge state, and
charge state. Charge
yes,
state.
yes,
You are saying.
and it's 0. Yes, yes.
So that means something is moving from one qubit to another, right? What is moving from one to another, which is getting delocalized or localized?
Yeah, that is, I'm saying the charge here, which is in a superconducting qubit Cooper pairs. We can think. Yeah.
Okay, so you are saying the Cooper pair will be localized?
Yes.
Okay. So that depends upon the interaction between the qubits, right?
Yes, yes.
And you are
Yeah,
also
qubit
talking
and the
about
bath. Yeah.
some boson bath, right?
Yes, there is a boson in bath.
What boson you are talking about there? What sort of bosons there?
So boson
Boson.
something. Yes, sir.
Yes, please. So you have Cooper pairs. They are also bosons,
Yes.
right?
Yes, yes.
And then another bath you are talking about. Superconducting qubit coupled with bath of boson. So is it some photons are also coming in the picture or what? Bosons are here what?
So that superconducting qubit I'm treating as it as a qubit, which is as a system, and that all the environment is depicted as a bath. So there is always like interaction between both type of charges, between the qubit charges as well as in the bath.
Okay.
Boson.
So, okay.
Yeah.
Thank you.
Thank you. I think Vinod Kumar is here.
Yes, please. Yeah. Vinod Kumar, could you please start your presentation and
Yes, sir, I'm here.
yeah, please.
So should I share my screen?
Yes,
please. Hi, Vinod. We cannot.
Yes, I'm sharing.
Yeah, please. Please stick to your 5 minutes time limit. Huh?
Okay, sir.
5 minutes thing, in 3 minutes you try to finish it. 3 to 4 minutes.
is there any problem from your side, or is it a network problem? Vinod, you're there?
Yes, sir, I'm sharing screen.
Any issues, please switch to take backup.
No, it's okay.
Yeah, please start. Increase the size a bit more so that we can see it.
Is it okay?
Yeah. Even more. Yeah.
Is it okay?
Yes, please.
Yeah, so myself Vinod Kumar. I'm from Quantum Magnetic Lab from Physics Department, IIT Bombay, under Professors A.V. Mahajan. So I'm presenting here the structure and magnetic properties of copper-based compound Ba2CO2 T2P2O13, which is a spin half coupled spin chain compound. So the specialty about this compound is that initially in the recent paper, it is claimed that it is a 1D system. So, but our findings show that it's not a 1D system, but it is a coupled chain system, and which shows ordering, and the ordering depends on field dependent. So, I'm audible, sir?
You are audible, but sometimes some screen, something is coming up on your screen. I think you are clicking some icons inside.
Okay.
So, okay, yeah, please.
So the introduction of this compound, it's as it is claimed as a 1D system, but we found that it is a coupled chain system and it has a field dependent ordering. So this is the specialty about this, which is not reported earlier. So here we have done the structural analysis. For that we have done the XRD measurement, and after that we have drawn the its crystal structure, which is earlier reported also, like in this image. Yeah, like in this image. So here Cu4 copper plaquettes are forming, and like this is in one direction, there is interaction among coppers, and there is also in the second direction. And if I rotate this in the third direction also, the coppers are forming chain. So if I come here, so I did the magnetization measurement. This one, the blue circles are the experimental data, and we tried to fit it with a 1D chain system with the method of Johnston method. So from here it show here a broad maximum. This is due to some short range ordering, and then there is some upturn here. This is due to some Curie wise. This is some Curie wise behavior, which is due to some uh, impurity in the sense paramagnetic impurities are here. So when we did the 1D fitting with the Johnston method, this red line, it shows the exchange interaction is around 90 Kelvin. So which is matching with the previous data. So in the previous data, they have shown it as a 1D chain system, and for there they have done the measurement up to magnetic field only 1 Tesla or 10 kilo-Oersted. So we performed heat capacity also, which is here reported here. So here in the low temperature region, we have shown the data. So like here, as one can see, so around 4 Kelvin. So this is the peak which we are seeing here, which is field dependent. Like one can see at 0 Oersted, there is no field. Then 10 kilo Oersted, that is 1 Tesla, there is also no peak is seen. But as we increases the field, so this peak position appears and it gets sharpened. And here below this ordering temperature, we try to fit it with the power law behavior, which show the ground state is a gapless. So to confirm all this, like in magnetization, whatever the magnetic properties are shown could be governed by or could be influenced by the like paramagnetic impurities. So we have a local probe technique called NMR, nuclear magnetic resonance. So we perform measure the nuclear magnetic resonance of phosphorus, which has a nuclear spin value I equals to half, and it is hyperfine coupled with our magnetic. Like here one can see, like here this is a phosphorus, the orange one is phosphorus, and it is hyperfine coupled with 3 copper ions. Like here one can see. Then so when we prove this nucleus phosphorus,
you have to be quick, right? You
yeah,
don't have much time left, maybe 1 minute.
Okay, so when we probe this phosphorus, then we can see the arrangement of this magnetic ion copper around it. So for that we have done the spectra measurement and spin lattice relaxation time measurement. So from here one can see, so the blue solid balls are the NMR spectra measurement, and the sky is the magnetic susceptibility measurement. As one can see, it is following the NMR data, the magnetic susceptibility following the NMR data, and by taking temperature as an implicit parameter, we plotted this isotropic NMR shift line as a function of chi, and by doing a linear fit, we can calculate what is the value of hyperfine coupling constant for isotropic part and for axial part. So the axial part and isotropic part are coming because of the asymmetric nature of the spectral lines. And here from
okay,
T1
fine.
measurement,
You go to the conclusion, Vinod.
Yeah.
Go to the conclusion and tell us what is.
Yeah, so from 1 by T1 measurement, we can see that there is a P position. So the conclusion, it's not a 1D system. And it has a broad maximum at around 53 Kelvin, which shows some short range ordering.
Okay.
And then heat capacity shows some long range ordering around 4 Kelvin. And then isotropic NMR sheet from this method is around 3539 orsted per μV. And axial NMR coupling constant is 479 orsted per μV. So, and it has a ordering at around 4K, which is shown by spin lattice relaxation time 1 by T1 measurement also. So this is the whole conclusion.
Okay. So this is not a 1D chain. That is what you have found out. And you are the first group to find it out, or people have already done it?
We are the first one, and this is recently last month it is published in PR.
So Vinod, what is so special about being a 1D system or not being a 1D system? Why is it?
So 1D system is special because it shows some very basic physics phenomena that the system get not ordered down to the lowest temperature. It does not show any ordering.
System does not order at lowest temperature.
Yes. So that's why this 1D system is important as a with respect to the experimental viewpoint and also the theoretical viewpoint. And the important thing is this 1D system is totally explained by theoretically. Yeah.
Okay.
Thank you, Vinod.
Thank you.
Okay, thank you.
Thank you very much, sir.
So next presentation is by Ruchira Bhatt.
Hi, sir.
Hi.
Vinod, you need to unshare.
Okay, sir.
No. So on top you can find
new share?
Unshare. Go to view option.
It's new share, but it's not showing.
No, not here, not on in this. This is your.
Usually next to the camera, you'll have a button like the green button, right, for sharing. You have to press that.
So it's a new share.
Sure. The green color.
Yeah, it's showing. It's showing new share.
Can I do the unsharing?
Yes, sir.
Thank you. It's done. So now the next one is Ruchira. Ruchira, please.
Sir, is the screen visible?
Yes.
Yes.
So hi everyone. I'm Ruchira. Today I would like to discuss briefly about our work on flow-K higher order topological insulators. So recently, it has been found that by periodically driving a trivial band insulator, we can access different topological phases of matter as well. So for instance, from a 2D system, and by periodically driving a 2D system, we can access a first order topological phase where we have conducting states localized at the edges with an insulating bulk, and as well as we can also get a second order topological phase which belongs to the category of higher order topological insulators, where the conducting modes are localized at the corners instead of the edges of a 2D system. And generally, the first order topological insulators are classified based on non-spatial symmetries, while higher order topological phases are characterized by or they are protected by spatial or crystalline symmetries. So in this work, we would like to focus on a chiral symmetry or sublattice symmetry protected higher order topological phase, which is obtained by flow-K driving or periodic driving of a trivial band insulator. So coming to our model, so our lattice model is shown in the right hand side, and the blue arrows, it represents the allowed range of hopping. Actually long range hoppings are allowed, and the dotted line indicates that there is a pi flux threading through each square plaque, and the on-site potential values are represented in this red letters, and they are chosen in a special way so that a dimer-like pattern appears in our square lattice. And equation 1 gives the time-dependent Hamiltonian, where we are modulating the on-site potential values by means of a square wave drive. So to understand the physics better, we do a high frequency approximation using Brillouin-Wigner perturbation theory. Also, we choose the on-site potential values, the alphas and betas, in such a way so that the sublattice symmetry gets restored in the system. So after doing both of this, we end up in equation 2, where there is no time dependent term and there is no on-site term also. So it's just a hopping model with renormalized hopping amplitudes, and the effective lattice is shown in the right hand side, and it have 4 different sublattices represented by A, B, C, and D, and 2 different types of hoppings, VR and WR, as shown in equation 3. And since this hoppings appears to be complex in nature, it breaks both time reversal as well as particle hole symmetry. And the factor that mainly controls these hopping amplitudes are this alpha over omega, which represents the strength of drive as well as the on-site potential values. Under periodic boundary condition, we can do a Fourier transformation for equation 2, and we can write it in terms of a 4x4 Hamiltonian as shown in equation 4. And if I look into the effective square lattice, we can see that along all the edges of the square lattice, we have again a dimer chain with the hoppings VR and WR, and it is also sublattice symmetric since hoppings within the same sublattices are not allowed. We tune the on-site values in such a way, and this resultant 1D edges can also be written in form of a d dot sigma form as shown in equation 5, and they are characterized by the winding number. Their topological phase is characterized by a winding number. So to understand the bulk topology, we first look into the topology of this edge Hamiltonian, and then only, so to understand the topology of this edge Hamiltonian, we fix our parameter alpha over omega at 3 different values such that we observe a phase transition for the edge Hamiltonian. And in order to see that, we look for the winding of the D vector as K is varied across the first Brillouin zone. So as we can see, when we move from figure A to C, there is a phase transition for the edge Hamiltonian where the winding number varies from 0 to 1 through the transition point. And for the same set of parameters, alpha over omega, we also diagonalize the bulk Hamiltonian in the K space for 2D lattice, as well as the real space Hamiltonian, effective real space time independent Hamiltonian. So what we see is that if I look into the parameter that corresponds to non-trivial phase for the edge Hamiltonian, we can see fourfold degenerate zero energy states. And if I look into the distribution of these fourfold degenerate zero energy states, they are localized at the corners of our square lattice, while the edge states, they are gapped out from the they are gapped out in the bulk. So since we are getting corner localized states, it's an indication of second order topology. And we also find that these states are protected by chiral symmetry preserving perturbations, and they are defined by the topological invariant, which is given in this blue box, where nu x and nu y represents the winding numbers of edge Hamiltonian along x and y direction. Now, if we look into the transition point, we can see that at the transition point, both the bulk as well as the edge gap is closing, and hence we say that our second order topological phase belongs to an extrinsic classification of higher order topological phases. And by increasing the range of hopping, so here we have considered only the nearest neighbor hopping, but our model is essentially a long range hopping model. So by increasing the range of hopping, we can also control the number of corner states. And our topological invariant is essentially related to the topological invariant of our corresponding lower dimensional model. So unlike the other works where usually a spatial or crystalline symmetry protects the higher order topological phase, here in this work we show that an emerging chiral symmetry alone can also protect our higher order topological phase. Thank you.
Thank you. Are you done, Pujita?
Yes, sir.
Okay. I have just one quick question. So in the model, the lattice model, you said you have long range hopping, right?
Yes.
And that figure indicates it's limited up to 3 neighbors, right? Is it true or is it?
No, sir. Sorry, sir. I forgot to add the others. Here, what I just wanted to convey is that hopping is allowed to all the lattice sites. But in the second figure, the second nearest neighbor hopping is not allowed because of the sublattice symmetry.
Only the nearest neighbor. Okay, so only second is not allowed.
Second is not allowed, like orange to orange is not allowed, green to green is not allowed, but orange to green is allowed for all cases.
So you have an extra constraint in that case. Okay.
Yes, sublattice symmetry is this.
All right. Thank you.
Hi, Ruchira. I have one question, clarification. So you are talking about a system where potential is changing locally, right? Every site potential is changing as a function of time, right?
Yes.
Okay. And is it changing randomly or in a periodic manner?
In a periodic manner.
Okay. Now, so two sites, the potential is changing at the same sort of phase, or there is a phase lag?
So
if you take two sites, side by side or adjacent sites, so how their potential variation will be related?
Sir, I think there is a negative sign difference, but with respect
Meaning there is a
to
phase lag, right?
Yes.
Okay. So because you know the phonons, so phonons are essentially the lattice vibration, right? Their atoms are also oscillating at a particular frequency. Okay. So how different will it be in this case from situation of a phonon? So, and what kind of potential oscillation here? Meaning just your potential magnitude is changing or its shape is changing? What is happening here?
Sir,
you are considering, I believe, these are square potential, well, no?
Yes, sir, its magnitude is changing.
Depth is only changing as a function of.
Yes.
Okay, thank you.
Okay, thanks.
Thank you. So next presentation will be by Sanjay Khawas. So he is our student. Yes, please, Sanjay, please share.
Share.
Can you hear me? Actually, Sanjay was taking too much time. Can you that compact file share quickly for last 4? Just share quickly that 4 one by one. Yeah. Sanjay, you just wait. We are sharing. It's taking too much time for sharing things. Yeah, go to Sanjay.
Can you see it?
Yes, please.
Yes, we do. Yeah.
Hello, sir. Hello.
Yes, Sanjay, please start.
Yes.
So you have only 3-4 minutes time to finish.
In this work, we have studied the self-assembly of gold nanorods, where we used evaporative self-assembly method. Self-assembly basically a technique in which the particles arrange themselves into a long-range order structure without any external agents. So the main thing is about the interesting thing about this is that this process is very involve easy steps and also achievable compared to our conventional lithographic process, which involve more complexity and much more costly for the pattern designing. On the other hand, the gold nanorods, which has gained a much more interest among the researcher due to its tunable surface plasmon resonance, biocompatibility, and also easily modifiable surface chemistry, have application in the field of basically in the medical field, like in the drug delivery, then bioimaging, then also in the display technologies. Here we use the well-known phenomena called the coffee ring effect phenomena to assemble the gold nanorods into a long-range order structure. So what we did here, basically, at first we synthesized the gold nanorods by using a seed-mediated growth process. Then we made 3 different samples of different concentration. Then we took 3 microliter of dispersion and cast it on a 300 kilon silicon substrate and allow it to dry in the room temperature and humidity. So after complete evaporation, we found that it formed a coffee-like deposition pattern. So this is our experimental lab setup where we put the drop on the silicon with the silicon substrate on a contact angle meter. So during evaporation, we found 3 different mode of evaporation. The first thing is advancing mode, then constant contact angle mode or CCA mode, and the last was the constant contact radius mode. The last one is very important because during this evaporation mode, the particles, the 3-phase contact line of the drop get pinned to the silicon substrate, and due to the enhanced evaporation rate at the droplet edge, the outward flow will be created. Now this outward flow drag those particles or nanorods from the bulk of the drop towards the edge of the drop, and that's why after complete evaporation we found a ring-like structure. To get the information about the microstructure of the ring, we carried out same characterization where we found 4 distinct regions. One is outer region, then thicker ring region, then depression region at the vicinity of the ring, and the central region. Now, what we found that in the thicker ring region, the particles are arranged in a symmetric manner. This is because due to the competition between the repulsive electrostatic interaction and attractive van der Waals interaction. So they arrange between these 2 different forces. Ultimately, they arrange in a symmetric manner. So we also found that if we vary the concentration, that is, if we increase the concentration, the particles are getting more ordered and less defective. So this is because with the increase of the particle concentration, the flow will become more viscous, and there will be less possibility for the structure to be disturbed by the fluid dynamics. So in conclusion, we can say that we were able to achieve the a well-ordered structure by utilizing the coffee ring effect phenomena, and which can be tunable with the particle concentration. So our future goal is to fitting our experimental observations into a theoretical model, and also modification of the fluid dynamics by introducing different surfactant molecules like STETEP, and then to see the effect on the final deposited pattern.
Thank you, Sanjay. So are you done?
Yes, sir.
Okay. So I have a question. So when you form the ring, right? You say that inside the ring you have a depleted region.
Yes, sir.
but you can still have a finite concentration of this particle inside the ring also, right?
Yes, sir.
You do, or how do we control it?
There is a inside the ring, right?
Yeah, so I understand on the ring there will be a higher concentration.
Yes, yes.
But do you have a concentration of nanoparticles?
No, at the depletion region, this region is actually depleted of particle. This region is actually contain the CTEV only, residual CTEV. This is happened due to the depletion interactions among the particles. So depletion region is actually depleted of particles and contain only the residual CTEV. That's why it is called depletion region.
So you're saying that inside there is no gold particles, no nanoparticles.
At the vicinity of there is 4 region actually. The depletion region actually depleted of particle, and at the inner region there will be less number of particles or negligible number of particles.
Okay. And the diameter of the ring is fixed by your initial arrangement, or is it controlled by other factors?
It is actually automatically. So we actually took the 3 microliter volume of the droplet and we cast it on the drop, and it automatically and it's automatic process.
Yeah, that means it's fixed by your initial arrangement. That's what you're saying.
Yes, sir. The actual volume is at control level.
Okay, thank you.
So I have a question. So I see one picture here that weight structure, and then on top of that, it looks like that you are using the gravity effect here in order to control the ring size or something.
This one, sir.
Yeah. So that experimental scheme section, I can see one wedge, and there I see the ring formation on top of that.
This is a substrate actually.
So why you have drawn a wedge-like structure? Is it important to have a wedge structure in order to
just
get
to not in a wedge-like means it's just as
just like that.
substrate.
Okay, it's just like that. Okay. Yes. You are talking about the ordered arrangement of the particles, right?
Yes, sir.
But how do you know that they are ordered? Meaning, I cannot get much meaning out of it. Like the picture what you are showing in the result section. Okay. So only just looking at the picture, you are saying that they are ordered, or you did some other measurements?
No, sir. We take actually images at different portion actually. If we zoom in this picture, let me. So if you see here in this case, there is no arrangement in the particles. There is much more defect. It is contain much more defects. And the next image, the particles are arranged in a symmetric manner, but this contain also some kind of defect. Okay. If we see here, the particles are arranged or interact side by side and also stacked layer by layer. So they form a like order structure, well order structure.
Okay. Thank you. Thank you. Okay. So yeah, you are done. Yeah.
Thank you.
Thanks.
Thank you. So next one, next presentation will be by Richa Fogat.
Hello, sir. Could I maybe share my own screen? That way it would be easier for me to zoom in and zoom out.
Okay.
Thank you. Right. Can you see my screen now?
Yes. Not yet. Okay. Not yet. Yes. Something is coming.
I think now it's visible.
White screen now. Still white.
Oh, it's well.
Now it is black.
It shows sharing from my end. I don't know why it's not updating over there.
Now it is.
Okay. Okay. All right. So is it visible to everyone now?
Yes, please continue.
Okay, I'll start. Yeah. So hello everyone, I'm Richa and I'm a graduate student working with Professor Puneet Parmananda, and today I'll talk about echo in small world networks. So first I would like to thank the organizers for giving me this opportunity to present my work here. This work was done in collaboration with Professor Sudeshna Sinha from IISc Mohali. So first, I would talk about echo. So echo is this system behavior in which two provoked increments in the order parameter are followed by an unprovoked increment. So when I say system, I mean phase oscillators. So you can imagine phase oscillators as particles moving on a circle with their individual frequency omega I. These particles are connected to each other through a sinusoidal coupling, my bad. And the average number of connections formed by each oscillator is the degree of the network. So I have said provoked increments.
Richa, your volume is very low. So could you please somehow...
Yeah, is it better now?
Better, but we need a little
I
more.
will speak a little louder, yeah.
Yes, that would be nice.
Yeah. So also I said that the first and the second perturbations are provoked increments. So when I say provoked increments, I mean that a pulse perturbation was given at these two times to reset the responsive oscillators. So when I say responsive oscillators, what I mean is that every oscillator whose phase is above 0.8 pi is responsive. And when we give this pulse perturbation, every responsive oscillator is reset to 0. That would, in a way, lead to a gathering of phases and hence an increment in the order parameter. Now, similarly, at the time of second perturbation, we see this similar gathering of phases and hence an increment in the order parameter. But at the time of echo, we see this unprovoked spontaneous gathering of black and green oscillators, and that leads to an increment which we call echo. Now, we use a quantity called zeta to, in a way, separate order parameter at the time of echo from the background fluctuations in the order parameter. There is a line at zeta equals to 1 in all the subsequent figures, and everything above zeta 1 will classify as echo, and everything below zeta equals to 1 would not be echo. Now, increasing coupling in networks also leads to a deterioration of this echo behavior. So we sort of take a contrasting baselines by taking C0 equals 0.5, where low degree networks, they do not show echo, whereas high degree networks, they do show echo. We start from here and introduce randomness in our networks. So imagine a network in which every oscillator is only connected to their nearest neighbors. That would be a regular ring network with no randomness. But now if we break some of the connections and randomly connect them somewhere else, then we have introduced randomness in our network. More connections we break, more randomness we introduce. And beta is this quantity which quantifies randomness. So we take the above networks where lower degrees did not show echo, higher degrees did, and we increase randomness in our networks, and we see that echo re-emerges for these low degree networks. Now, this work was inspired by our inability to observe echo in human brain waves. And brain networks have been proposed to be this intermediate degree and intermediate randomness network. So here we see that for intermediate randomness, that is beta 0.3 and beta 0.7, the intermediate degree networks, they do not show echo. So we sort of explain that observation. Now moving on, we introduce time varying connections in our network. So this dynamical rewiring completely destroys echo in low degree networks, as we can see over here, as well as in this figure. So to conclude, we segregated our networks based on whether they do or do not show echo. And earlier this year, we were able to publish this work in Physical Review. And I'm open for questions now.
So Richa, your network is completely, the connectivity is totally topological, or do you have a spatial information there?
The spatial information we have tried to encode using the omega formula over here. So frequency in a way is index dependent, but I must insist that this would exist even without, so echo behavior you would see even without the spatial information, and also our results will persist even without spatial information.
But you do have spatial information, that's what you're saying.
In this work we do, yes, but we verified without spatial. information also. But yeah, in this, to answer your question briefly, yes, in this work, we have spatial information in terms of frequency of the oscillators.
Right. Okay.
So, Richard, what is, I mean, can you give us some sort of physical picture why this echo is taking place?
Right. There is a very beautiful mathematics going on behind as to why echo happens. I'll try to briefly sort of cover this. So we have this network of phase oscillators, and there is a particular frequency structure. The information between the information of the time between first perturbation and second perturbation is in a way gets encoded in this frequency structure. And that is why, so you must notice that you see echo tau time after the second perturbation, where tau is the time between first perturbation and the second perturbation. So you can mathematically show by making groups here. Let's say we divide these oscillators in two groups. One group which was reset by the first perturbation, one group which was not reset by the first perturbation. By the time you reach second perturbation, you have four groups: reset by both perturbations, not reset by either of the perturbation, and then there are two groups which are reset by either one of the perturbations. Now, if you calculate the frequency structure of these groups, you will have two groups which will lie in this particular frequency region when you calculate their positions tau time after the second perturbation. So in a way, the information of the time between two perturbations gets stored in the frequency structure of the network, which leads to a temporary gathering of oscillators at a time tau after the second perturbation, which gets observed in this macroscopic observable that we have, which we call order parameter.
I can see it this way from physics point of view. Let's say physical picture could be like this. Like you have some oscillators which are kind of connected. Now you are detuning because of some randomness in it. So that is naturally getting detuned, and suddenly you are putting some kind of perturbation which is pulling it back, meaning that detuning is also kind of getting suppressed. So in one direction it was happening, and then suddenly you are putting another one perturbation which is changing it to the opposite direction, which is giving rise to a echo, right, after some time.
Right. So you're right. In fact, detuning in a way would lead to a deterioration also of echo behavior. Like in this particular equation, if we increase C0, we are increasing the detuning between the networks. We are destroying their original frequency structure.
But something is happening in the opposite direction also because of your perturbation, right? That then only you can get a echo, right, after some time.
Right. Two perturbations are necessary to observe echo. You can't get it just with one perturbation. And initially, so let's consider a completely uncoupled network. In an completely uncoupled network as well, you will see this behavior. So we have initially these oscillators which are doing their own thing because they are in a way related to each other very much. And when we leave them to evolve on their own over time, they sort of go back to their original configuration. That's why we see that order parameter has again gone back to 0 after we leave the system on its own for a while. Then when we give the second perturbation, during second perturbation, this information of time between the two perturbations gets encoded. In fact, I have a very good video.
Anyway, so maybe we can discuss later on. Huh? So we have to.
Yeah, I mean, I would request you to please come to, because it will take some time to explain the groups and the math.
Okay. Thank you, Richard.
Thank you, Richard.
So the next presentation is by Akash.
Yes, sir. Can I share my screen?
Yeah, please.
Is it visible, sir?
Yes.
So good afternoon, everyone. My name is Akash, and I am explaining my work on biomembrane nanoparticle assembly at liquid-liquid interface. So in this work, I have made a 2D film at the interface of two different liquids, which are shown here. How can I? So, just a minute, sir. It is not getting zoomed.
It's visible to us.
No, I am zooming this figure.
You don't have to. Please.
Yeah, you can
Okay.
see this. You don't have to
Okay. So two different liquids here are chloroform and water. So I have kept chloroform in subphase and water in bulk phase, and positively charged lipid molecules, that is DMTAP. DMTAP is added in this chloroform, and gradually we have added water on the top of this chloroform. So after adding water, the lipid molecules get self-assembled at the interface. So here we have investigated the absorption dynamics of lipid molecules at different concentrations, and also I have investigated the effect of divalent cations, that is Mg2 plus, and investigated its effect on this 2D film. So in the absorption dynamics, what I have done is I have done all experiment at constant surface area. For that, I have taken one beaker, and there in the subphase, I have kept this chloroform, water in the bulk phase, and changed the concentration of DMTAP molecule, positively charged lipid molecules. And using the Wilmy plate at Langmuir-Blodgett technique, I have measured the surface pressure. What I have concluded from here is the concentration increases, you can see the surface pressure decreases. It means the absorption of molecules at the interface is favorable when we increase the concentration. Yes, after increasing concentration very high, it may get saturated, but till my experiment, on addition of this lipid molecules, we can see the absorption at interface increases. But the I am main concerned on this crossover phenomena, which we can see that firstly it is increasing. With increasing the concentration, then it goes on decreasing. So for my further investigation, I have used these two concentration points, that is 6.8 nanomolar of DMTAP and 25 nanomolar of DMTAP, to check it with different concentrations of salt. So the divalent salt is further categorized in two regions, that is low concentration regime and high concentration regime. In low concentration regime, I have used different concentration in nanomolar range, and in high concentration regime I have used in millimolar range. So in low concentration regime, what I have observed is there is not any effect on my film with this divalent cation. Yes, both are positively charged. My lipid is also positively charged, and this salt molecules Mg2 plus is also positively charged, but there is not any effect. Yes, there is some fluctuation in the curve for both 6.8 nanomolar and 25 nanomolar DMTAP. But this is because my film is on interface of liquid. This is dynamic, means continuously the molecules is going in subphase. Here it is going in subphase, coming again. This is active continuous.
Please go to your conclusion. What did you get?
From here, what I have got is, I have just done, these are my first set of experiment. In this, I have optimized some values, that is on increasing this concentration of lipid molecules, the absorption is increased. Another one is that addition of salt in low concentration regime does not affect my salt, but on addition of salt in high concentration regime to my film, it relaxes my film, means the film can be broken up. Another one is for structural analysis. What I have transferred the film on negatively charged silicon substrate, and what I have got here is the film is transferred, but it is reacting. This I got from I have compared with previous result, and these are reacting. So my next step is I will try to do another methods like making substrate hydrophobic and these things. And with this,
okay,
I will conclude my presentation.
thank you.
Thank you. So can I ask a question? So I think initially you are interested in this decrease and increase of this surface pressure, right? For this.
Yes, sir.
So if I understand, so is it, do you conclude that it is because of some structural change of the surface, this membrane? Is it the reason?
No.
Or okay.
There is no structural change. Means I have two immiscible liquids. So at the interface, energy is very high. So molecules will go at that interface to decrease the energy. That's why it is going. But if I'm adding so much of molecules, then it is also positively charged. There are different forces acting on it, like thermal force, like this, what we call electrostatic force. Another one is this van der Waals force. Different forces are acting on this one. So structure is not, it is forming a film. This is the thing. And I am just optimizing at what concentration I should work so that I will get a complete film without any defect.
Okay, thank you.
Thank you.
Thank you, sir. Thank you, sir.
So the last presentation will be by Jyoti, right? Jyoti Sharma, please.
Hello, sir.
Hi.
Hi,
Hello, sir. I will share my screen now.
Yes.
Okay. Is
Please
it
finish
visible
it
to all?
on time, right?
Yes, it is.
Yes. Okay. Is it visible to all?
Yes.
Yes, it is.
So I will be talking
Please
about.
Increase the size. Increase the size. Zoom it.
So I will be talking about the rotational synchronization of camphor ribbons. This work is experimental as well as simulations, and all the experiments are done in nonlinear dynamics lab group at IIT Bombay. So the camphor ribbons are self-propelled particles, and you can call them as active particles also. And in the yesterday, Professor Nitin Kumar talked very nicely about the active particles. So why we are interested in this study? We are trying to find out the nonlinear aspects of the collective dynamics of camphor ribbons here. And this kind of studies are very important from the experimental point of view, because these help us to understand the complex phenomena those happens in active biological systems. For example, flagella, cilia, bacteria, etc. So what we do in our lab is we prepare camphor particles, which are basically a strip, a rectangular sheet on which camphor is infused. When you put this ribbon on the surface of water, it instantaneously starts to rotate about the axis of the pivot. Why it does this motion is because of the surface tension gradient that is induced by camphor ribbon on the surface of water. Okay. So initially we did experiments with two ribbons. So the two ribbons will rotate in same direction or in opposite direction. This we call as co-rotating mode of synchronization, and this as counter-rotating mode of synchronization. So then we jump to multiple systems, which are 3, 4, and 5 systems placed in different geometries, basically the linear geometry and well as the closed geometry. All these figures which you can see, this schematic diagrams show all the available configurations in the experiments, and the number of configurations that we observe in the experiment is dependent upon the geometry of the system. Is it closed or is it open? And the number of the camphor ribbons. So in the closed geometry, some of the configurations are restricted because of the geometrical constraints. Okay. And these phase plots shows the phase synchronization of the ribbons. How do we plot this? We analyze numerically the ribbons. We do image analysis of the ribbons, and that's how we plotted this. And furthermore, we have seen in the experiments that in the case of a triangular geometry, the configuration where you have maximum number of negative bonds, that means the counter rotating bonds, is preferred over the configuration having all the positive bonds. which is clearly shown in this histogram. Okay. So now to understand why this is happening, we have simulated this system using repulsive Yukawa potential between 2 point particles. But in the interest of time, I would like to discuss the details of the simulation as well as experiments in the parallel session. So I would invite all of you to please attend that parallel session, and then now I will conclude my poster. So what we have observed is the rotational synchronization of the ribbons in different geometry. This synchronization is observed when the pivot to pivot distance between the ribbons is less than twice the length of the ribbon. And furthermore, we have seen that this simulation model was able to qualitatively explain all the experimental findings that we had. So thank you so much.
Thank you, Jyoti. Once you fix a geometry and you get this combination of either clockwise or counterclockwise, right? Configuration.
Yes.
So is it fixed in time? Does it change over time?
Yeah. So first, when we put the ribbons, of course, they are at a distance where they can physically touch each other. So they do some kind of transient dynamics, and after that, they settle into one of the configurations allowed by that geometry. So once they have settled down, they try to be in that configuration unless and until you externally perturb them. So in that sense, the configurations are stable in time.
Okay, thank you, Jyoti.
Okay, sir. Thank you.
So now thank you, thanks to all the poster presenter here, and thanks a lot for your nice presentations. We have also learned a lot of things. So over to Sanjay now. I think we are running late.
So thanks to session chair, Professor S. Dhar and Professor Raghunath. So we already announced in advance that we will have photo session. So click quickly on your video, and within that time, I just want to announce that our next session is at 2:30 instead of 2:15. And also I already requested all poster presenter to start their parallel session at scheduled time. Those who are late, they can take that another 15 minutes, mean they have to finish 2:30 p.m. 2:30 p.m. is next session. So Mr. Sangshaptabde,
yeah,
are you here? Monica Jawale. And one more person can take photo, whoever having some good internet. So Kuljit, can you take a screenshot?
I'm unable to switch to my start video. Please host.
Okay, let me check. Yeah, ask to start video. I did
Yeah.
that part.
Yeah, thank you.
So please come up quickly. So we will wait another 1 minute. Those who are coming, not coming, then take a screenshot. Yeah, Mr. Sangshaptab and Kuljit both take.
okay.
And once it's done, please tell me.
So ready? So I will take a screenshot.
Yeah, ready.
Okay, done.
Thank you.
Kuljit, you're done?
Yeah, it's not working for me. I don't know why. I'm trying.
Okay, so I got some sounds from Sangshaptab, so he clicked, so it's okay. Let's go ahead. Okay, so
Okay, thank you.
Website, there is a poster session part, parallel session. All links are there, Zoom links, so you can visit. I will also direct from here itself. So let me share the screen. So visible is Can you see the screen? Can anyone respond? I need to go.
We can see your
Yeah, we
screen.
can see this.
Yeah, thank you. So I need to go full screen mode. I have to go to. So this is the place where you can get the link. So this you can see that Arjun posters presentation. If you click that, you will go to that person room, and then following way, Minmoy and all 11. So in parallel, all 11 poster is happening. So please visit there and just again come back at 2:30 p.m. So next session will start at 2:30 p.m.
So Sanjay, can I just test my presentation?
Yeah, sure. Yeah. I'll come back. Just so this portion where I can tell I don't have to share from here always. So it's there to schedule. You need to go schedule and then go to day 2. So those who are here, just for their information. So then go to parallel session. Okay. And then if you click, so then you will get. So now I am stopping this and I want to do some trial with Professor Anil Kumar. I think he called me already. Yeah. Thank you, sir. Please share. It's enabled already. Please share. So actually, Professor Mahajan is already here. So I hand over to Professor Mahajan. Both can do that part. I am just leaving for some time. I will come back. Take forward. Please take forward.
Can you see my screen?
Yeah. Screen is good.
Screen?
Yeah. It's fine.
Yeah, then it is normal. Yeah.
Yeah.
Fine, great. So we are joining at this site only, right?
Yeah, I think so.
Fine. So then I will be mute and I'll switch off the video and then I'll wait until the call.
Sure. So same, I'll also come back in 10-15 minutes.
Okay, good. Yeah.
Okay, bye.
Have to unshare, stop share. Yeah.
Anil.
Yeah. Suresh.
Ready.
Just so how's things?
Fine, fine. So morning also you were there, right?
Yeah, I was there for quite some time. Yes.
Yeah, yeah,
Sometime I was there.
So how is the new life?
Oh, tough.
Yeah. Especially
Really?
initial days.
Yeah, especially because you have to learn a lot.
Yeah. And new rules also on spending this one, that one. So.
Pardon?
New rules on spending, all kinds of things.
Yeah. The only thing is that you need to understand everything. That's the whole issue.
Yeah.
Rules which are prevailing from 1950s until the latest amendments, you should know. That's the whole problem.
Yes. It's a new learning process.
Yes. Usually the band structure is intact, right? Once you establish it, remains there forever.
Yes.
So
Minor
that makes the
modification.
life of physicist easy.
Minor additional states here and there, that's all.
That's all. And silicon is not going to become, metallic
Whatever
in the future.
Sorry, what's the discussion?
Anil has a very big responsibility now, administrative responsibility.
What is it? Your dean or something?
Yeah,
He was already
Dean of Administration and Finance.
Arre baap. Yeah. Both very tough actually.
Yeah. Earlier he was academic, so he was on computer, I think.
I was a Dean of UG earlier, but still I have not left the Deanship of UG, which soon will happen, hopefully.
Oh, I see.
So how's things there?
It is going on, yeah.
Corona is under control?
Yeah, I think people started ignoring, at least that much. We will have something like 70 students soon. Close to 70, maybe in the next 2 months or so. PhD students.
Students are, okay. What percentage is there? You mean to say 70?
Yeah, our department will have something like 70 students by, I think December.
Only PhD? Only
PhD. Yeah. And some MTechs are called. Final year MTechs, actually, I think all final year MTechs are called, but I think they are not opting. The students are not opting, many of them.
That's true. Only students who only students who have experimental projects are opting to come back.
But here, even that we are not seeing many. I don't know about the engineering departments. So you are at home?
No, office.
Anil has some problem.
Am I audible?
Yeah.
Now it's
for me, yes.
You're at home or office?
At office.
Yeah.
Okay.
Since morning, my telephone is not working. It says no service, but WhatsApp will work.
Wow.
So in case in between, if you have to give me a call, then WhatsApp is the best. Or Suresh, I'll just leave my landline number. It's 2293.
Okay, let me know.
080.
Wait, I'll just know. What is the code? 080, yeah.
2293.
Yeah.
3586.
3586. 08022933586.
Yeah. or WhatsApp, in case if I get stuck in the video or anything.
Yeah, yeah.
Because I won't know that, whether I'm stuck or not.
Yeah, yeah, yes. But so far things have been very, without any problem.
No, it depends on my network also. Just now it got stuck a bit.
Yes, yes.
So yeah, Kolkata, there was a conference, and before my talk, everything was going fine. The moment I started, within about half a minute, it threw me out. Nothing I could do. So then I had to log in again. So it takes a couple of minutes before you again start off.
Yeah. Yeah, this nobody can predict.
Yeah. So I will also be muting and
Sure.
Yeah, afternoon, I think Sunday afternoon, the number is less.
Yeah.
And this is the last session, no?
Yeah. Okay, more or less, yes, yeah.
More. Although in a virtual session, it should not matter. In a physical session, everybody is in a hurry to now, get back to whatever airports and this and that.
But the virtual meetings have now, increased the load.
Yes.
For everything, there is a meeting now.
Yeah, now I started writing down. Otherwise, it was not needed.
Most of our meetings are in Teams.
We also.
Calendar, it get registered.
So here also, more or less, official thing is Teams, classes and all, mostly.
Yeah.
But people.
Senate takes this WebEx.
Yes. But once you start using the Zoom, somehow people like it.
Yeah, you get used to it. That's all.
Yeah.
Actually, WebEx is very similar.
Yeah, but I think certain features are not there.
Okay.
So Narayana told me that the Zoom, why it is not promoted. One of the reasons is that, of course, the security features are not very good, it seems.
Okay.
That's why we feel it very comfortable.
Yeah. I watched your convocation. Suresh, send me the link.
Okay.
Yes. So what about your convocation?
We don't have.
Oh, you don't have actually. Okay.
See, usually we never had convocation until 2015. There's no convocation. Once in 3 months, the degrees will be given to the students, because once in 3 months, students, after a council meeting, students are ready to receive degrees, because our majority is PhD students. Their graduation is, very staggered.
So for them, we have two convocations, one May and one in December.
Yeah.
February, yeah.
In that respect, we have, in principle 4 used to be. So whenever the degree is ready, they will come and collect.
So who gives it? Director?
It's not a formal function. The dean or somebody.
Yes,
it's not a. But nowadays, it is a formal function. It started in 2015, where we will have a guest, etc. But that just didn't happen this year.
Yeah, I hope next year things will be all right.
Hopefully, yeah. So the BTech admission started?
No, it is going on. Somebody told me yesterday that, see, now everything has to be uploaded. In the new IITs, it's okay because the number is small and also it is kind of staggered. But if, it was taking so much time to upload, it seems. One day they could upload only something like 60 people. I don't know. The people who are getting in Bombay and all will be finding it very difficult. Somebody told me that it has to be extended. Otherwise, there will be a lot of issue.
Right now, what is the deadline?
I think everything will get over by November 7th or so. We are starting on 16th as it stands.
November 16th.
Yeah, because most of our seats will be filled by third round.
Okay.
But I don't know, because yesterday, this is a very sad thing in the sense that it takes so much time to upload. And you have to upload so many things, and it seems people have to go to various places, medical certificate, this one, that one, bank, and all these things, and they have to upload. Because earlier it was physical, you can just give it.
Yeah.
But now collect and upload, I mean, it's terrible. And just 3 days for the first round, we'll have large number of students. So
okay.
So I did not see anything. Probably nothing has come to the newspaper. Maybe it will come today that they need more time or something, because this calendar is fixed.
Actually, a friend of mine whose daughter got a rank. So he was saying for payment, no? So it says, yeah, credit card, this, NEFT, all kinds of things. He says, but actually, finally, only each one was, I mean, all others were disabled. Then he managed to call this JOSA chairman. Somehow he could get the...
Yeah, only actually IITs are completely out of this.
Out. So then he told him, but nobody called me. He said, look, but I am facing this.
Yeah.
He said, okay, let me check. He said, first, yeah, you write to SBI or something. Then finally he was convinced that, okay, there's a problem. Then later he called back. He said, yeah, there was some mistake. So by evening, we'll enable all that. So
this is a usual problem. At CD, we have seen this. Even our own thing, the payment is always an issue. But this, unfortunately, the IITs have no control on JOSA.
Yeah, it's out of it.
Even just flashing a message saying that there is no branch change rule now, there is no change. So they refused. They told that we can send emails to all the people, but definitely we don't want to put anything there. But I know this, they have been very, I mean, completely, because they are more, I think they are detected by the NITs, probably.
Yeah.
The number is also more.
Suresh, can you hear me?
Yes.
Yes, still. Yeah.
Still. I'm just wondering whether my network is stable. Otherwise, I should move.
Maybe you can try the sharing, na? Just see.
He did already try.
I see.
Yeah, some 10 minutes back.
Okay.
Because in between for 10 seconds, I lost you. That's why I was wondering.
No, I think there is a small problem. Hey, Sanjay, we have enough time. Deepika is not there.
Oh, Deepika is not there?
No, she sent a mail.
Oh, okay.
I think Sanjay has seen it. She has some sudden emergency.
Oh boy. Oh, so as it is, there were Anil Kumar +3. So now it will be +2. Okay.
Right. I can see Dushyant is already here.
Hello,
Avinash, how are you?
Hello, Prof. Baskaran. Yeah, how are you?
I'm fine, great.
Yeah, you are muted right now.
Sorry. No, I said you have a beautiful background.
Yeah. It's not actual, unfortunately. I mean, I'm not sitting in there. I would like to, but I'm not.
Okay, bye.
So Professor Ghosh also will join for your talk at 4 o'clock.
Oh, thank you. Oh, yeah. I'm very happy.
So he has taken the registration and all this. So I will remind him. Yeah, he told me that.
Yeah, great. Thank you.
You are waiting for some more time, Sanjay.
Suresh, I think it's announced as 2:30 starting point.
2:30. Okay. Okay.
Yeah. He delayed it 50. I think the previous ones were maybe a bit delayed. So yeah,
because I left in between towards the end.
Yeah, I also didn't know. I happened to join early, and then I heard. And on the chat window somewhere it is there that it started 2:30.
Because this power panel work also I had to go in between.
Okay.
Hello, am I audible? Hello.
Yes.
So yeah, so our session chair and both speakers are here. So welcome back. Good afternoon to all. So I hand over the session to Professor Avinash Mahajan. Take it further.
Yes, good afternoon. It's a pleasure to welcome all back to this virtual conference, SYMPHY 2020. And this session will pertain to experimental aspects of condensed matter physics. Actually, condensed matter physics is a very vast area. Within that, experiment is also itself quite a vast area. So this will touch upon some small number of topics, obviously, because in a limited time that we have at our disposal, with limited number of speakers, it'll touch upon some small subset of experimental condensed matter physics. So we actually have one invited speaker and followed by 3 oral session speakers. So of which I understand one is unable to make it because of some other emergency. So it's going to be one invited speaker followed by 2 contributed talks. So as far as the timing is concerned, for the invited talk, it is 40 minutes of the presentation, followed by 5 minutes of possible 5 minutes of questions. And for the other contributed talks, it's going to be 12 minutes of oral presentation, followed by about 3 minutes of questions. So what I will do is, so for the first talk, for example, it seems there's a provision to annotate a slide when the speaker is presenting. So at 40 minutes, I'll try to flash a text saying that, okay, 5 minutes remaining or some such thing, with as less intrusion as possible. And then, sorry, at 35 minutes, and at 40 minutes, more or less, the speaker will end, and then 5 minutes for questions. Similarly, for the contributed oral presentations, it's going to be 10 minutes, after which I give a very gentle warning. Then the speaker has 2 minutes to wind up whatever he or she is saying, and then 3 minutes for questions. Okay, so the first speaker is Professor P.S. Anil Kumar from IISC Bangalore. Actually, Professor Anil Kumar is a very frequent visitor to our department here, physics department at IIT Bombay, in various capacities, and he has given many colloquia here, and I mean, I've heard most of them, and he's a very scintillating speaker and a very large body of work in the area of nano-related condensed matter, but also several other areas. So today he's going to talk about physics and technology with quantum materials. So I would request Professor Anil Kumar to give his talk. Thank you.
Thank you, Professor Mahajan. Thank you for the nice introduction. First of all, let me congratulate the students of the physics department of IIT Bombay for conducting this event. And I was supposed to be in the campus to give a lecture, and then due to this current pandemic, this is now an online version. And still I find that, it is as successful as it could be, even if it is on a virtual platform. So, and I thank Mr. Sanjay and other organizers for inviting me for this lecture. So today, since I know that the audience are very diverse, I'll be just, be at the basic level, but at the same time, I just wanted to convey the excitement in this area. And I just wanted to tell that, how exciting and, how tedious also in this kind of work is. So I'll just talk about the quantum materials, and I'll show you, it will be a purely an experimentalist view of this study. So I'll be showing you how devices are made and how measurements are made, how interpretations are drawn out of these things, etc. So this work is basically carried out by my former PhD student, Abhishek Banerjee. He is now with Professor Charlie Marcus in Copenhagen, working on quantum computation, experimental aspects. And Mr. Anantesh, he was a bachelor's master student, did project with me. He's now doing PhD at Purdue University. And Abhinav, again, is our undergraduate student, did master's and bachelor's project with me. Right now, he's continuing for PhD with me. And Dr. Ganeshan is my collaborator in the department. I also, in this particular work, in the work of topological insulators, which I started, 6 years back, I do collaborate with Professor Dillip Sen of Department of Physics of Department of Center for High Energy Physics at IISC, and Professor Biju Rajashekar from IOP Bhubaneswar, where we do collaborative work on angle dissolved photoemission spectroscopy. And as usual, these are the funding agencies that support our work. And I thank the support from all the funding agencies, and those who are interested in some of our work, you can follow these publications, which is there in the abstract, which I've given as well. So let me just start, since it's a topic which is maybe new to some of you and may not be. So the experts, please bear with me. So if you really look at the quantum materials, are materials that exhibit exotic electronic properties that is sometimes manifested due to reduced dimensionality, quantum confinement, etc. And if you really look at the Wikipedia definition, we just go to Wikipedia to understand a first glance information about many things. It says that it's a broad term in condensed matter physics to put under the same umbrella materials that present strong electronic correlations and or some type of electronic order, for example, superconducting, magnetic order, etc. So in that sense, many of us are working on quantum materials in this definition. But I will be concentrating on materials such as topological insulators. So today, though Professor Chandrabas gave a very nice lecture in the morning about topological insulators, I thought I'll just start with a little bit basics so that the students who are not familiar with the topological insulators should have some take-home message from here. So there are many materials like graphene topological insulators, wire semi-metal, spin liquid, etc. So these are being investigated by the condensed matter physics community for the past couple of decades, and these are expected to be the building blocks for future technological applications. So let me just start with a very, very basic introduction. We all know that if you consider an ordinary insulator, electrons fully occupy energy bands. The next available energy state is far away in energy, and this gap what renders diamond or silicon insulating, right? So we understand that part. Now, of late, in the last 1 or 2 decades, you see that there's a new term that is coming in, which is known as the topological insulators. Here, the energy gap between the occupied and the empty states is modified due to spin-orbit interaction. So what you see in the morning talk, Professor Chandrabas said that you have spin-orbit interaction that modifies the band structure, and since the spin-orbit interaction, it depends upon the spin-orbit interaction is high when the Z of the material is high. That means if you consider heavy materials, then you have spin-orbit interaction much more stronger, and this spin-orbit interaction is required for band inversion and other exotic properties. That's why the material which I am going to discuss today will always contain heavy elements like bismuth, antimony, tellurium, selenide, and those kind of elements. Now, what is this topological insulator? This is a new kind of a semiconductor that looks like an ordinary semiconductor in the bulk, and on the surface, it hosts protected metallic surface stage. So how will you visualize it? It's like this. So you have a material whose bulk is insulating or semiconducting with a fairly good band gap, and the surface is conducting. So the surface is acting as a metal. So many times an analogy is drawn. What is a topological insulator? You can think about that. You take a wooden block which is insulating and then cover with a copper foil which is conducting. So this is just an analogy. Please don't take it exactly like that, but it's an analogy. The bulk of the material is insulating or semiconducting, whereas the surface is acting as a metal. And now the peculiar band structure of this material is the one that is drawing my attention to this materials, because I work on magnetism and spintronics mainly. But the peculiar band structure of this material says that, look, there is a spin momentum locking. So what does it mean? If you see that this band, if you look at it, this is an upspin band and this is a downspin band, and this crosses this this gap, and then there is a Fermi level. So always you get a metallic surface state. Now, because of this peculiar band structure, you see that if there is an upspin electron which is moving in this direction, that keep on moving in that direction without any scattering. So now if this upspin electron has to scatter back, it should change its spin direction, because to accommodate this band structure. So a downspin electron is moving in this direction. Now, unless I have a magnetic impurity in the system, I cannot take a U-turn here. So that means this electron, ideally speaking, will keep on moving in that direction, and I will get a perfect source of spin polarized electron. So that's the kind of idea that by which we are interested in this kind of materials. And over the last decade, many new exciting things are happening. And at the end, I will also touch upon this topological insulator superconducting interfaces, which can potentially host topological superconductivity. So this is typically what you do, angle resolved photoemission spectroscopy, to understand the band structure. So this is the bulk valence band, this is the bulk conduction band, and this is the topological surface state, and that gives rise to something called a Dirac point or a Dirac cone. So this is an example of a crystal that we made in our lab and then did the angle resolved photoemission at Bhubaneswar. So now the band structure engineering in semiconductor physics is a central theme. So there are different ways people were doing the band structure engineering. Either you look at a field effect transistor, you apply electric fields, or you dope the materials, or you do the buck function or band gap engineering in heterostructure designs, and you can tune the band structure of a material. Or Professor Chandrabas was telling you in the morning that strain, you can apply high pressure, etc., or strain by growing thin films on a substrate, etc. Or you can play with the dimensionality, 2D materials, 1D nanowires, etc. So in that sense, if you look at the last few decades, you will see that there's a lot of activities happening around this, band structure modification. So this is our aim also. So I will, with this brief introduction, let me get into the talk which I'm going to give today. So I'm going to play something called a Lego game. So we have 2D materials, all this, graphene. So if you look at the materials like graphene, hexagonal boron nitride, niobium selenide is a superconductor, MOS2, and then many of these topological insulators. These are all 2D materials because their layers are connected by van der Waals interaction, so that you can easily exfoliate this material. So if I have a graphene and I put a scotch tape, and then if I peel off, and the graphene gets into the other sheet, and again put another scotch top, peel off, another scotch top. So like that, repeated peeling off will give you thinner and thinner layers, and you can exfoliate down to a single layer of graphene. So today I'm going to tell about how to play Lego with this kind of 2D materials. So let me start. So the material that was envisaged in the second generation of topological insulators, the first generation was simple bismuth antimony, bismuth doped with antimony, etc. When it came to the second generation topological insulators, people started talking about bismuth selenide, bismuth telluride, antimony selenide, antimony telluride, etc. So this materials has got a bulk band gap of 300 MeV, and this forms a quintuple layer of selenium, bismuth, selenium kind of thing. And then the next layer can be exfoliated out of it. So this quintuple is intact. It's approximately a kind of 1 nanometer. It's around 0.9 nanometer. And then, you can make several, exfoliations, and you can make thinner and thinner two-dimensional materials. So the step height, as I said, is around 0.96 nanometer. But if you look at this particular band's angle resolved photoemission spectroscopy, what I said in the beginning, that I want the bulk to be insulating and the surface to be conducting. But if you look at this band structure, you see that your Fermi level is sitting deep into the bulk conduction band. So when the Fermi level is in the conduction band, this is a heavily n-doped material. So the intrinsic silicon vacancy in bismuth selenium is responsible to make it self-doped like an n-type doped material. So now I cannot distinguish between the surface state and the bulk, because the bulk itself is heavily conducting. And if I have a surface state, then that surface state will get completely masked by the immense conduction of this bulk. So then, people have different ideas of making, different kinds of crystal. So, for example, if you take bismuth selenide, it's an n-type semiconductor because of intrinsic doping, because you don't get the ideal composition all the time. At the same time, if you take antimony telluride, it is an intrinsic p-type material. So then people started thinking about, can we make a solid solution of this? That means you make a material with the bismuth, antimony, tellurium, and selenide And is it possible that, you push the Fermi level into the bulk band gap? And, this is one such crystal that we made. Please understand that this is the actual composition. Actually, we intended to make bismuth 1, antimony 1, tellurium 1, and selenium 2. And but at the end of the day, what turned out to be in this particular crystal, it is 1.25, 1.75. So when I say 1.25, 1.75, it is not the intended composition. This is the final composition that is obtained here. Now, the angle salt photoemission spectroscopy told us that in this kind of a material, the Fermi level is within the band gap. So what you see is only the surface states, and your conduction band and the valence band is not seen here. So this is a potential candidate for getting this, the ideal topological insulating properties. So let me just tell you, these crystals are grown by modified Bridgman technique in our lab. So in order to make one crystal, you need around 15 days. Probably around 10, 15 crystals were made. Finally, this crystal is cherry-picked with the right property. So that means if you want to make, 10 to 15 crystals, and each crystal will take around 15 days, then all sort of characterization, etc. How tedious this work is. But at the end of the day, you get a crystal that gives the right properties. So then, we investigated this crystal further. So this is just to give you about, you take a flake of this, we call it as BSTS because it has got bismuth, antimony, tellurium, and selenide. And you look at the X-ray diffraction, you see that all 00L peaks like 003, 6, 9, 12, everything is present here. And there's no other peak. So this is giving you a kind of confidence as this is a single crystal. On top of this, we do Laue diffraction, and there also we index it and find that this is a perfect single crystal. So now what do? You exfoliate these crystals and start making devices out of it. So to start with, a particular device I'm going to talk about here is that you take a silicon substrate and it has got silicon dioxide in it. On top of it, say typically 285 nanometers of silicon dioxide. And on top of that, you exfoliate a layer of, a few layers of your BSTS, which is bismuth, antimony, tellurium, selenide. And then you cap it with hexagonal boron nitride. Hexagonal boron nitride is also another material that can be exfoliated. And then you give electrical contacts that, you deposit gold here, you deposit gold here. So this acts as a source, this acts as a drain, and you have a top layer contact through this gold. Then you can apply a gate voltage because HBN is an insulating material. And across this few layers of HBN, you apply a gate voltage. And then this is a top gated device. And similarly from the back side, using this silicon dioxide as an insulating layer in between, you can do back gating as well. So you can make a device and then you can do top gating, you can do back gating, you can pass current through it, you can measure the resistance, you can measure the Hall effect. So this is the real image of such a device. So this is a flake of this BSTS. Then there is a HBN capping on top of it. You have, see, two electrical contacts, these two, that passes current through it. If you measure the resistance across these two leads, you get the longitudinal resistance. If you measure the voltage across these two, and if you apply a magnetic field perpendicular to this, you get the Hall effect. And then if you apply a voltage through this line, then you get the top gating. So this is a typical device that we make. So now it's very easy to say that, this is very easy to make such devices, but it's a real complicated process and it needs a lot of hands-on experience to get good quality devices. So what we do, you take a glass substrate and then put PDMS on it. And then using a scotch tape, you put HBN on it. And parallelly, you take silicon dioxide substrate. And then you using scotch tape, HBN at the top and BSTS here. And then what happens? One is glass. So if you bring this glass substrate on top of it, you can look through this glass substrate and you can see under a microscope this BSTS, and you can align this the top plate such a way that the HBN is coming on top of the BSTS, and you bring it close to each other, and after touching, and then you apply some some temperature so that releases the HBN from the PDMS. and then you get a transfer of the device here. So now this is a silicon dioxide substrate on which you have BSTS, and on top of that you have HBN. And actually this is done in a glove box. So what we do is that we have everything, all the crystals and everything made and keep it inside the glove box. And then we have a microscope, optical microscope inside the glove box. And then we made our own stages, so that you could look. I mean, then there is a camera here and there is a screen here. You can look through the screen, and then you can start adjusting the position, and you can land this HBN on top of this BSTS, and you can adjust the height so that then they touch each other, and then it is sitting on a heating stage. You apply the right temperature so that one layer releases, and then you get the transfer. So now you have a BSTS layer protected with HBN. This HBN acts as two different, has a dual role. One, it protects the top surface, because we will be taking out this, inside this, it has got less than 1 ppm oxygen level. But once you take it out from the glove box, you are exposing to atmospheric oxygen. So this HBN protects the surface of this BSTS, and also this can act as an insulating layer for the gating studies. So this is how you make the device. And after making this, then we do the lithography to give electrical contacts. We do E-beam lithography to give electrical contacts. And you see, we make several such devices, and you have to do the same study over several such devices to find out the repeatability and the reproducibility of the results. So once you have repeatable and reproducible results, then we say that, okay, this is the result, and then we start investigating the physics behind that. And here you can see that each device has got different shape and size. This is because you have no control over the exfoliation. So once you do an exfoliation, it gives an arbitrary shape. If you do a next exfoliation, it gives a different shape. So each of this device will look, shape-wise differently. But since we know all the parameters, like what is the thickness of the flake and what is the distance between the voltage probes, the distance of the current probes, etc., you can get all the properties of the material evaluated from this kind of devices. So this is how we make the device. Now, what we do, we make this device, and then at the end of this pads, we have larger pads, and where we do wire bonding. So we don't do the soldering, and we don't do the silver paint, because that can lead to bad quality interfaces. And also, if I do a soldering here, this entire device blows off. So you can't afford to have a soldering here. So we do wire bonding. After the wire bonding, we put it into a chip carrier, and this chip carrier, the other end, we do the soldering to the base plate of your cryostat. So this is an Oxford cryostat where there's a chip carrier, and then this is a chip holder, and this is inserted there, so that without any soldering or anything, your now device is ready for the measurement. And you can cool this system to 2 Kelvin or millikelvin temperatures, depending upon what kind of experiments you do. And you can apply high magnetic field, and you can do temperature dependence of resistance, resistivity, and also you can look at the magnetoresistance and all those kind of things. So this is how we make the device, and then we move forward. And we do typically 2 different kinds of measurement. Either we do a DC measurement, we're using a current source and a nanovolt meter, or we generally prefer to do a lock-in technique, because that can give you, better quality results in terms of, many noise aspects can be thrown out with this kind of a lock-in technique. So this is how we do the measurements. Now let us look at, I told you, look, a topological insulator is a material that is insulating in the bulk and conducting at the surface. So, and also I told you that we did the angle salt photoemission spectroscopy, and there we got indications that our Fermi level is into the band gap of this material. Now, if that is true, now if I look at the resistance versus temperature of this particular, so I'm just talking about 2 different devices here. You see that as you decrease the temperature, the resistance keep on increasing. It keep on increasing and reaches a maximum point, and then the resistance starts coming down. So I can interpret this result. You have seen many kind of metal insulator transitions. But here, I'm just telling you here, look, this is the bulk which is insulating. This part of the data is given by the bulk which is insulating, and this part of the data is given by the surface which is conducting. So what's happening? The bulk is a semiconductor with a 300 millieV band gap, and as you decrease the temperature, the resistance of the bulk keep on increasing. But at the same time, if you look at the lowest temperature, I say that the resistance of the bulk has gone to much higher values, whereas the surface has got some conductivity. That surface conductivity, if you start increasing the temperature, the resistance keep on increasing. And above a particular temperature, the surface resistance is keep on increasing, whereas the bulk resistance now matching the surface resistance, then onwards the bulk starts dominating. So now this is a second proof that ARPAS is a conclusive proof that the Fermi level is in the band gap. And now it gives an information that could be that you have a material which is insulating at the surface, at the bulk, and it is conducting at the surface. Just to check with you, am I audible, right? I'm not losing the connection, right?
Yeah, you're still good.
Good. Yeah. So now comes the next level. You made a material, you think it's a topological insulator, you did ARPAS study, you found that the Fermi level is in the band gap. You did the resistance versus temperature, and you found that indications of an insulating bulk and a surface conductivity. Then what you can do a gating study. I had a top gate. Now I start increasing the voltage to 4 volt, and I look at the resistance. I look at this data which is collected at 2 Kelvin. You see, as you decrease the gate voltage and it comes to 0, this gives you the resistance which is same as this resistance. Now, if you increase the gate voltage in the negative direction, and you see that it goes through a maximum and then it starts coming down. I would say that what is happening here at this point of time, believe me, what I'm telling is correct. I'll give you further proof that what is happening is that you are started moving the Fermi level of this material because you have this gating. So you started moving the Fermi level of this material. And if there is a Dirac point, when the Fermi level hits the Dirac point, you have minimum density of states, and then you have maximum resistance. So what is happening is that, look at this peak. On the right side of this peak, your Fermi level is above the Dirac point. At the top of the peak, your Fermi level is in the Dirac point. And below this point, your Fermi level is below the Dirac point. That means this region is an N-type conductor, and this region is a P-type conductor. The same material, just by doing the gating, you can make it N-type or P-type. So if this is also true, then you are further reinforcing the fact that this is a topological insulator. Now, how do we do this? You go to the Hall effect measurements. Look at this. X-axis is the applied magnetic field. You see that for certain gate voltages, it gives a slope in this direction, and for certain other gate voltages, this is a back gate voltage, back gate, gating. That's why you see higher voltages. You see that the slope of the curve. All of us know that the slope of the curve will tell you the nature of charge carrier. If it's like this, it's an N-type carrier. If it's like that, it's a P-type carrier. Now, across this charge neutrality point, I said that this is a P-type region that is further reinforced by this Hall effect measurement. So now all these things are coming close to the kind of conclusion that you have a topological insulator. You can further investigate. You have in this particular case for certain thicknesses, we can analyze the Hall voltage in a 2-component carrier density and mobility model. There we find that there are 2 different channels here in our particular system, and one channel that exhibits a mobility of 100 to 300 centimeters square, whereas another channel that is giving you a mobility of around 2000. We can also calculate the carrier concentration of each of this channel. And this is a very busy slide. Please don't look into the details. I just wanted to tell you is that we are in a position now to tell that we have the Rashba, the topological surface state, and in this material, because of the heavy spin orbit interaction, we also see what is called the Rashba surface states. And also in a topological insulator, when you look at the magnetoresistance, you can fit it with an equation called an HLN equation. I hope HLN equation is not given here. And then you can also find out how many conducting channels are there. Now, coming back to this point of, so this is a device which is backgated. Look at this resistance versus backgate voltage. This is another device. But I keep on changing the device, but the physics remains the same. So here you see that as you decrease this gate voltage, the resistance goes through a maximum and then the resistance goes down. So this maximum point is the point where the Fermi level is at the Dirac point. And above this peak, it is an N-type conductor. Below this peak, it's a P-type conductor. Then what you can do, you can look at the, this is conductivity versus gate voltage. You see that two different regimes. We can also calculate the mobility of the P-type regime and the mobility in the N-type regime. So this is how we can do that. Now, in order to understand the physics here, what you are doing is that you are moving this Fermi level across this point. When the Fermi level is above the Dirac point, you have N-type conduction. When you bring the Fermi level below this Dirac point, you have the P-type conduction. So we ask this question, in this kind of a material, since we are able to do this kind of P-type region, N-type region, we ask the question, can we make a PN junction out of this? So the motivation comes from the fact that in graphene, people have looked at PN junctions. In topological insulators, people have not looked at PN junctions. So we have another interest here. As I told you, the electrons are spin polarized. Our end goal is to look at the spin filter effects in this kind of situation. So there's no experiment prior to our experiment. So that's motivated us even further. Again, we make different kinds of devices of different size and shape. This is not within our control. Each exfoliation gives you different size and shape. So now, what are we doing here? Look at here, silicon dioxide, topological insulator, and we have a gate here and gold on top of it. Here, this is the source, this is the drain. Now, imagine that if I apply a large gate voltage from the backside, I can make this entire topological insulator either N-type or P-type. Similarly, if I apply a gate voltage from the top, I can make the region below this either N-type or P-type depending upon the voltage that I apply. So that means by applying a suitable gate voltage from the backside and the top side on the top gate, you can make regions which are entirely N-type or entirely P-type or a small N-type region included in a P-type matrix or a small P-type region included in an N-type matrix. So this gives you a very good flexibility of, by moving this Fermi level, you can do, so this is called the local gating and this is known as the global gating because the entire device is connected from the backside, whereas the top side is only a small restricted area. So now what we did was you did a different, if you follow this schematics, by depending upon what kind of gate voltage you apply from the bottom and the top, we are able to make a device which is, now this is PNP, this is NPN, and this is completely P, and this is completely N, and so many such varieties are possible. So now, so this is the schematics. So just concentrate on this particular graph only by applying a top gate and a back gate. I can make it either NNN type or PPP type or PNP type or NPN type. This is just to give you a feel, there's a lot of physics involved here and which I'm not going to discuss because, I just want to discuss something more here. And also we really looked at the quantized longitudinal resistance at 7 Tesla. And this is further reinforced by doing the measurement at 25 millikelvin at 16 Tesla. So finally, I just wanted to tell you is that, it's a rich field. So in a silicon, for example, in silicon, if you want to make a PNP junction, you have to dope locally or, you have to dope N-doping, P-doping, everything separately. Now imagine the beauty of this material, a single material where just by applying the gate voltages at the appropriate places, you can make a PN junction, you can make a PNP, or you can make an NPN, so whatever way you want. So this is the beauty of this kind of experiments. So we are working on it. The work is in progress to explore further aspects. So I just wanted to tell you, since I was telling you about this game of this 2D Lego game, we also try to look at, can we make a two-dimensional superconductor and then use that topological insulator that we made, because that's a perfect topological insulator, because it gave all the right ingredients of a topological insulator. Bulk was insulating, surface was conducting. So we asked the question, can we make a junction between a superconductor and a topological insulator? And this long-standing prediction of 2008 that if you make such a structure, you can induce topological superconductivity in a topological insulator. So again, see, we grow all our crystals, so this is done by chemical vapor transport method. So niobium selenide crystal, and this is like an image of a crystal. So the crystal that we made was with a composition of niobium selenide 2.06 plus minus 0.09. So that means it's an NBSE2 crystal. So this analysis done by EPMA. So we take this EPMA analysis at several points. In this particular case, this is the data from 41 different points. We do it and then we do this. That's how we get this error bar of 0.09. So this is the compositional variation we are talking on the surface. Again, this devices also, we make, the niobium selenide device, we exfoliate it and then find that, it shows the right superconducting properties. So initially we faced some difficulty with this fundamental phase in this niobium selenide, and then which we overcome by appropriate dissipative coupling. And then now we have a superconductor which has got a TC around 8 Kelvin. And then we have a topological insulator which is a bulk insulating and surface conducting topological insulator. We ask a question, can we bring them together? And then we can see whether we can see topological superconductivity. So the prediction says that if you have topological superconductivity induced, then that should host Majorana fermions. So that's a theoretical prediction. And this particular work, which we published earlier, says that when we have this superconductor, which is niobium selenide, and then this topological insulator, and we see topological superconductivity from all our DI/DV curves and everything. So we showed that it is possible to have two-dimensional superconductivity at the interface between a topological insulator and a superconductor. So now we ask the question. We also do a lot of different kinds of work. So we ask the question, so that is published. Now I'm talking about the work which is ongoing. I told you earlier that we make this topological insulators. See, this topological insulators, here you see that we cover it with hexagonal boron nitride. We also did quite a lot of work where we covered the top surface with complete hexagonal boron nitride. So because this structure, if I transport through air to my electron beam lithography system, you see that this surface of the topological insulator is exposed to ambient. And what we found is that though everybody feels that topological insulators are intact and it will not get affected, but what we see is that, look, the surface is getting slightly modified. And you see that if you analyze the conduction mechanism itself, if it is completely covered with HP and boron nitride, you see that it gives you the Nyquist electron-electron interaction model. Whereas if we are leaving this surface open here, we get always the variable range Hoping conduction mechanism here. That is because oxygen is attacking and there are defect sites forming, etc. So in this particular case, we devised a new technique to give contacts to the side surface of a topological insulator. Imagine that this is my multi-layer. So what we do, we cover it with the top hexagonal boron nitride, and then we give contacts from the side surface. So that means the junction of these two can be contacted. So it's like a one-dimensional chain kind of thing. So we ask a question now: if we make a bismuth selenide, which is a topological insulator, and we put niobium selenide on top, what happens at the side surface? So the top surface, we know, we showed that it is possible to have induced superconductivity. And what is more sought after is that you must have seen these experiments where semiconducting nanowires in proximity to a superconductor hosting Majorana modes. So we ask a question: can we have a similar one-dimensional structure here? And I think I'm running out of time. So this is the work ongoing. So we made this BSTS, niobium selenide, and then capped with hexagonal boron nitride. And then we started looking at the side surface. So that means this is completely capped with niobium selenide. Just below that, you have the superconductor, and below that, you have the topological insulator. Now, when you give contact from the side surface, what you are looking at that if there is a one-dimensional superconductivity in the topological insulator side wall. And very interestingly, we see all the signatures of, this is the TC of the niobium selenide, and the superconducting gap opens up. And we see that, look, there is a possibility of, we do see evidences that, topological superconductivity in one-dimensional side wall here. And this is further substantiated by the fact that, so I told you, I can move the Fermi level up and down in my topological insulator. Now I have a back gate. Now we ask a question: what happens to this system when we start? And look at this. This is a source drain current with the normalized conductance. You see that when I start changing the back gate voltage, you see at certain back gate voltage, that means at the point where this Dirac, where the Fermi level is hitting the Dirac point, you see something called the zero bias anomaly. Zero bias anomaly is a holy grail, and it can come due to variety of reasons. But in this particular case, we believe that this zero bias anomaly that we are seeing here is due to this one-dimensional superconductivity that is induced at the junction. And this thing is vanishing above a particular point and below a particular point. So that means this zero bias anomaly is available when our Fermi level is very close to the Dirac point. And further, we also looked at the stability of this. You see that this zero bias anomaly is at 0 Tesla, it is there. The moment I apply more than 30 millitesla of magnetic field, this zero bias anomaly completely vanishes, and above that you see the normal behavior of an niobium selenide. So this may be indicating that, look, not only in the two-dimensional, which we proved already, now in a one-dimensional chain also, we are getting all ingredients of topological superconductivity. If the theory can be believed, then this is a good host for the Majorana fermions, which is predicted, and we have not investigated that fact yet. So to conclude, I just wanted to tell you, this is a glimpse that quantum materials are proving to be a building block for future electronics, right? The spintronics or, everything. There's a lot of scope in this kind of, material for this materials. And also I showed you that electrostatic gating allows novel aspects of topological surface state. And also I showed you that NPN junctions made out of this topological insulators. These are the areas we now, because once you have this NPN area, and if there is an upspin electron moving towards this, the moment it hits this P region, then it should take the boundary and then come back. So we are exploring the possibility of spin filtering effect, etc., in this kind of materials. And also the most exciting thing which we think at this point of time is that we are able to show superconductivity in a niobium selenide topological insulator junction, and that is published. Now we are in the process of getting this one-dimensional superconductivity where we get all ingredients of this effect. And hopefully this will be a hot area in the coming years. And with that, let me thank you for your attention. This is my research group. This is taken last year. Now students, very less number of students are here. Thank you for your attention.
So thank you very much, Anil, for these very recent and very exciting results on topological physics. The session is now open for questions. I would request people who have questions to either type in the chat window.
I won't be able to see the questions.
Yeah, so you can type in the chat window and I will then repeat the question.
Because my screen is shared, so I won't be.
Since nobody is typing, shall I ask a question, Baskaran?
Yes, Professor Baskaran.
Certainly, Professor Baskaran, sure.
Thank you, Avinash. So, Anil, it was a wonderful talk. I'm very happy that Narayana Fermions have come to Bangalore. So,
induced superconductivity, Majorana not yet. We don't know. It may be there.
No, because you see the zero bias conductance, very beautiful way. So, my question was related to that. There, according to theory, there should be a Majorana mode, which has some characteristic size. And the theory, predicts some characteristic size. It would be very, very nice to measure that characteristic size at the end of this superconducting wire. So I don't know if I make myself.
Yeah, it's true, Professor Bhaskar. And so then, what kind of experiments that one should do is that should be able to do an STM measurement at the extremely low temperatures. This is what people did for the semiconducting wire superconductor junctions. So we are also in the process of looking, we have to do these measurements below 2 Kelvin. So we are also looking at the possibility of those kind of measurements now.
Okay. I have another short question. This quintuple layer Bi2Se3 family. At what stage the surface Dirac cones start overlapping? Like if you take one single quintuple layer, it's very likely that the two Dirac cones very strongly overlap.
I will tell you what's happening here is, see, for example, when we make this kind of devices, okay, maybe the best thing is my first picture. So if you look at these things, what we have seen is that, though the predictions, the calculation says that this surface state can penetrate into the bulk up to around 2 to 3 nanometers.
Okay.
What we do is that if we have two decoupled surface states, when you do the magnetoresistance at very low temperatures, because of the weak anti-localization, the resistance suddenly drops. And you can calculate by fitting this data with HLN equation, and we can find out the number of conducting channels. What we found is that if the thickness of this layer is 10 nanometers, so we see a single conducting channel, that indicates that probably your top surface state wave function and the bottom surface state wave functions are overlapping and you get a single channel. The moment we put more than 10 nanometers, 10, 15, 20 nanometers, we see the alpha value, which we calculate as a number of conducting channels, are 2, indicating that they are decoupled. So to give a short answer to your question, below 10 nanometers, that means 10 quintuples, we see that they are talking to each other.
Oh, I see. So it's as large as 10 quintuples.
That's what we get. It could be due to the defects in the material, etc. Maybe an ideal structure. I think the calculation says that it should be around 2 nanometers or something like that.
And you also mentioned about the issue of selenium vacancy.
Yeah.
How much you can overcome that problem now, in terms of material science? Because
it is a tough problem, because you know that the kind of doping which we are talking about is 10 power 17, 10 power 18, 10 power 19. So it's a very minute, parts per billion kind of a doping which is coming in. So we have overcome this difficulty just by making this material where this Sb2Te2 is a p-type semiconductor. The self-doping is making this Sb2Te3 as a p-type and Bi2Se3 as an n-type. So we did a series of composition. It is not that this is the only composition we did. We did a series of composition and we found that there are n-type crystals and p-type crystals, but where the Fermi level is into the bulk. So this is the crystal where we found that the Fermi level is in the gap. So around this composition, we are able to overcome this problem. Ideally speaking, what I want is a crystal where this resistance should keep on increasing up to room temperature. That means I should not have any bulk conduction. Bulk should be really insulating. So that's not still happened.
Thank you. Thank you.
Yeah, so we might have time for another question or two. So
Sir,
somebody has a question, please just make yourself audible and just
one. I have one small query, sir.
Yeah, please go ahead, Dushyant.
So on the NPN junction slide, that it was pictorially depicted in one of the slide. Yes, sir, here. So at a time we have to use only one this gate voltage, okay, sir?
No, we can do both independently.
Okay, sir. So suppose this full region, I mean in this topological insulated region, if suppose we want to make it fully NRP type, then what we have to, I mean, do the voltage or some supply for the VTG. I mean, we have to set it to 0 or some other voltage.
No, see, VTG 0 in our material, VTG 0, VBG 0 in our material is intrinsically n-type because our Fermi level is above the Dirac code. So if you don't apply any voltage here, it is an n-type material.
Okay, sir. So, okay, independently we can operate both gate voltage.
We can independently apply both. That's why in one of the graphs I showed you, the x-axis is VTG and the y-axis is VBG.
Yeah, right, sir. Yeah, I got it. Okay, sir. Thank you, sir.
Any other question? Maybe we can accommodate another question if anybody has. If not, please join me in thanking the speaker once again through maybe actual claps or virtual claps. Thank you, Anil, for the very nice talk.
Thank you. Thank you.
So next speaker, so now we are going to have two contributed oral presentations. So next speaker is going to be Mohammad Salman Siddiqui, and he's going to talk about soil moisture measurement using some interesting devices, I think. So could you start sharing your screen and go on with your presentation? So
yes, sir.
As I mentioned, you'll have 12 minutes for talk and 3 minutes for questions. After 10 minutes, I'll give a short warning. Yeah, please go ahead.
Slides visible to all of you?
Yeah, slide is visible. It's good.
Yeah. Good afternoon, everyone. I am Mohammad Salman Siddiqui, working under the guidance of Professor Muhammad Aslam. And today I am going to present graphene oxide based multi-sensing probe for monitoring of in-depth soil moisture for advanced agricultural application. The outline of the presentation is the first. I will discuss about the motivation of the present work. After then I will talk about different type of moisture sensors available in the market and their pros and cons. And I will discuss about the graphene oxide based macro sensors for the humidity sensing measurement. Further, we have used graphene oxide for the humidity as well as soil sensing measurement. For that, we have done the fabrication of the IDE structures. After then, I will discuss about how that multi-sensing probe or array sensing probe can be used for the soil moisture profile measurement and the effect of the lumps formation on the soil moisture measurement using that multi-sensing probe. I will end the talk with the conclusion part. The motivation behind the present work is that we all know that the employment in India is 52% agricultural based, but the amount of the GDP obtained from the agriculture sector is very low. That is 14% according to the data from 2018. But the other sectors results in the high value of the GDP and 80% of the water resources are used by the agriculture sector. Why there is a low value of the GDP is because there are several issues in the Indian agriculture, such as the decrease in the yield of the crops, the agricultural marketing is not proper, lack of mechanization, soil erosion. And the decrease in the yield may be due to one of the following factors or maybe all of the factors, such as non-maintenance of the soil moisture in the crops, non-maintenance of soil moisture in the crops, not maintaining the proper fertilizers, the crop health, weather suitability, soil suitability also play a beneficial, important role in the yield of the crops. I will discuss about the maintenance of the soil moisture using graphene oxide based array sensing probe. And the soil moisture sensor must be affordable, and it must be accurate, and it should be easily usable in order to maintain measurement of the soil moisture in the crop field, and it will help in the increase in the yield of the crops. These are the different type of soil moisture sensors which are currently available in the market and are basically used, such as the gravimetric technique, neutron scattering techniques, FDR technique, this is the frequency domain reflectometry, dual probe heat pulse technique. There are several pros and cons of each technique, such as gravimetric technique is only a lab-based technique, and it is a destructive technique, time-consuming, as well as inapplicable to automatic control. While the neutron scattering is very costly, and it have some radiation hazard also, and need to calibrate for different types of soil. Frequency domain reflectometry is also a very high cost technique, and special calibration is also required for this technique. Dual probe heat pulse technique is a inexpensive technique, but it requires very high power for its operation, as well as it is very soil temperature dependent, and it has very small zone of influence also. And in all these techniques, or except the FDR technique, these all techniques cannot be able to monitor the in-depth soil moisture, which is very necessary for optimum irrigation. That's why there is a need of micro sensor technology. Using macro sensor technology and using some multi-sensing points along the probe can be used to analyze the moisture content at different depth zones. At present, no moisture sensor can be used for soil moisture penetration at different depth except FDR. And the device constant for the macro sensing technology, that it need to be stable also. It must have multi-sensing point to analyze the moisture content at different depth zones. The sensor need to be thin as possible in order to avoid the soil disturbance, and it must be temperature and soil conductivity independent also. And this can be achieved using graphene oxide based micro sensor, which was earlier used for the humidity sensing measurement. As we all know, that graphene is a one carbon atom thick two-dimensional layer which is arranged in a hexagonal lattice structure. It has very excellent electrical properties as well as the sensing property due to its large specific surface area. And the derivative of the graphene, which we called as graphene oxide, have a different amount of oxygen functional groups on the edges as well as the basal plane, such as epoxide, hydroxide, phenolic groups, etc., as shown in the figure. And these are the few literature survey that people have used the graphene oxide earlier for the humidity sensing measurement. After then, in order to use the graphene oxide for the soil sensing measurement, we have synthesized the graphene oxide using the modified Hamas method. These are the SEM, TEM, AFM pictures, and this is the height cross-section profile to measure the thickness of the graphene oxide seed using the AFM. The average height of the seed is around 1 to 2 nanometer, and the specific and the surface area of the sheets is vary from 100 to 400 micron. After then, we have in order to confirm the presence of the oxygen functional groups in the sample of the geo, we have done the XPS analysis and the Raman analysis, and this is the high resolution C1s spectra of the XPS of graphene oxide, and this is the Raman spectra. The OYC ratio obtained in case of XPS, that is 0.43, and the high value of the ID by IG 1.20 confirm the presence of several functional groups on the graphene oxide surface. After then, we have done the fabrication of interdigitated ID structures using the conventional lithography method on the SiO2 wafer. The finger width is around 50 micron, and the interfinger spacing of the ID structure is around 92 micron. This is the schematic of the conventional lithography which we have used for the fabrication of ID structure. Further, after the fabrication of the ID structure, we have drop casted the graphene oxide having a concentration of 2 mg per ml, and the 15 microliter of the graphene oxide was drop casted on the ID structure to fabricate a single micro sensor. After then, we have arranged all micro sensor. We have taken the 5 micro sensor geo based on the PCB board, and we have fixed those micro sensors on the PCB board, and the connection were taken using the copper tracks. The height of the final device, that the graphene oxide array probe sensor APS, was around 20 centimeter, and the width is 4 centimeter, and the thickness is around 0.5 centimeter. In order to encapsulate the graphene oxide array probe sensor, we have make a mask 3D design mask using the SolidWorks tool, and it was printed using the 3D printing technique. Further, we have encapsulate the geo APS as shown in the figure C, and the windows were covered using a mesh of pore size 145 micrometer in order to avoid direct contact of the soil particles with the micro sensing units. This is the SEM picture of the fabricated ID. This is the magnified view, and this is the SEM picture taken after drop casting of the graphene oxide between the ID fingers. Initially, we have tested the graphene oxide array probe sensor using different saturated salt solutions, which we have used to maintain the constant relative humidity environment. The relative humidity was varied from 11 to the 97% using saturated salt solution as shown in the figure, and the GeoAPS was fixed in a closed container, and the response was measured using a LCR meter. And we have also done the DC measurement at 55% relative humidity levels in order to confirm the adhesion of the graphene oxide on the ID structure. The graphene oxide makes a linear ohmic contact with the prepared ID structures. This is the response of the graphene oxide array probe sensor with respect to the relative humidity. The capacitance of the 5 microsensors which are arranged on the graphene oxide array probe sensor goes on increasing with the increase in the relative humidity levels, as it is clearly shown that the capacitance goes on increasing, and the response which we have calculated using this formula is also plotted here, and the response also goes on increasing with increase in the relative humidity levels of the graphene oxide array probe microsensors. Why there is increase in the capacitance and the increase in the response with increase in the relative humidity? It is because as we goes on increasing the relative humidity, the water molecule get physio adsorbed on the graphene oxide sheets and makes hydrogen bonding with the functional groups, oxide functional groups which are present on the graphene oxide sheets, and which further results in the dielectric capacitance dielectric constant of the graphene oxide sheet, which further results in the increase in the capacitance of the sensor. After then, we have used the graphene oxide array probe sensor for the soil moisture sensing measurement using a conventional LCR meter, and this is the schematic of the experimental setup which we have used to perform the soil sensing measurement. This is the experiment. This is the digital image of the experimental setup. This is the soil mold, and the geo APS, the graphene oxide array probe sensor is deployed in the soil mold, and the response is calculated again with the use of the LCR meter. And these are the results which we have obtained using the soil moisture with the variation of the soil moisture content. In this case, also the capacitance of the graphene oxide array probe sensor goes on increasing with increase in the soil water content, and the response is calculated using this formula, where Cx and Ci are the capacitance of the sensor at X% and the 3.2% soil moisture content respectively. We have also done the response of the measurement. The GeoAPS shows good repeatability. As well as we have performed the stability of the graphene oxide array probe sensor with respect to the 3% and the 43%, and the graphene oxide probe was stable around 46 months, and it can be used without further calibration at different stages of the crop without further calibration. After then, we have used the soil moisture profile measurement using the graphene oxide array probe sensor. This is the soil moisture profile which we have obtained using the graphene oxide array probe sensor. It can be seen from the diagram that the sensor S1, S2, and S3 responds very quickly due to the infiltration of the water downward. But after a certain and the sensor S4 and S5 respond after 18 minutes and the 38 minutes. But after a finite interval of approximately 2 hours, there is a saturated moisture condition occurs, and all the sensors approximately show the same value of the moisture content. This type of profile measurement can be used for the infiltration rate as well as to track the moisture movement within the soil mass, as well as to measure the moisture content at different depth zones, which is very necessary for the optimum irrigation application purpose. After then, we have tested the graphene oxide array probe sensor in case of lumps formation within the soil mass. When there is a uniform lumps formation, a single sensing unit works very well. When there is a non-uniform distribution of soil moisture, the single sensing micro sensors, which is earlier in the market, leads to inaccurate results. That's why we have tested the GeoAPS in such conditions. Also, we have prepared 3 different types of soil samples, 3%, 15%, and 35%. In these 2 cases, there is a uniform distribution of the soil moisture, and the GeoAPS works very well in comparison to the overnight method. And the main advantages of the multi-sensing point that in this case, when there is a lumps formation of soil mass, it can be seen that the sensor S2 and S3 are not in contact with the soil mass, and it leads to very small value of the moisture content, that is 25 or approximately 30. But other 3 sensors, that is sensor S1, S3, and S5, are still in contact with the soil, but and the average value of the GeoAPS is very much close to the overnight method. The main advantages of the multi-sensing configuration is that that even if the few macro sensors are not in contact with the soil mass, the other sensors are still in contact, and it leads to the positive average value, which gives the accurate value of the moisture content in comparison to the overnight method. And this is the moisture content measured from the GeoAPS and the standard overnight method due to the presence of the lumps in the soil. And it can be seen in case of 35% this water content samples, that few macro sensor leads to very small value of the moisture content, but the average value comes out to be 30.96, which is very much close to the original value. This is the conclusion. We have fabricated a soil water content monitoring technique using graphene oxide for in-depth soil moisture detection. The fabricated design of the GeoAPS is very useful in uneven distribution of soil moisture. Due to the multi-sensing configuration, the average value of the capacitance provide approximately same value of the moisture content present in the soil. And this probe design have a very small thickness, and it provides very minimum disturbance to the soil moisture, and it have very low power consumption, convenient installation, and the removal process. Environmental friendly operation of the design probe makes it a desirable candidate for cost-effective agricultural application. Thank you.
So Salman, thank you very much for this nice talk and nearly keeping to the time.
Thank you.
The talk is now open for questions. Yeah, Saurabh Gupta, yeah, please go ahead, and you can actually unmute yourself and please ask your question.
Hello.
Yes.
Yeah. At one place you have said that the H2 molecules are physio-absorbed.
Yeah.
So
how
it is different from chemi-absorbed, and why they are not chemi-absorbed and only physio-absorbed?
The oxygen functional groups present on the graphene oxide sheets makes a hydrogen bonding with the oxygen molecules from the outer surface, that is from the environment, surrounding environment.
So it should call as chemi-absorbed, na? They are chemically reacting.
Yeah. These are chemically physio-absorbed. Yeah, sure. Yeah.
So it is physio or chemi-absorbed?
These are physio-absorbed.
So you are saying that they are reacting with the OH of the graphene oxide sheets.
Yeah. No, they are not reacting. They are just making a physical hydrogen bonding with the oxygen functional group present on the graphene oxide sheets. And as we remove the sensor from the or changing the relative humidity from 97% or that 85% to the 55%, there is a reversibility in the measurement. Now that's why the atmosphere gets absorbed the water molecules which are originally physio-absorbed on the graphene oxide sheets. That's why we are saying it as a physio-absorbed molecule.
So
and why not chemi-absorbed?
Yeah, so maybe we can discuss this later offline.
Yeah.
We are running short of time. If there's one more question by somebody else, we can take that up now. So if not, please join me in thanking Salman for a nice talk on graphene oxide sensors for moisture content. Thank you very much.
Thank you so much, sir.
Please unshare your slides. Okay, so the next talk in this session is by Dr. Dushyant. He is going to talk about anomalous Hall effect in silicon nickel multilayers. So Dushyant, please go ahead and share screen.
Yes, sir. Hello.
Yeah, yeah. Yeah, go ahead.
Good afternoon, everyone. So, welcome to my talk. And title of my talk is Study of Skew Scattering Dominated Anomalous Hall Effect in Silicon Nickel Multilayers. So here are my outlines. So first I will introduce about multilayers and their some peculiar properties, and then we proceed for the anomalous Hall effect, and then experimental details, how the sample prepared and the type of the sample, the structure of the sample, and then I will proceed for the result and discussion. So on the result and discussion, I will discuss about the scattering phenomena like side jump and skew scattering in anomalous Hall effect, and then I will summarize and conclude my slide. So like multi-layers, basically multi-layer is a repetition of single bilayer, which is composed of a ferromagnetic layer separated by a non-magnetic layer. And there are many more peculiar properties which are exhibited by these multi-layer structures like metal resistance, whereas we know the material has a tendency to change its electrical resistance in the presence of an external magnetic field. So this can be used as a memory application. So another is geometric resistance is also kind of magnetic resistance, but rather it has a higher resistance and is a quantum based scattering phenomena magnetic material. And another is the exchange bias effect, which is where this is observed in bilayer system, which is made of ferromagnetic and antiferromagnetic material, in which it has been observed that a hard magnetization behavior of an antiferromagnetic material causing a shift in the hysteresis loop of a soft ferromagnetic material. As a resultant, we see the system shows a shift of the hysteresis loop towards positive or negative axis or the in magnetization measurement. Another is the Hall effect measurement, where generally we produce a Hall voltage across an electrical conductor placed in an external magnetic field, which is carrying a finite current. And that Hall voltage, that is in transverse direction to the both magnetic field and current. Due to these many and other many interesting properties, this is very promising the memory applications like magnetic and random access memory, reading writing heads of the hard disk drive. And also these are very useful in the magnetic sensing technology like position and motion detection in automation, power and power management and keyboard. As we know, the Boss meter is made of the Hall effect devices. So anomalous Hall effect, this is observed by Sir Williamson Hall in 1979, and in conducting material generally the observed Hall effect is known as the ordinary Hall effect, which actually linearly varies as we increase the voltage. This magnetic field, the resistance is linearly increasing, but in magnetic material this is changes in an extraordinary ways. This is non-linear with the magnetic field, and it has been observed that the anomalous Hall effect resistance is much and more than the ordinary Hall effect due to the inclusion of the extra term of the resistivity because of the magnetization of the magnetic material, and because of the magnetization of the magnetic material, which is caused from the scattering of the electron while it is traveling throughout the sample and encoded from many magnetic impurities. So this responsible for the anomalous Hall effect in magnetic material is basically there is two proposed this skirting phenomena. One is the skew scattering phenomena, and another is the side jump. So in skew scattering phenomena, it has been observed that while electron is traveling across an magnetic conductor, after encountering with the magnetic impurity, is scattered off by making an fixed angle from the impurity, and again traveling until it is again encountered by another magnetic impurity, and it has been found that its anomalous Hall resistivity is changed to vary linearly with the longitudinal resistance resistivity of the sample. And under the sand jump, inside jump, it has been observed that instead of making a fixed angle from the incident beam of the electron in a conductor, it is shifting towards up and down at the magnetic impurity based on the experimentation of the electron. So by combining these two effects, an empirical scaling law is also formed, which is for this, and another the side jump and scattering, two parameters are associated, and this parameter will tell the dominating factor or the dominating scattering effect in the magnetic material. So all these best effects are combined as originating from the spin orbit interaction and the exchange interaction happening in the sample. So here sample that we have prepared using DC magnetron splitting system at ambient temperature and with the use of plasma power of 40 volt at 420 to power minus 3 millibar of the sputtering pressure. We had deposited all the sample over silicon and glass substrate. So structure of my sample looks like this. The base is the silicon or glass substrate. So top of this substrate, first we have prepared a single bilayer. It is composed of nickel and silicon layer, and then we have made such a 20 repetition of the single bilayers. So structure will look like this. And for specifically for this presentation, the sample is noted by this, where nickel layer has a thickness of 30 angstrom and that of the silicon is varied from 5 to 100 angstrom. So under the result and discussion part, first I'd like to discuss about the structural part of the material, where this is the GXRD pattern open for the material. From this material we can see while we have seen a strong intense peak around 44.45 degree, which is mainly originating from the nickel material, and but we have not observed any peak from the silicon material. We have extended here graph, we have zoomed around 38 to 52, but there are two peaks, which is another is 151 degree, another is somewhere like 74 degree. But those were also when it is matched with the standard JCPD file, it is found that all those peaks are originating from the nickel layer. So this analysis tells that the nickel layer in multilayer system is of the polycrystalline form and has a strong structure along nickel 111 plane, and silicon layer is amorphous. So in this figure we have plotted the actual it was dominating, so these peaks were absent. So we have calculated this nickel nanocrystallized cell for only this peak. So here we could see that as we decrease silicon layer thickness in starting. Hello, I am audible or not? Hello.
Yeah, it's okay.
Hello. Yeah.
Yes, you're audible.
So,
go ahead.
So in starting is gradually increasing, and then below TSI is equal to 20 angstrom, it has very sharply increased. So region behind this sharp increase is found from the cross-sectional transmission electron microscope. This method image. From this image, we could see that we could see there is the presence of several pillar holes in the materials, and this tells that the adjacent nickel nanocrystal at the nickel layers are connecting with each other as a result, and we have observed a drastic change of the nickel nanocrystallized sizes in this graph. So next one is the magnetic transport property. We have measured anomalous Hall effect. So here's the Hall effect data. So in this Hall effect data, we could see that this for positive field, magnetic field, we are getting negative resistance, and for negative and vice versa, we are getting opposite resistance. So from this one, we could see that this behavior is seen for the electron-like behavior of the my multi-layer system. See here we have plotted in this graph the saturated Hall resistance versus thickness of the silicon layer. this saturated Hall resistance is calculated from this anomalous Hall data by extrapolating high field saturated data to the zero field and cut off where y-axis we have calculated, that is plotted here. We could see that this is also increasing as the degree silicon layer thickness, and upon reaching a maximum value, again it is decreasing. So decrease of this one below this this TSI is equal to 10 angstrom is, again we can confirm from this selected area difference fraction and the 10 images. We could see that the TSI is equal to 5 angstrom. All the nickel nanocrystallites are connected with each other, but for TSI is equal to 10 angstrom or higher for higher thickness, these are separated from each other, meaning that for the lowest thickness of the sample, the electron does not feel much and more resistance as all the nickel nanocrystallites are connected with each other. So we have normalized here in this figure to the right y-axis about the maximum thickness of the sample to the lowest thickness, and we have seen that around 33 times enhancement in the saturation Hall resistance is observed. And in the here we have plotted here in order to find out the type of the scattering phenomena happening in our sample. So for this one, first we have utilized the power law. In the power law, so rho Hs is the power of the anomalous Hall resistivity is plotted with the power of the longitudinal Hall resistivity. We could see that for few samples, those are giving the 0.05 exponent value of this n, and other samples are more than 3 samples, those are giving negative samples. This positive value of 0.5 exponent n is falling between 0 and 1, which is suggesting that the skew scattering mechanism is responsible for the anomalous Hall effect in our sample, but for others it is contradiction to the theory. So again, because of the contradiction, we have plotted using empirical formula. So by plotting this one, and all the data is fitted here very well, and we have extended the parameters A and B. So A value is coming to be positive and that of B is negative, so meaning that again it is confirming the skew scattering phenomena is responsible for our delta, but we can see a transition at this point, meaning that as we decrease the silicon layer thickness, this skew scattering phenomena is getting more prominent in the material. So here I want to summarize and conclude my talk. So in the silicon binickel layer is composed of the amorphous silicon and polycrystalline nickel layers. Sample shows the signature of electron-like behavior from the anomalous Hall study, and anomalous Hall study.
Are you finished, Dushyant? So looks like we might have lost Dushyant. Dushyant, are you there? Am I being heard? That's the first question. Hello, Dushyant. So if people have questions, Dushyant, thank you very much for the nice talk and very much keeping to the time. So now this talk is also open for discussion. Any questions people would like to ask? You can raise your hand and actually simply unmute yourself and go ahead and ask the question. Anybody has questions? No questions? Okay, in that case, I would like to thank all the speakers of this session for having kept to their time and for very lively talks. Thank you very much. And with this, I would like to end this session and hand the microphone back to Sanjay, who might have some other instruction to give us.
Yeah, thanks to Professor Avinash Mahajan, Session Chair of Experimental Condensed Matter, also speaker Professor Anil Kumar, and all other oral presenters. So we will have a group photo session quickly. So please on your video. So Mr. Shangshaktab, please be ready for photo session. So following photo session, we will have a virtual tour at IIT Bombay. So yeah, so first we will have a photo session. So please on your video.
Hello.
Yeah. So we'll wait for another 1 minute. So it takes some time. Sometime video coming. Professor Aptavalom, please come out.
Hello. And take the best photo finally, yeah?
No.
Take multiple photos.
Yeah, but then take the most
after end
handsome
of the
finally.
session. This
Take
is
the most handsome finally.
no, another photo. Last finishing will be end will photo session.
So as Sanjay requested, everybody please enable viewing yourself by others.
You can on your video, or you want last video on. Okay, let's click. You want to on your video? You don't on?
No, I not have a good internet connection, so maybe another one can take a screenshot along with me.
I'm taking.
Yeah. So Monica, are you on laptop or mobile? Where are you?
Yeah. Now I am in old laptop.
Okay, so any other backup, if someone can take, it will be good things. So 2, 3, at least 2 backup will be good. So whoever is clicking, just we are set. So please click and let me know what's the update.
Okay, so ready? Yeah. So I'm taking the screenshot.
Ready? Yeah.
Yeah. Done.
Done, Monica? Done?
Yeah, done.
Okay, so we all will go to virtually at IIT Bombay. Just wait, let me share. Is it audible and visible? Can someone tell me quickly?
Am I audible?
It's not.
So we are only seeing the Explorer desktop.
Okay. It's not coming, right?
Audio probably was there.
Audio was there, yeah, but it was only your desktop. Yeah, now it is good.
Yeah, fine.
Okay.
Yes.
Okay, thank you.
Let's begin from the beginning. The main building. Like all other main buildings, it holds the various administrative departments of the institute along with the offices of the deans. And a very secret staff canteen. The convocation hall. You start your journey here, and one day in your black robes and holding your graduate degrees, this will be the place where you will look back and say, I wish I were a freshman again. The Students' Activity Center, or like we fondly call it, the SAT. The focal point of all cultural and sports activities in the institute. This is where hobbies become talents. It also holds the open air theatre or the OAT, which is actually wait and watch. And like every other institute, we have a library as well. With an immense supply of books covering life, the universe and everything, students come here to read and learn. Although a lot of them come here for the air conditioner as well. The Infinity Corridor. An almost endless array of departments and lecture halls, the Infi Corridor is like the backbone of the institute. Academics and research. You are, and this isn't boasting, joining the best technical college in the country. With professors and facilities surpassing your imagination, you will hardly cease to be amazed by the awesomeness of the Indian Institute of Technology, Bombay. Who says engineers can't be artistic? What sets IIT Bombay apart is the enthu for cult that you will discover here. Sing, dance, act, speak, write, paint, shoot. Do what you like the best, with the best. IIT Bombay is a pleasantly surprising treasure trove of culture that will not fail to dazzle you. You will discover skills you never knew you had, develop them to become a master at your art, and finally, culminate into a thing of beauty that will inspire generations of IITians and more. Technology. Something we can say without any point of contention we are brilliant at. After all, it is in our name. Dream a dream and learn to make it come true. And with style too. IIT Bombay will teach you how to be a proud, self-proclaimed geek with a knack for coolness. Sports. Jog, sprint, run, kick, celebrate. Race, keep racing. Observe, run up, deliver. Toss, hit. Smash the ball down the table. And he hits it over the ropes. Dive into the coolness. Dribble, look, pass, and score. Think, attack, dodge, swerve, and above all, play. Student media. So you are a student. But more importantly, you are a resident of IIT Bombay. And it's up to you to be as aware as you can be. With the readership of more than 1 million and making an impact on national media, the student media bodies help you be more than a student. You become a citizen of IIT Bombay. Mood Indigo, Asia's largest college cultural festival. Students from all across the country, performers from every corner of the world, and a carnival of concerts and celebrities. Mood Indigo is something no college student anywhere in the country wants to miss. You will witness an extravaganza of talent and fun like no other. Concerts, competitions, workshops, events like hot air ballooning and paintball, and above all, friendship and joy await you here. TechFest, a technical festival that amazes you with its brilliant competitions and showcases. TechFest will bring to you the best technical marvels of the country and the world at your doorstep. Stuff like laser tag, robo-walls, laser shows, and many more will show you how technology can be entertaining and amusing. The entrepreneurship cell. IIT Bombay is known for its glorious alumnus, but everything starts from a tiny idea. An E-cell is that incubation chamber that nurtures and gives life to your idea and helps you be a successful entrepreneur. So what do we do when we are not being awesome? Campus Hub, a hygienic and tasty assortment of popular Indian and continental dishes served at pocket money rates. Gulmohar or Gullu, a bigger restaurant and cafe area that hosts various rendezvous, be it academic or romantic. The beauty of IIT Bombay is unmatched. From the serene and wonderful lakeside to the rooftops of high-rising buildings, there is always a place to enjoy the rare natural beauty in the middle of the city. Mom's Khana and Brewberries are snack joints, providing fast food, much needed cold beverages, bakery products, and at times full meals as well. The Samir Hill. Climb it and see for yourself why this high corner of IIT Bombay deserves a mention in every IITB guidebook. Just carry water and food because you may not want to come back. For latest updates on campus news, follow us on Twitter, Facebook, and YouTube. IIT BBC. Subscribe us. Thank you.
Hello, am I audible? Hello.
Yes, you are audible.
So let's move on to next session. So Professor Aptabalam is here. Yeah. So I would like to hand over the session to Professor Aptabalam, session chair of Theoretical Condensed Matter Physics. Sir, please take it over.
Thank you, Sanjay. So we are almost towards the end of the symposium, and this is the last scientific session on theoretical condensed matter physics. In this session, we have only invited talk by Professor Baskaran, one invited talk by Professor Baskaran, and two contributory oral presentation. Although Professor Baskaran does not require an introduction as such, however, I take an opportunity to say a few words about him, specifically for the knowledge of younger community who are a key component of this symposium. So Professor Baskaran is a SERB Distinguished Fellow and a professor at the Institute of Mathematical Sciences, Chennai. He is known for various pioneering contributions to the field of condensed matter physics. To name a few are the resonating valence band theory to describe behavior of the high TC superconductors, emerging gauge fields in strongly correlated systems, etc. He received several awards such as Shanti Swarup Bhatnagar Award, ICTP prizes, etc. Today he's going to talk about the art of model building in quantum world. So with that, a very warm welcome to SYMPHY, Professor Baskaran, and the stage is all yours.
Thank you very much, Akhtar. Do you hear me?
Yes, yes.
So I thank Sanjay and all colleagues and Akhtar for a very nice introduction. Thank you for inviting me to join this wonderful webinar. I wish I am there personally to enjoy the beauty of IIT Bombay and also meet people. So let me begin my talk and share. Is my screen visible?
Yes.
Okay, wonderful. So today, in this today's meeting, I'm going to talk about art of model building in quantum world. So I have to first of all thank I'm trying to move my, So I got superannuated from math science years ago, but thanks to various organizations, including math science, who continue to support me. I had wonderful fellowship from DAE, Rajaramana Fellowship, and a distinguished SCR Distinguished Fellowship from DAE, India, DST. And since last year, I'm a distinguished professor of IIT Madras. And for the last 10 years, I'm a distinguished visiting researcher at Perimeter Institute. So I've been enjoying my career wonderfully, thanks to all these people who support my research. So I am originally from Institute of Mathematical Sciences. It's a very small research institute. Many of you know about it. It has about 60 faculty, 100 PhD students, we focus on theoretical physics, pure mathematics, and computer science. Now, many students will know about it, how to enter, and we have an extensive visitors program, from young people to senior people. Please have a look at our website. You may find some resonance with some people. You're most welcome to visit. Now, since the last 1 year, I am associated with this great Indian Institute of Technology like IIT Bombay. There are no leopards here in IIT Madras, but there are deers and of course monkeys and wonderful trees, and it's a mini forest. And often when I go to my office, monkeys greet me and I start talking to them theoretical physics, they run away. Then I spent like half of my time, like 4 or 5 months every year at Perimeter Institute of Theoretical Physics at Waterloo. It's a remarkable institute which focuses on quantum science, theoretical physics, quantum gravity, quantum matter, and so on. They have a 1-year program called Perimeter Scholars International, which young people may like to look at. Now, more interestingly, this institute is very special because it was started by someone who started BlackBerry cell phone company, Mike Lazaridis. He had a fascination for theoretical physics. He says that he wanted to become a theoretical physicist, but he could only become a billionaire. Okay. So at some point he started funding. He gave $100 million as an endowment. And that's how Perimeter Institute of Theoretical Physics started, and it's growing in stature and so on. So far, he has given about $400 million, and we have many examples of respect by an individual for theoretical physics and science as something that helps transform society. So there are many international examples, our own local examples: Tata, Saragappas, Birla, Mehta, A.C. Muttaya, Girish Gopalakrishnan, Infosys Group, Shanmugam Group, Shastra, Shivanadar, Azim Premji, and so on. Now, I'm saying this because it's for you, young people, some of you who are listening to me, to tell your rich uncle or billionaire that science is worth supporting, because in the long run, it helps society. Now, in fact, you can trace back to the state that we are now, most of the things to science. Of course, literature, art are important, but science has played a very important role in the last few hundred years. So please remember this. And of course, I know that IIT alumni are very, very generous. They have been supporting science and technology in IIT. And it's nice to extend it outside also. Okay. So this is what I plan to do. I will start about model building in many particle Hilbert space, and how do we navigate Hilbert space with the help of models, and then model begets model, and the random walk. This will be it's a very general talk. So, I have this models to follow. Let me start with Chanchal Majumdar and Deepan Ghosh. So your professor from IIT Madras, IIT Mumbai, they wrote a wonderful model called Majumdar Ghosh model. I described it in some detail. And Chanchal Majumdar student Shastri generalized this model, and there's a very famous model called Shastri Sutherland model, which is even now flowering. Many new things are being discovered based on that model analysis in real systems and Haldane Shastri model. And lately, in the last few years, this wonderful model by Sachdev, A. and Kitaev is really making news. No other model has drawn so much attention in the history of physics. It's a model of, it all started in a humble way to describe a quantum spin liquid in a random system. Then Kitaev noticed some deep issue there, deep physics there. Now it is really a great thing, and it's even throwing light into the dark black holes, how thermalization takes place in quantum scrambling and so on. So these are all our friends. They're really models to follow. So nature is quantum mechanical, but quantum mechanics is shy and most often hides. So experimentalists work hard and bring out non-trivial quantum properties from old and new materials and continue to provide challenges to theories. And if you take materials, there are quantum liquids like helium-3 or helium-4, super-helium-4, Mott insulators. You already heard about some of these things, topological insulators, the past talks, and the lower dimensional materials, higher dimensional materials. And there is a wonderful variety: quantum dots, semiconductor devices, nanoparticles, nano mesoscopic semiconductors. And lately, I'm sure you have heard about so-called synthetic quantum matter. You can create desired solid-state situations by using lasers and creating standing waves and creating some periodic potential and trapping cold atoms using some very sophisticated techniques. They are called optical lattices. And you can mimic or you can simulate your desired models. It could be quantum effect model or Hubbard model. And Josephson lattices are being built, like in Mumbai, you have Josephson qubits at IIT, at TAFR, and I'm sure in IIT Bombay there are people working on many quantum bits based on superconductors and cavity electrodynamics, strongly interacting photons. And so they are all synthetic quantum matter. So these are all new challenges and new avenues. Now the basic ingredients in the world of quantum matter that we are worried about is our electrons, nuclei, and spins. Basically, Coulomb forces, electromagnetism, and spin orbit coupling. So these combinations can do wonders. Now, if you look at the predictions of these models, for example, there is a Fermi liquid model by Landau and others. You have quasi-particles, electron and hole like quasi-particles, composite fermion, thanks to Jainendra Jain, that came in quantum Columbine. Majorana fermion, you heard about it from Anil, Kumar in the last talk. Parafermions, fractons, phonon, magnon, resonance, phazon, pions, spinon, holon, and even objects which have very peculiar exchange statistics called anions and quantum number fractionization. It's a wonderful world that all has its genesis in simple-looking handleable models. So now the issue that we are going to face is how these artists or the scientists build these models, what guides them. Now, since we are in a quantum world, the Hilbert space is big, too big. Like even if you take a harmonic oscillator, the Hilbert space is infinite dimensional. Of course, we worry about ground state and pure theory state. Similarly, if you take hydrogen atom, the Hilbert space is infinite. But you worry about 1s state, 2s state, 2p, and so on. So it is very important to find the right corner or sculpt the Hilbert space and identify the relevant corners and proceed further. So reduced Hilbert space is also big. So finding the relevant low energy corners of the reduced Hilbert space is also an art, even more than a science. So scientific life of a quantum matter scientist is a voyage in Hilbert space. We often get lost in the vast Hilbert space or land in wrong places. So experiments and modeling come to our rescue. Every good model opens a door to a new world. Now, let's look at historically how these models have guided us to our present status and present understanding of nature to some extent. For example, nearly 100 years ago, soon after Planck's modeling of distribution of blackbody radiation, Bohr said that if you want to explain the spectral lines, you have to have a model which is simple enough, which says that basically the Kepler orbits are chosen, they are quantized, so they satisfy the conditions. So those are all allowed orbits or stationary states. So that simple looking model was the beginning of quantum physics. Then before Schrödinger equation came, great Einstein said that if I want to explain specific heat of solid, which deviates from Dulong-Petit's classical law at low temperature, I have to invoke presence of some quantum harmonic oscillator. That is, each atom in a solid is sitting in a self-consistent potential harmonic well. So he started modern solid-state physics. It's called Einstein model of solid. Then lattice dynamics, phonons. Then came Sommerfeld. He said, if you build atoms with the electrons filling up 1s, 2s, and so on, what do we do with the electrons in a metal like copper? He says, let us fill up plane wave states, and then automatically Fermi C came. So Bloch's theorem, Brillouin zone, band structure, band gaps, Fermi surfaces, Landau model of quasi-particles. Many models just fell out. Now Einstein's free Bose gas model, inspired by Bose distribution, and then Bose condensation. Then London theory of superfluidity of helium-4, applying Bose-Einstein condensation. And then Heisenberg's model of exchange interactions, the beginning of quantum magnetism. Then, of course, beyond condensed matter, in nuclear physics, you have shell model, interacting boson model, Salam-Weinberg model, to which, for example, my former director, George Sudarshan, made a very important contribution called V minus A theory. So we have had great model builders, and models are really great guidance because it's a big forest. So you should not lose the big forest for all the trees. So how did artists, Bohr, Einstein, Bose, Debye, Sommerfeld, Heisenberg, and all these people build models? Most of them analyzed and contemplated on experimental results. Use their imagination to build simple but non-trivial mathematical models. Models simplify bewildering variety of complex issues. Models provide way of dealing with science of complexity. Just to give you one example, it's a very popular model called the Hubbard model in the context of quantum strongly correlated system. It was discovered by several people independently, Hubbard, Kanamori, Gutzwiller, Anderson, in the context of ferromagnetism, water insulator, antiferromagnetic, spin liquid, high temperature superconductors, and so on. I will come to this later. Now, it's very important to recognize the work done by Phil Anderson, who is no more, unfortunately. He passed away early this year. He's a model builder par excellence. In fact, he gave a new direction to quantum matter physics. In fact, separately, I have given a couple of talks about his contribution. So it's important to recall him as somebody who gave us several models. Like, I have shown here in his career, running over about 70 years of intense scientific life, Anderson gave so many models. One of the first models, which is soon after his PhD, was something called Anderson Tower. So he wanted to understand spontaneous symmetry breaking that takes place in a quantum antiferromagnet, which is nominally a singlet ground state. How does antiferromagnetic order emerge out of it? So we built something called quantum rotor, and there is a consequence, Anderson Tower. Then super exchange, double exchange. Then Anderson's model of motional narrowing, his PhD work. Mass generation of elementary particles, Anderson-Higgs model, Anderson localization model, local moment, and Anderson localization together got him Nobel Prize. Edwards Anderson model, spin ice model, and RBB theory model, gate theory model, variety of model. So what is the secret of this artist? So I want to recollect a personal experience. Anderson's 50 years of contribution was being celebrated on Aspen, a great center for physics in Colorado, near Colorado. So as an old collaborator, I also spoke. I told the audience that I would reveal the secret of Anderson's success. So Anderson, who was in the front row, raised an eyebrow. I said that Anderson kept looking at body of experimental results and communed with nature till he found the right model. This everybody understood, knew that, because Anderson is very fond of trying to understand experimental results and keep good knowledge of phenomenology. My next sentence surprised the audience and got a smile from Anderson. I said that while everyone would try to solve his or her model using mathematical methods, analysis, approximations, computers, Anderson would go back to experimental results. Experimental results guided him to guess the right solution with the model via physics-driven mathematical analysis. This may sound strange to you. In fact, Anderson's great success in many of the fields that he opened up is due to this physics-driven mathematical analysis. It's not a pure mathematical analysis looking for a small parameter. You look at phenomena, so you do some analysis, you do some approximation, which is very non-perturbative and gives you new insight. So that's where experiments come. Now I will talk about models. That's the home ground. There is a famous model called the Majumdar cone model. Again, it came from lots of experimental results were available in those days on dilute non-magnetic alloys and magnetic alloys. And Kohn and Majumdar wanted to build a simple and soluble model to gain some insights into this very complex phenomena. Now, from there, many things came: Friedel's theorem, phase shift analysis, Anderson model, local moment formation, and so on. Now, what was interesting was, this is a paper of Kohn and Majumdar. Anderson looked at this paper and he's like standing on the shoulders of giant. He said, it's very true. However, if you look at the same phenomena in the presence of a Fermi sea, something more is going to happen. So that was the beginning of something called Anderson's orthogonality catastrophe. So it was built on Kohn-Majumdar model, Kohn-Majumdar model, and in the context of a Fermi sea, which has very soft excitations around the Fermi surface. So which means that if you take a Fermi sea and then you create local perturbation, the entire Fermi sea will adjust and become orthogonal. This is called orthogonal catastrophe. It holds the secret to X-ray singularity, Anderson impurity model, Kondo effect, heavy fermions, hidden fermi theory of cuprates, and a variety of things. So you see, I said model begets model. Kohn and Majumdar wrote a model, and then Anderson made use of it and opened a new direction altogether. Now let's come to Majumdar-Ghosh model. It's very interesting. At that time, in those days, several decades ago, Bethe solved Heisenberg's spin chain exactly. It's an exact solution using Bethe ansatz, what is called Bethe. It had very peculiar behavior. People didn't understand it physically, but the mathematics was very clear. Conyers-Herring, whom I had the honor to meet and spend a few months together at Stanford many years ago, Conyers said that these models is more to the world of thought. Experimental compulsions tells you that you should go beyond issue to symmetry. You should go beyond nearest neighbor interactions and so on. So this was the genesis of Majumdar-Ghosh model. There was an experimental compulsion being told by people like Conyers-Herring that you have to go beyond nearest neighbor Heisenberg model. What did Majumdar-Ghosh do? I will tell you how they arrived at it later. What they did was they went one step beyond and constructed a model which is just nearest and next nearest neighbor coupling. And the nearest and next nearest neighbor coupling has a particular ratio, namely half. And lo and behold, this model became exactly solvable. The ground state can be explicitly written down. And at that time, nobody knew how much excited state, interesting excited states it has. But already it became very famous. And then started, in some sense, it was a forerunner to the notion of quantum number fractionization. That was made very popular and worked out very detailed by Schrieffer-Higgen model. That is, they studied polyacetylene, which you can view it as some kind of Majumdar-Ghosh model in which there are singlets which are arranged in a periodic fashion. So suppose you take a singlet and create a triplet by some means, then the triplets will separate into two spin half. As you see in the picture, one spin half here, they are called soliton or spin-on. So this is what will happen. In fact, that's what happens in Majumdar-Ghosh model also, as shown by Sastry and Sutherland later. So a quantum number fractionization idea is hidden, this very simple looking model, which came out in course of time. So it was a kind of forerunner to those kind of issues. Now, Majumdar and Ghosh, they did not look at experimentals. Of course, they listened to Conyers-Herring and wanted to generalize nearest Heisenberg chain model. But they did something very interesting. They performed extensive exact diagonalization of finite size spin chains and related analytical analysis. And in the process, they discovered Majumdar-Ghosh was Hamiltonian and the exact valence bond ground state. So it was not a wild guess. They struggled hard. Instead of doing experiments, they did numerical experiments. So here I want to recall a breakfast meeting with my old friend Klaus Schluten. He's a very distinguished quantum biologist who was at Urbana-Champaign. He started as a quantum strongly correlated system person. So we were in a workshop on quantum processes in biology. And we were having breakfast. He told me, computations and numerical analysis are like computer microscopes. Data they generate the data they generate give us rare and precious visions of what goes on inside, which you may not be able to do with standard experiments. Because with great effort, you can take an STM tip and then look at the surface. But if you want to go 1 nanometer deep, you cannot go. You have to do some art phase and so on. Whereas a computer can do wonderful things. So some of the most sophisticated and real experiments are not capable of giving us clues as to the length and time scales. So use these visions to build mathematical models. This was Klaus Schluten's idea that we should use computers to generate data and don't use them as numbers. Use them as something that gives you a view of the inner world and use them to build models. In fact, there are many, many successful examples. I can give any number of this. Now, this is very important in the modern context because Now the world is full of machine learning, deep learning algorithms, and so on. So, we have machine learning, deep learning, so neural networks, sorry for this typo. So we solve problems, very great optimization problems we're able to solve in time, and we are able to analyze Monte Carlo data and extract critical exponents in statistical mechanical models. Now, is that sufficient? Now, it's important to remember, after data mining machines supply us a wealth of new insights and relevant data. It is for us to build new models or teach machines to build models. So a lot of typos are there. Let me give you an example. When machine learning became very popular, I was asking a question myself. Can machine discover the laws of quantum mechanics? Can machines discover Schrodinger equations? I spent several weeks thinking about it and playing with it, and then I forgot about it. Then 2 years ago, I listened to a talk at Perimeter Institute by a young man. I'm very extremely sorry I forgot that reference here. He is an assistant professor at San Diego. What he has done is, he has taught a machine to analyze data from Bose-Einstein condensation of pattern of cold atoms. As you know, that suppose you have a random potential, the ground state wave function will be some kind of random, it will have a random shape, it may be localized, and if you have bosons, all bosons will condense to that state. So what he did was, he asked the machine to analyze this for various input data and find out what is the origin. And lo and behold, he had machine told him there are 4 possibilities, and the 4th one is Schrodinger equation with the right coefficient. So in some sense, a careful analysis of the data from machine learning, and he calls it as contemplative machines. In fact, if you give that phrase, contemplating machine, you will get the, if you do Google, you'll get the reference. I'm sorry, I should have put the reference. So it's not only you solve problems using machines, it is also possible to discover laws. So my query 6 years ago, when machine learning was becoming popular in entering physics, was that can it discover quantum physics? Now it looks as if given enough data, and if you train it properly, and if you make it contemplate on its own, it can teach you new regularities and new laws. So this is something that I wanted to tell young people, that here there is new opportunity to build models using machine learning. It's not that, in fact, my memory goes back to 91 or 96. I was listening to a talk by Terry Sanowski, a very distinguished neurobiologist now at San Diego. He started as a gravitational theorist. He gave a talk about what is called Boltzmann machine. So he demonstrated in the colloquium a machine which has been trained to identify grammatical error. So you show a text, so machine will tell you if the grammar is correct or not, if it is grammatically correct and what is the mistake. So I asked him at the end of the colloquium, so Terry, you say that the machine has learned. Now, can you go to the circuit of the machine that you have, statistically reorganized, you change it? So the circuit knows the grammar of English. So can you unearth, or can you write down the grammar of English? He laughed. He said, that's $1 million question. So another simple way of saying is that now you have talked about Google car. So the car has been trained to run extremely well, no accidents. Now, in principle, inside the car, the rules of the game, like keep left in India, keep right in the US, and various nuances are there. How do you get it out of the circuit? So that's a big challenge. That's like model building. So this also, lots of things are going on in machine learning. So machine learning just don't produce numbers alone. They don't solve optimization problem. They also give you an opportunity to discover new laws. Okay. So now let me go to the, now, as I told you, Majumdar-Ghosh model, it was a depth of singlet physics in many electron isolate spin system. Then, it predates Anderson's RBB theory. It's very interesting. Anderson looked at Pauling's RBB theory and said that it is applicable to Mott insulators, and wrote this very famous paper in 1973. And Majumdar-Ghosh model is slightly earlier. In fact, Majumdar-Ghosh model is also applicable to a Mott insulator, but except that because of the way the interactions are, there is no valence bond resonance, but it's a frozen valence bond. So it predates Anderson's RBB theory. And so translation symmetry is broken, but it still is a quantum spin liquid in the sense spin-spin correlation function is short range and so on. Now, you can take this model and then analyze it further, like done by my friend Amshesha, Zoltan Susan, Manoranjan, Calcutta, all these friends. You find wonderful phases as you deviate away from Majumdar-Ghosh point, all kinds of chiral states and so on. So these models open a door for you, some corners of the Hilbert space around which there is richness. There's a variety of beautiful things going on. Now, I said at the beginning, model begets model. So Shastri was a colleague of Deepan Ghosh and a student of Majumdar. And Shastri and Sutherland wrote a model which is a beautiful generalization of Majumdar-Ghosh model to 2 dimensions. So you see a square lattice here. So you have nearest neighbor spin-spin coupling on this lattice. And then this dashed lines corresponds to next nearest neighbor coupling, which has half the strength or some 1/4 of the strength. Then it turns out you can write the entire Hamiltonian as sum of squares of 3 spins. And then you can get an exact ground state. And when Shastri did this, once I remember I was joking with Shastri, so what? It's just a model. You know, as a friend, Shastri is my old friend. But nature is always kind to people who do serious work with models. That's what I have learned now. Because Shastri and Sutherland, when they wrote the model, they didn't have any system in mind. Then, thanks to Japanese friends, they discovered a borate, strontium copper borate, which 99% follows Shastri-Sutherland model. Okay. Now, okay, that's fine. So it has this ground shape. But what is really amazing is even which Shastri and Sutherland did not anticipate this. If you take this model and apply a magnetic field, strong magnetic field, it's not exactly solved. You can solve it numerically or you can do experiments. What you find is so-called magnetization plateau. If you take a standard antiferromagnet and apply a magnetic field, the sublattices will get polarized, and then at the end, strong field, all the spins will point along the field direction. So it will be uniform increase in magnetization, and then it will become flat. But here on the way, before it gets completely saturated, there are so-called magnetization plateau. Now, if you look deeply into magnetization plateau, they have beautiful connection to quantum spin liquid or RVB theory and diffraction of quantum law. So this is the power of the model, because Shastri and Sutherland, Majumdar and Ghosh took you to one corner of the Hilbert space, and that was a beautiful basis. Sit there and go around, you find wonderful world, new world. So who would have expected that Shastri-Sutherland model hides or is connected to RVB state in fractional quantum Hall-like state. So that's why I call it. And in our own country, many friends have worked on this, like Indrani and Mitra. They have generalized Majumdar-Ghosh model. They have frustrated spin-half model in 2 dimensions with known ground state, Bose-Mitra model. And Brijesh Kumar was a student of Brijesh was a student of Sriram Shastri at IISc Bangalore. So he's a professor at JNU. He has built beautiful models, more exotic, based on this kind of ideas. And then he has a very nice review article about someone at Sahayan and his friends have analyzed a model called PEV model, and they find Majumdar-Ghosh and other versions of that. So, model begets model and takes you to very rich corners which you may not have anticipated before. Okay. Now, this is, as I said, Majumdar-Ghosh model had a frozen valence bond. Then there are valence bonds. You have liquid of valence bonds, which is a resonating valence bond state, which was started by Pauling and then Anderson, and it was revived in the context of cuprates by Anderson. And I was fortunate to be with him, and we joined the game. And my friend who is no more, Patrick Fazekas, he was holding on to it after Anderson's work and did very beautiful work. Okay. Now, it's interesting. See, this J1, J2 model, okay, has a very beautiful ground state. So what? People may ask. Now, it's interesting that people have used it, like in this paper, which is already 2012, Stephen Haas and Chancellor, they have taken this model which is handleable, and sit at the Majumdar-Ghosh point or move slightly around it, and then use it as a quantum data bus. That is, these days you want to do teleportation in the context of quantum technology and quantum computing. So you want to transfer objects from one end to another, quantum state. So these people said that this simple looking model can be used. Now, similarly, Ms. Dongsheng Wang just wrote a paper this year, classes of topological qubits from low dimensional quantum spin systems. He refers to Majumdar-Ghosh model and uses it. So who would have thought that when the Majumdar-Ghosh model has had its genesis, that it will become useful for quantum computing? It's amazing. That's why I think it's very important for young people, whenever you get a chance, try to build a model. Out of 10 models, maybe one will be very good. So it's worth attempting to build your own model. So it's like sculpting by a sculptor. You take many stones, may break many of them. Suddenly you will find a beautiful shape. Just to my colleagues at IIT Madras, they have studied very fascinating entanglement structure. See, for example, when Majumdar-Ghosh model was proposed, the entanglement idea was known because singlet there is, but now entanglement idea has become very powerful because all many-body states, quantum matter, has characterized by non-trivial entanglement structure. So Arul Lakshminarayanan and his student Chandra and Rama Karthik at IIT Madras, they have studied this Majumdar-Ghosh model and found out that there is a dimerization across the dimerization transition, or as you go through Majumdar-Ghosh point, very beautiful entanglement transition take place. So this is something amazing. Similarly, now this is something very fascinating. So Majumdar and Ghosh gave you a ground state. Now, what about the spectrum? Because it has a 2 to the power of n, if n is the number of 2 to the power n of states. So normally you will say, okay, it's featureless, maybe because there is no phase transition. But lately there are very fascinating phenomena called quantum scars. That is, if you look at the many-body eigenstates and just look at the density of many-body eigenstates, they are related to thermodynamic quantities via microcanonical ensemble theory. What you find is, while most of the spectrum looks thermal, there are a subset of them which is non-thermal. They are called quantum scars. In fact, they have been seen experimentally. And nobody realized that it could be sitting inside Majumdar-Ghosh's model in the spectrum. What are these quantum scars? They are very fascinating because according to hypothesis called eigenstate thermalization hypothesis, if you take a typical state from this many-body collection of many-body eigenstates, you take a typical state, locally it will look like a thermal state. That's called eigenstate thermalization hypothesis with probability 1. Now these scar states just defy eigenstate thermalization hypothesis and they don't thermalize at all. And they are there buried. And what is remarkable is this bright student Sanjay Moudgalia from IIT Kanpur, I have met him as a student at IIT Kanpur, later at Princeton. He and Birnavig and Rena and Rachel, they have found out that in non-integrable model, because Majumdar-Ghosh model is not integrable, but still you can find out some exact excited spectrum and they correspond to so-called quantum scars. So it's extremely fascinating that a simple model which was built based on experimental compulsion has profound consequences in course of time. I think this can be told of any model, starting from Bohr-Saturn model and that models that you come across. Finally, we are all finite human beings. We have limited imagination. We have to, like Newton, when he wanted to formalize Kepler's law and celestial motions, he said sun is a point and the earth is a point. It's a good approximation. So don't worry about the radius of the sun, just worry about the mass. So when you build models, you really focus on the relevant things and throw away the irrelevant things. And in fact, these days there are formal ways of getting models through enormous group analysis, teaching the fixed points and so on. So I think I have just crossed my time limit. So thank you for your attention and I'm very happy to answer questions. Over to you, Aftab.
Thank you for the very nice overview and the motivating talk on theoretical modeling. So the session is open for questions. If there are any questions.
I'm sorry if I was very fast or unclear.
Sanjay, on the YouTube side. Okay, yeah, Shanky, please go ahead.
Professor Baskaran, I have a question regarding this this thermalization.
Yeah,
so can you explain this eigenstate thermalization? So what are the conditions actually? From the figure, it was not very clear what was that actual. From the figure, there are some states which are on the curve and some states which are not on the curve. So are the ones which you are talking about? So that
yeah, I will explain completely. I'm just going back to my transparency, and yeah. So see this figure. Do you see the figure now?
Yeah, I can see. Yes, please.
So this simply counts the number of eigenstates in a small energy interval as a function of total energy of the system, or as a function of energy per particle. So and this is related to so-called entropy, because that's the picture in microcanonical ensemble. Okay. Now, what microcanonical ensemble tells is, it says that just count the number of eigenstates in a small energy interval, and that is sufficient to define you thermodynamic quantities, because you get entropy. From that, you can get internal energy by taking then you can define temperature and so on. Now, eigenstate thermalization hypothesis goes one step beyond. It says that you take a typical eigenstate, close your eyes and pick up one many-body eigenstate, and then look at it locally in the sense of integrating over degrees of freedom outside a small local region. And then the density matrix of this local region will look like a Boltzmann factor with a corresponding temperature. In fact, there are very beautiful numerical analysis to this effect. You can, I can give you a reference. That is, you solve a problem of, for example, a Heisenberg chain or a Hubbard model 10 sites, and then get the spectrum, and then pick up one exact eigenstate and calculate what is called entanglement of entropy. It coincides with thermodynamic entropy. So quantum entanglement is closely related to statistical entropy. Okay, so this is the folklore about eigenstate thermalization hypothesis. But in this picture, you see there are lines and dots which are hanging, right?
Yes.
So if you by mistake picked up that eigenstate and you do you find completely different behavior of entanglement entropy. The entropy is small. So they don't give you, they don't follow eigenstate thermalization hypothesis. They are called quantum scars. Very interestingly, they have seen it in Rydberg atom, in the cold atom experiments. So they are in some sense scars, deviation from the old ergodicity hypothesis in many-body theory.
Yeah, okay, so can I just can I ask a more specific question? So if I remember right, the eigenstate thermalization also relates saying that all the conserved quantities, right, of the system.
No, no,
so
no.
If
no.
I have some of them actually the constants are related to the conserved quantities, right?
Okay, very good. So, for example, if the system is has a lot of conservation laws, it satisfies.
Correct.
You have to define so-called generalized Boltzmann ensemble, and then you have to sharpen the eigenstate. So typically, eigenstate thermalization hypothesis works very well when the system is non-integrable.
Right.
So if the system is integrable, there are many conserved quantities. Then you'll have to define sub Boltzmann ensemble and do it. Here, what is remarkable is Majumdar-Ghosh model is not integrable in the technical sense. But in spite of that, there are some pseudo-conserved quantities which bring out these scar states.
Ah, okay, fine. Okay.
It brings out the scar state.
Fine. I understood. Okay.
Okay. Are there any further questions? comments?
See, my personal experience is whenever I give a talk, our Indian students typically don't ask questions. But once I come out of the room, lecture room, they crowd me and they start asking questions. So now I should find a way of coming to your lecture hall or to their house.
Definitely, we'll be delighted to invite you.
After one comment I have.
Yes, please.
Professor Baskaran, Professor Ghosh was here. He got disconnected.
Oh my God, I'm very happy. I like to say hello to him.
He's been here throughout.
Oh, wonderful, wonderful. So I haven't seen him for ages. We are old friends.
Sanjay, can you connect him back, Professor Ghosh? He got disconnected just now.
He's here. He is here.
No, he's already there.
Oh, he's back.
He's here, but he's muted. I think he's muted.
Okay, I'll tell him.
Yeah, you're muted, Professor Ghosh.
Got disconnected. That I saw. I will tell you.
So hello, Deepan.
Here, he is here.
Hi. Great to see you, Professor Baskaran. And it was
Great, yeah.
a
long time.
Such a long time, yeah, very long time. And I was just mentioning to Suresh that the model you talked about is exactly 50 years old. Okay?
Oh, I see. Very nice, very nice.
Yeah.
Okay.
And so thank you very much for reminding me the old days, and
Congratulations.
particularly TIFR.
Year celebration.
Yeah.
It's really
Thank you
deserved.
very much.
Very
Thanks
nice.
a lot. I really enjoyed it. Thanks a lot. Great to hear.
So where are you talking from, Deepan? Are you at Bombay?
I'm talking not far from IIT. I live very close to IIT in an IIT housing complex built by retired people.
Okay.
So, yeah. So this is in a place popularly known as Hiranandani Gardens.
Okay. See, each time I have visited Bombay, I have always enjoyed it. It's a fascinating place. Contrast. You go to Zoo Beach and you go to TIFR, which looks different. You go to IIT Bombay, it's different. And
Absolutely. Juhu Beach looks much more different now because there are no Bhelpuri walas there. The place is totally cleaned up.
Okay.
Where are you speaking from? It said perimeter is...
Actually, I am speaking from Madurai. See,
Oh, you
I
are in Madurai.
I live in Madras, but I have come to Madurai to see my mother. So I am speaking from Madurai. And incidentally, I also left Madurai for my PhD exactly 50 years ago.
Oh, great.
I joined my PhD at IISC in 1970.
You were in Palkalai Nagar or you were in American College?
American College. So I did my MSc in American College. Yeah.
Right.
A great college.
Great. Yeah. Beautiful building also, right?
All
So
right.
very nice greetings. Yeah.
If there are no further questions, moving on. Let's join me to thank Professor Baskaran again for joining us.
They can just join for the photo session, both Professor Ghosh and Professor Baskaran.
Yes.
Okay, what do we do?
Please
I just say, I haven't had time to make up.
We have a few things remaining, then they will go for the photo session. If you don't mind, please stay back.
So I stay there?
Yeah, please.
Yeah, so I have sent some messages privately, both of you, I think, saw that message.
Okay, if you can be there, that would be great. Let's move on. The next talk in this session is by Jiban Kangsabnik, and he's going to talk about electron-phonon interaction in late free double perovskite halide. Jiban?
Hi, can you hear me?
Yeah, please share the slide.
Yes, yeah. Can you look at my screen now? Slides?
Yes. Go ahead.
And am I audible?
Yes, yes.
Yeah, thank you very much. Thank you very much for I would like to thank the organizers for letting me talk here. I'm Jiban Kangsabnik, a PhD student from Department of Physics, IIT Bombay. And I would really like to congratulate all the organizers for such a beautiful online SYMPHY, and I feel really proud to be a part of the department here. And so today I'm going to talk about lattice dynamics and electron-phonon interactions in late-free cesium, silver, indium, bismuth chloride. So the outline of my talk will be, I'll give some introduction on halide double perovskites. Then I will briefly talk about phonons, Raman spectra, and Froelich interaction. Then I will mainly talk about estimation of carrier lattice coupling via Froelich interaction in cesium, silver, indium bismuth chloride, and mainly we will touch upon the mobility limit. And then, basically the topic consists of lattice dynamics, phonons, Raman active modes, and then electronic structure, transport in Bi alloyed cesium, silver, indium chloride. Okay. So first, this is a perovskite structure we will be mainly talking about. So this is A atom is a green atom, if you see my cursor. So and then there is A atom is a green color, and so B is of the violet color. So this is in the octahedra, and then there is brown colored spheres, which are the halide anions. So these B and X form an octahedra, and A remains in the between the octahedral cages. Now, if we go to double perovskite, actually the stoichiometry doubles it up. So it's like A2, B2, X6. So that means that is like A2, B2, X6. Then, but here we replace one B with a B dash. It's a different element. So then it looks like a alternate octahedral between violet and golden colored. So if you can see the structure, this is a double perovskite structure. So next, I will mainly talk about phonons. So phonons are nothing but like quantization of vibrational modes in the compounds on a molecule. Depending on the nature of the vibrational modes, they can be classified into acoustic and optical phonons. Now, so this is a schematic diagram of 1D channel. So 1D is spring. So the acoustic mode where the atoms, which are red in color, so moves in the sync actually. So these are called, then the vibrational mode will be called an acoustic mode. Then for the optical modes, the motions will be like this. So in the opposite direction or something other direction. So these will be called an optical phonons. They are now depending on the direction of motion, then both optical and acoustic and optical phonons can be longitudinal or transverse. Now lattice dynamics. So we will be talking about Raman spectroscopy. So the basic principle of Raman spectroscopy is interaction of light with vibrational mode. So you just illuminate a material with a laser, and then you see what are the changes and the related interaction. And why it is so efficient or something. So I will say that this is a reliable probe to explore the structural fingerprint of a material. So to see if there is any phase change depending on the environment or so. So if you can use Raman spectroscopy. Now to give you a little bit of physics, so the Raman active mode for a compound will be basically a rotational or vibrational mode of motion for a molecule, where the changes in the polarizability of the molecule, where it will change the polarizability of the molecule periodically with time. So how it will do? So I'll just show you a little bit of video I took from YouTube actually. So this is a molecule which is has a symmetry, symmetry I think. So this is a symmetrical stretching of the molecule. So if you see that there is no so this is the polarizability between the anions are changing. So this will be a Raman active mode. But the other, which is asymmetrical stretching, the overall polarizability of the system will not change. So that means this will be Raman inactive. The same thing will happen with the in-plane bending or out-of-plane bending motions. So the overall polarizability will not change. So these will not be Raman active. So this only the symmetrical stretching mode for this molecule will be Raman active. Next, I will go to a little bit of polarons, which will be main topic of discussion in this talk. So in a dielectric crystal, so constituent atoms will shift when to effectively screen the charge of an electron roaming into the crystal. So this is some simple schematic diagram. So you see the electronic wave function is moving, and then according to screen the charges, these atoms are vibrating towards that. So and in that way, they will also create a electric field between those, and that interaction will give you some scattering mechanism and limit the mobility. So in case of polar semiconductors, such as halide perovskite, which we will be talking about, the interaction of carriers with this macroscopic electric field generated by those is known as Froelich interaction, named upon the Professor Froelich. And there is a measurement coefficient which is Froelich constant. That depends on the static dielectric constant, then the high frequency dielectric constant, and then an effective longitudinal optical phonon frequency, and there is effective mass and etc. So which can be measured from first principle simulation and also something from experimentally also. But we will be talking about from simulation point of view. So now depending on the value of the alpha, the Froelich interaction strength varies. Now going to the, so I'll just give you the introduction of the problem. So basically halide perovskites have a very high tunability and they are promising for LEDs. Now for LED to be a good LED, so you need to have a good photoluminescence quantum yield. This material is one of the double perovskite, which is non-toxic, and this has a direct band gap, but the direct band gap is optically forbidden. So that means that photoluminescence quantum efficiency will be low. Now, what people did actually, in this class of materials, actually, what you need to keep in mind that the carrier lattice interaction plays a major role in the various optoelectronic properties, and frolic interaction remains the dominant scattering mechanism for this class of materials. Now, in the next slide, I'll talk about the problem statement. So this is in the pure lattice, we alloyed some bismuth actually into it. So this will look like this. If you see that there is a black octahedrous into the replacing some of the golden octahedrous. So that means some alloying going into the IN place, some BI. And that what happens is whenever BI goes into that IN place, the band gap remains direct, but the transition is now optically allowed. That means that a substantial increase in PLQI. Now, what we will be studying in this study or presentation, so that is we are trying to understand is effect. What will be the effect on lattice dynamics if we substitute BI into this material, and then what will be the effect on electronic structure and related transport, but according to it. So now in this case, this is one picture, actually experimental picture done by our collaborators Devji. So from here I will only show this picture, which is, if you see my cursor, which is a picture. So it shows that the Raman active modes in the alloyed materials and the pure compounds. So if you see, there is one T2G mode, one EG mode, one A1G mode. These are actually depending on group theoretical symmetry. So T2G is triply degenerate also, yeah. So depending on the symmetry. And there was another, actually this spectra is from 100 to 400. So there was another mode T2G, which we could not show here, but there was two T2G modes, one EG mode and one A1G mode. Now, by symmetry and group theory, what we try to understand is how these modes are formed. What will be the main molecular vibrations or atomic vibration we would like to see. And another thing I would like to point from here, if you see that when BI and IN has a lot of very big mass difference, but the Raman active frequencies are not changing that much because these are phonons. So depending on the mass, it should change, but it is not changing. So these two reasons we would like to find. We did some simulations, and here I would like to show the Raman active modes actually. So we had two T2G mode, one EG mode and one A1G mode. So the first T2G mode actually look like this. So if you see the video, so the CS atom actually only moves. So this is a CS translational motion. Now to the next mode, another T2G mode, it's a high frequency one. So that actually for that octahedral motion. If you see that breathing motion, yeah. So to the next, there was an EG mode, which is actually for octahedral stretching. So it's like that stretching part, and there was another A1G mode, which is the highest frequency one, and that is like a different kind of octahedral stretching. So these are the four Raman active modes for this compound and the alloyed compound also. The similar thing happens. Now, what happens then? Next, we try to see the bond length of these octahedras and see that the strain on the AgCl6 octahedra remains higher than the others. So what that means that when either you dope or not, but the main intense peaks or the Raman spectrum comes from the AgCl6 octahedra. So that does mean that the Raman spectrum will remain same, because whenever we are substituting BI into IN, but we are not changing the AgIN. So that was the reason behind that. And so there will be now next we will proceed to the electronic structure part. So the left one, A, is actually the electronic structure for the pure CS2 AgIN Cl6, which has a direct band gap, if you see, but the below this thing is actually can be seen as an optical transition probability. Now if you see that in that point it is 0 actually, so the optical transition is not allowed. And also due to the d orbital contribution, the valence band maxima is pretty flat. Now whenever we do some 25% BI allowing, if you see that the direct band gap remains direct, but the band gap is not allowed.
You have 2 more minutes.
Yeah, and then you see that due to the S contribution part, the band gap, the valence band maxima becomes dispersive. And why this? So you see that there is BIS contribution. So now as the BIS orbitals are much less localized than the IND orbitals, so the valence bands will be much more dispersive. And that means that we will get reduced effective mass. Now for this, I will talk about lastly about the frolic interaction part. The end compound. So first thing we need to keep in mind that the end compounds CS2Ag, INCL6 and BICL6 are show p-type majority carriers in experiment. So we will be mainly discussing about the whole mobility here. So now in the next I will show some tables. So we will just follow with me. I will just show 1-2 data. So this is a pure compound which has a whole effective mass of 1.47. But whenever we do some BI alloying, so it reduces drastically and becomes 0.72. But the other things, actually the static dielectric constant, high frequency dielectric constant, and the effective LO frequency remains almost similar. And that does mean that the folic interaction strength we previously defined actually reduces a lot. And according to that, the mobility, whole mobility part, depending on the folic interaction, increases a lot, which will really help in the transport actually. So maybe help in the year. So the main take home message will be the small BI substitution may increase the mobility. Okay, so next thing I will just summarize the results. So allowing BI in CS2Ag INCL6 induces a parity allowed optical transition. That direct transition is optically allowed now, hence increased PLQY. Next, the dominant vibrational modes remains almost similar. Mainly comes from the AgCl6 octahedra, so does not change a lot, the Raman active modes and etc. Next, introduction to BI introduces BIS-like states, orbital states in the valence band, and hence reduces the effective mass, and which in turn actually simulation reveals that a carrier mobility will be increased in this material. So these are our main studies. So actually and we actually managed to publish it in Journal of Physical Chemistry Letters earlier this year. And with that, I would like to conclude that, and then I will acknowledge the persons related to this work. So Dr. Devashish Das from our group, who helped me in the theory simulations, and then my Professor Apta Valam, who supervised the simulation part and all the theoretical part. Then there was experimental part where Devjit actually did the experiments. Then there was Dr. Tapan Kumar Das and Professor Ashwini Vella, who actually supervised the experimental part. And with that, I would like to thank you all for listening to me, and I would like to conclude. I will be taking some questions if you have any. Yeah.
Thank you, Jiban.
I'll just stop sharing. Oh, should I stop sharing?
No, that's fine. Hold on.
Okay.
So I have a question.
Yeah.
Well, the first question is, are there chances of small polaron formation here? Because
no, sir. Basically, what we try to see here is the large polarons here. So whenever okay, I'll just show you one table. Actually, this is LP is the polaronic radius we measure.
I see.
So that is actually almost 40 angstrom, which is covers 4 times the large polaron. So the interaction is not that strong. Yes.
I would have thought that once you allow for octahedral rotation, there
and
could
then
be.
If large polarons are not there, to frolic interaction will not be applicable though. The frolic Hamiltonian part.
So so are there also opportunities for bipolaron formation? Because these are all very deformable lattices. Bipolaron formation.
True. We have not explored it yet. I could not say.
Thank you.
Thank you so much.
Any other questions, comments? If not, let's thank Jiban once again. Thank you, Jiban.
Thank you. Yeah, thank you, sir. I'll just stop the share.
Okay. Our next speaker is Dr. Naufal Jassim. Naufal, are you there? Naufal? Are you there? I can see you have to unmute.
Yes, I'm here.
Okay.
Share the.
Can you quickly share your screen? Yeah.
Can you see the screen?
Yeah, please go ahead.
Okay. So today I'm going to talk about generalized measure of quantum synchronization. The title is different in the SYMPHY booklet, but the abstract remains the same. These are our collaborators. So the reference of this work is given here. So it just got accepted in Physical Review Research. So outline of the talk is as follows. in the introduction, we'll talk about the classical synchronization. So there I will show you a video of an example of the classical synchronization to understand what I mean by synchronization. Then I will talk about quantum synchronization. There we will discuss some of the existing measures of the quantum synchronization. So there are many measures of synchronization. So we will talk some of them. So there I also motivate why we need a unified measure or generalized measure. Then I will introduce a new measure, which is a distance-based measure, which we will apply to unipartite system as well as the bipartite system. And then we will discuss an interesting example, synchronization of dissimilar systems. Such systems has not been studied in the literature before, so we will discuss that here. So I want to show you a video. So here we have two classical oscillators. So initially they are not synchronized to each other, but we can synchronize them by coupling them appropriately. So it is done here by keeping them on a common platform. So you can see now they can talk to each other. They can, they can adjust their rhythm in order to become synchronized to each other. So now you can see they are synchronized to each other. So that is the synchronization. So now what are the requirements for the synchronization? So in order to have synchronization, we have to have a self-sustained oscillator and we have to have a free phase associated with the oscillator. So the self-sustained oscillator in the sense that the oscillator is coupled to a pump and a damp, so that if any disturbance happens to the system, the pump and damp will compensate that disturbance. So let me explain that using the space-space diagram. So here we have, so this bowl curve is the preferred trajectory that we would like to have for the oscillator. But in case if we supply some additional energy to the system, then the damp will take out that energy and then bring it back to its original state. And if we take out some energy from the system, then the pump will supply energy and bring it back to its original state. So the system always remains in this bowl curve. This acts as an attractor. So we call this bowl curve as the limit cycle. And the free phase means the system doesn't have any phase preference, meaning the system can take any phase value with equal probability. Okay, so similarly, we can synchronize quantum systems. So we can take a single quantum system and then we can phase lock this system onto an external signal. So if we have only one single system and then lock onto some external signal, which is such synchronization sometimes called as the entrainment, or we can have a large number of large number of quantum systems and couple them appropriately and we can synchronize them. Such synchronization are called a mutual synchronization. There are many such examples studied in the literature. Some of them are given here. But in each of these examples studied by these authors, they study a new system and then they have to introduce a new measure to study the synchronization of that system. So this motivated us, motivated us to look for a unified measure, a generalized measure, which can be applied to all of the system as well as any new system that we want to study. So let's discuss some of the existing measures or weakness of the synchronization. So here in this paper, Lee and co-authors study a quantum van der Pol oscillator, a driven quantum van der Pol oscillator. Van der Pol oscillator is nothing but a harmonic oscillator coupled to a pump and a damp. So this is the evolution equation. So here these two are the Limblad dissipative term corresponding to pump and damp. And then this van der Pol oscillator is driven by an external signal. So the system is locked onto this drive actually. So epsilon is the field strength, delta is the detuning, and A is the annihilation operator. So to study the synchronization, the Lee and co-authors look at the Wigner function for the system. So Wigner function is quasi-probability distribution. So here X is the moment position and P is the momentum quadratures. So if you look at this Wigner function, you can see that when the drive is switched off, so for the limit cycle case, there is only pump and damp here, not drive. So then the system doesn't have any phase preference. System can take any phase value with equal probability. But when the system is synchronized, when we switch on the drive, the system is synchronized. So the system has a phase preference here. So that's how we know whether the system is synchronized or not. Now here Roulet-Bruder study spin-1 system to study the spin-1. So here they establish the limit cycle using this is the pump and this is the dump, and these two, pump and dump, will pump the system to this middle state. Omega 0 is the natural frequency, and then this system is driven by an external signal to which this system is phase locked. Okay, so omega d is the drive frequency, epsilon is the field strength, and these SIs are the SO3 operator, S plus, S minus are the ladder operators. So now to study the synchronization of this system, Roulet-Bruder introduced the Husum-EQ function, which is again a quasi-probability distribution. So they introduced this Husum-EQ function using the spin-1 coherent state. So which is the rotated extremal state. So 1 is an extremal state. So it is rotated along the parameters theta and phi. So and in terms of that, so now these spin coherent states represent all the pure state of this system. And to get the probability of getting this state is given by this. So that we define as the Husum-EQ function. Now, if you look at the time evolution, these and the free evolution of this this spin coherent state, you can see that the phi is the relevant parameter which varies with time. So that the phi is the parameter that we can phase lock onto an external signal. So that's the relevant parameter for us. Here the Q function is plotted. The theta is along the vertical axis, phi is along the horizontal. So when the epsilon is 0 for the limit cycle case, you can see that phase phi doesn't have any phase preference. So the system can take any value with equal probability. But when the epsilon is not equal to 0, you can see the system has a phase preference. So that is the synchronization. As we are not interested in the theta, we can integrate out this quantity, and then we can call this integrate out the theta, and then we can call this quantity as the sync measure, which is plotted here. The maximum value of the sync measure is plotted here. Here it's plotted again as the field strength epsilon and the detuning, and this orange region is the region of synchronization. We can see that as we increase the field strength, we can increase the region of synchronization. So this is called the Arnold-like behavior, which is characteristics of the synchronized systems. The same measure can be extended to a 3-level atom where we have unequally spaced energy levels, unlike the spin-1 case where we have an equally spaced energy level. So this can be done using the SU3 coherent state. This actually, we extended this Roulet-Bruder measure to 3-level system to study the nanoscale synchronization in a nanoscale heat engine in this paper. Now we have another measure here. So this is Ameri and co-authors studied mutual synchronization. So they coupled 2 quantum VDPs, and then they showed that the mutual information can be used to study the quantum synchronization. So this is the mutual information where S is the von Neumann entropy. And again, the mutual information shows Arnold-like behavior. G is the coupling strength. So now we have seen that there are many kind of measures introduced to quantify the synchronization. So that made us to look for unified measures. So here we propose a measure based on the distance. The idea is that we know for limit cycle there is no phase preference, but when there is when the system is synchronized, the phase preference changes. So if we can calculate the distance between the density matrices corresponding to the limit cycle and the synchronized case, then we can quantify the synchronization. But there is an issue. So let's explain that using this van der Pol oscillator. So here we have an undriven van der Pol oscillator where this is the position quadrature, this is the momentum, A is the annihilation operator. So here you can see again, there is no phase preference when the system is in the limit cycle state, but the limit cycle is centered around this wide dotted curve. But when we introduce the drive or coupling, there are 2 things can change. One is that the limit cycle itself can change. So we have a limit cycle initially here, but now the limit cycle is somewhere here. And also we can change, the phase preference also can change. Now you can see the phase, the system prefer phase here. So, but we only want to capture the change in the phase preference. We don't want to capture the change in the limit cycle state. So what we do is that we optimize our measure over all possible limit cycle state. So D is any good measure. Rho is the steady state when the drive is on. Sigma is the limit cycle states. So we can optimize over all possible limit cycle states, and we can calculate the. So that will give us the sync measure. So here we particularly look at two kinds of measures. One is the relative entropy of synchronization. The other is the trace distance. But because of the time constraint, we will only look at this measure here in this talk. Okay, so let's apply this to a unipart system. For the unipart system, we can optimize our measure over diagonal limit cycle state.
2 more minutes.
Okay, so here our measure reduces to, when we optimize over diagonal limit cycle states, our measure reduces to the S coherence, which is a measure of relative entropy of coherence. Sorry, that is measure of coherence. So this is the relative entropy of coherence, which is given by this. Rho is the steady state when the drive is on, and rho diag is the state rho when with all the off-diagonal elements set to 0. So this again is in agreement with our observation in the physical review E, recent paper, where we observed that the amount of synchronization present in the system is related to the amount of coherence present in the system. Let's apply this to a bipart system. For bipart system, we can have marginal limit cycle states, diagonal limit cycle states, and partially coherent limit cycle states. For the marginal case, our measure, again, if you optimize over marginal in the sense that it's the state of the system A or state of the system B, so the sigma A or sigma B. So our limit cycle will have something like this form, rho A tensor rho B. If you optimize over that, our result reduces to the mutual information, so we reproduce the Ameri result. If you optimize again over diagonal limit cycle states, our measure reduces to relative entropy of coherence. For partially coherent limit cycle states, we won't get anything simple like these expressions, but it can be done numerically. So we specifically take two spin-one systems and optimize over a particular partially coherent limit cycle state. So our measure can be applied to all the examples that we discussed before, but we will only look at an interesting case, that is the synchronization of dissimilar systems. So we particularly look at, we couple a VDP with a spin-one system. So these two are the Bayer Hamiltonian for the spin-one and VDP, and this is the coupling. Delta is the deuterium between these two. And here is the evolution. So this is the unitary evolution. So these two are the dump and pump for the spin-one, and the other two are for the VDP. And measure is again plotted here. We can see it gives us an Arnold tongue-like behavior. Okay, thank you.
Thank you, Naufal. This session is open for questions. Any questions, comments? All right, if there is no question, let's thank Naufal again for the nice talk. I will now hand over the stage to Sanjay. Sanjay. Sanjay, the stage is all yours. Let me call him.
You decide now. After Sanjay is joining.
Yeah, Sanjay, you need to come on the Zoom.
Hello, am I audible?
Yes.
So where I am not getting where I am. Yeah. Yes, sir. Session is end.
Yes.
Yeah. So yeah. So thanks to Professor Aptavalo, session chair of theoretical condensed matter. So let's move on. So we are all actually almost at the end. We are entering to concluding session. So we are having company session actually. This is so they sponsored for our real SYMPHY. So it's actually resume SYMPHY. So we are as promised. So we are having some talk for them. They are actually our big sponsor, Thermo Fisher. So I would like to call Miss Bashanti. She's here. Can you just come out? I am not seeing Bashanti. Yeah, she's here. So please on and yeah, please start. So your time starts now. So 10 minutes.
Thank you very much, Sanjay. Let me just share my screen quickly. Allow me a minute if you're able to screen.
Yes, it's already allowed. So you can share. Yes.
Yeah. Thank you very much. Very good evening to all the participants and the organizers. It's been 2 days. It's a great event. Thank you so much. So this evening, I'm going to quickly give you an overview about what we do at Thermo Fisher Scientific, helping our scientists across the world. So we are really proud about our mission that we enable the scientific community, people who are working in the research laboratories, to make the world a healthier, cleaner, and safer, so that we accomplish this mission day in and day out. And this is what we are here, to prove. So globally, we are around 70,000 employees, and out of which around 10,000 employees you might be seeing on the field. So that's where we come in the form of either a sales representative or an application, or it's a service employee who will be meeting, the scientists. And we also have 5,000 R&D scientists and engineers, which is where these products are coming as a tool or an innovative technology to you to enhance your laboratory, in which you can save the time and also reliability on the equipment. So from the time when many of you started your laboratory work until now, you can see the improvement in the technology, which is all thanks to these engineers and R&D scientists who are working behind on these tools. We also invest in R&D every year so that we get the new tools and going back with the older tools, so that this will enable and accommodate with the new technology which is coming up and all the software which is getting embedded today. So that's a great investment we do, out of which the $25 billion as a company we stand today of 2019 ending. So that's where, as a company overview. So what do we do when you meet in the lab? How do you identify it? So you might be seeing many equipments coming with different brands. So the breadth of the portfolio, whether it is coming as Thermo Scientific today or Applied Biosystems, which is again very a prominent name in the research, Invitrogen more into the life science sector, Fisher Scientific or Unity Lab Services, and to that a new addition last year we did was Patheon, which is into the pharmaceutical contract services, which is very important today, because the technology can move from place to place and country to country, but then the services would help them to lead that way. So anytime when you come across these kind of brands, all are under one brand, which is nothing but Thermo Fisher Scientific. So with this breadth of portfolio, we do not restrict ourselves into one particular research, whether it is healthcare. Yes, we could supply today to the earliest as we can possible to the doctors, the life science portfolio, and we are very proud that we are part of each and every step of the COVID research which is happening today. So the COVID testing, if you see, around 70% of the products are from Thermo Fisher Scientific, and we are able to help and detect the cases much earlier. And the COVID research, which is happening in isolation of the RNA from the COVID viral RNA, and also the vaccine research. So the vaccine research and storage is a big portfolio, where we are able to serve, and that's where we are really proud about living our mission there. Applied markets, yes, it is refinery, coal, or its power. We have the cutting edge technologies to serve them. Now coming to the laboratory, portfolio, which is where our bench scientists, starting of any of our careers in our research, we do work in our sample preparation, or it's going to be an analysis, or it's a storage. Our entire laboratory portfolio you might be coming in across. So that's where we have a division which will accommodate this. And also in the manufacturing of pharma and biotech, there is a huge amount of portfolio which goes into. So that's an overview. And today where we are representing, where I'm sitting here to representing the Laboratory Solutions India, we have a breadth of chemicals with all the brands, whether it is imported, and also our homegrown, India Qualigens brand, which you might be aware about these bottles lying in your laboratory, and the equipments which is mostly used in the sample preparation and storage, and also the consumables. So this is majorly the laboratory portfolio which is required for day in and out in your lab. A very quick overview about the chemicals which you might be using, mostly to the participants who are present here. So you must be either working under the inorganic chemistry or in the analytical. There is a wide range of portfolio and the forms, and we are very, specific to maintaining a smaller size portfolio so that it will accommodate our research scientists, keeping that in mind, so that the shelf life or the nature of the chemicals do not, vary. So right from a very, very small size, pack size, which can be used for a research scientist. And to all the participants, one urge and a friendly urge is, please do visit our newly launched website specific to chemicals, and it is exclusive only for India. This is the first time we are launching something exclusive to Indian customers, which is thermofisher.in/chemicals, where all our 7 brands are accommodated into one single website, because many times we hear that people do visit different websites for hunting for chemicals under Thermo Fisher Scientific. And this is a boon to ease out that search. So you can search as many chemicals and the portfolio or the purity levels based on your research you can accommodate. You can also look out for, having a 1-hour session with our lab safety team who can guide you in terms of the chemical safety or a lab safety. That's a kind of webinar we can organize. So you can either browse by chemicals or by brands. And there are also 2 cool tools which you can use. It's free of cost and it is embedded in the website. One is the chemical structure. You can draw if you are interested in synthetic chemistry, or if you have any molecules of interest, you can draw and look out for those molecules of availability. And second is an interactive element, the periodic table, whether it is metals and non-metals you're working on, whether it is available in a string form or a powder form, depending upon which area of research you're working on. This interactive periodic table will be handy, which is very well embedded in the website itself. You don't need to download any software. So that's the ease of this new website. You can look around it. You can choose the products. You can email cart. It's a new functionality which is available. It's like sending, if you're working here and you have your colleague working in Chennai, for example, you can select the products, email the card saying, this is what we require in our research and this is the purity. So that's the kind of ease we have brought in. A quick overview about the fine chemicals, which is specific to applied chemistry, where the participants today might be working on is the metals and materials or inorganics. If there is anything specific which you're looking at moisture sensitive application, we have something called as an AcroSeal product ranges, where most of your organic reagents, which are to be sensitive and it should not be hampered by moisture. So these are the seals which comes with a very specific septic valves, seals, so that it doesn't allow as many times you aspirate the chemicals, the moisture will not enter, so that it can be intact. So that's something which you can keep in mind as an AcroSeal range of products under the organic reagents. So anything related to analysis, or if you're working in NMR, there are very specific standards and solutions available under the fine chemical portfolio. So with that, a very quick overview about the lab equipments, whether it is as small as a magnetic stirrer to a recirculating chiller, where you want to manage the temperature and maintain in a particular constant temperature. We have the entire range, irrespective of the sample sizes, whether it is small or a multi volume liters. And the other important thing about the high purity water, which you want to
hello ma'am,
analysis. Yeah, please.
Ma'am, sorry to interrupt, but are you sharing any slides?
Yes.
No, but your slide is not visible. Sorry.
Oh, really? That's what I was actually confirming.
Yeah, I thought you were saying. Yeah.
No, I've been sharing the slide. I'm extremely sorry. And I did confirm with the team, right?
Please try again. Like.
You can quickly share the screen.
Yeah.
There is screen option.
I did share the screen, and already. Oh, I'm extremely sorry.
Oh, yeah. Sorry. We thought you were saying. Yeah.
I did select this screen. Maybe I'm extremely sorry. So just quickly an overview. Though I spoke a lot, I will just show what so this is the brand names which I showed under Thermo Fisher Scientific, and these are few of the equipments, that is healthcare, life science, applied, and the laboratory equipment. And from the laboratory perspective, where it is sample preparation or the analysis, we have chemicals, equipment, and consumables, which quickly I briefed upon. And then the chemicals portfolio, whether it is analytical, inorganic, organic chemistry, or it is into the novel life science and screening libraries where we are into the drug discovery, we too have libraries, a ready library available. You don't need to synthesize. And this is the quick overview about the new launched Thermo Fisher, chemicals website, which is exclusive to India. Please do visit the website. You will get to know all the chemicals under the brands under Thermo Fisher Scientific, all our 7 brands, whether it is alpha, IISR, across. You will get to see at one site. You don't need to, jump into different websites. So that's the advantage of thermofisher.com/chemicals. And these are the 2 tools which I was telling, that is the structure search. You can draw the chemical structure, you can do an exact search or a substructure, or you can interact with the periodic table, which is an interactive periodic table, whether it is metals or non-metals. You can interact and get to know which form of the metal you're looking at, whether it is in the powder form or the crystal, or it's going to be the strings and wires. So that's the availability of the, and the quick overview about the moisture sensitive reagents, which I was talking about. One is on the inorganics, metals and materials, and the moisture sensitive comes under the organic reagents. So if you have anything specific to moisture sensitive application, please to refer to an AcroSeal packaged, reagents, so that it, it has a septic along with it, so that it doesn't allow the interaction of moisture sensitive, reagents to go bad in a very quick time. So as many times you aspirate, there is no, the reagent is intact, the chemical is intact. So that's the idea, when you have specific moisture sensitive applications and you're working on it. Rest is, relative to what application you're working on, whether it is IMR, NMR or IR, you have the analysis and also the essential solvents, acids and bases under the entire fine chemicals portfolio. And all these volume pack sizes comes into, very small range, as you can use it for a quick work, not for a larger volume. You can go for the small packing sizes as small as 10 grams to 50 grams as well. So that's the idea what we look into when we speak to the research scientist. So under the equipments for a sample preparation, you might need a water bath or a small magnetic stirrer to a recirculating chillers, where you want to maintain the temperature for a long duration of time till your experiment is working. You can go on for the temperature controlled equipments. And we also have the water purification system, where you need water either for dilution or for the analysis, and it should be free from impurities like ions and any other heavy metals. So that's how the water purification systems helps you deliver that. And the centrifuges comes in a mini or a micro centrifuge to a large volume. And coming to the cold storage, we have the entire range from a refrigerator to the cryo storage of the -196, depending upon what kind of sample would you like to store. And the range of electrochemistry, mostly, the basic is a pH meter, which we need for all the experiments, followed by a conductivity meter or a titrometer, and a UV visible spectrophotometer comes in the entire range of the electrochemistry portfolio. Going ahead of, the ovens and furnaces, which is again a wide range or a large heavy duty products, which has a very, very rugged life portfolio, is also under the equipment portfolio, which we call as the everyday use of the laboratory. And without the consumables, I think we cannot aspirate the sample or do a sample preparation. So all the NUNC or the Nalgene brand, which you would be hearing about in the lab, is all under Thermo Fisher Scientific. So the glasswares, plasticwares, pipettes and tips, with multiple compatibility based upon your chemicals, what you use, you can be sure about the compatibility, what you would need, because that's very, very important to choose the compatibility, any glassware or a labware which you wanted to work on. And also the gloves, which is again more into chemical resistant glasses, you can look out for, or a clean room apparel, depending purely upon which area working on or which instrumentation lab you're entering in. So with that, the overall Thermo Fisher India, we have 17 offices, but we operate at 42 locations with our remote representatives, so we can to even the smallest lab. And also we support from the application standpoint with the new applications. If there are new method which we need to develop, we have 5 different application labs and 2 R&D centers only in India to support our Indian customers, because we are now ranging, really, moving ahead biotech, pharma, and the healthcare overall, if you look at, and secondly, the food. So we have very specific scientists who are working behind so that we can support India to be one of the global leaders as well. So with that, I would end my presentation, and we definitely are proud about the mission, to enable you scientists to make the world healthier, cleaner, and safer. Each one of your experiments would be definitely leading to any one of these missions. So thank you very much. If there are any questions, I would be happy to take. And I'm really sorry that I couldn't share my slides. I'll be happy to share the slides in case if you need. Please unmute if you have any questions. Sanjay, thank you for your time. Is there any?
Anybody have questions? Thank you so much, ma'am. I think there is.
Thank you very much. Thanks for the time.
I think Sanjay is not there. So.
Okay, I would be happy if is there any questions that I can take?
Yeah. So thank you, Miss Bashanti. So let's move on. So we are concluding session now. So I would like to call. So who is sharing something?
I
Okay.
shared
So
this slide.
yeah. Thank you.
I
Thank you,
think you
Monica,
have
for
mentioned.
sharing.
Okay.
So I would like to call Professor Aptabalam. So Professor Aptabalam is here.
Yes.
So yeah. So now this session we are having announcement of oral and poster results, and then he is actually our SYMPHY2020 coordinator, faculty coordinator. Also we have another faculty coordinator, HOD sir, and I am the student, means out of PhD student, I am the coordinator. So I would like to hand over to Professor Aptabalam for this session, announcement of result and some concluding remarks. Yeah, let's take it over.
Okay, so this is the most difficult task given to me, the responsibility to announce some prizes. And I will refrain to use the word best presentation because all the presentations during both oral and poster sessions were of good quality. I'm sure all the speakers must have invested sufficient effort to put together their slides and hence the presentation. However, the organizers would like to facilitate 3 prizes in each category, oral and the posters. And it was actually not easy to decide these prizes because of such a vast set of research areas covered in this symposium. However, organizers made a judicious choice of different parameters based on which these presentations were evaluated. So based on these evaluations, there are 3 prizes that is decided for oral presentation, and for poster presentations there was a tie. So there is going to be actually 4 prizes for these, and there is nothing called first, second, or third, but I will just name as per the alphabetical order. So in the first of all, in the poster presentation, the first name is Bhavna. So what I'll do is I'll just quickly share the award that we have.
Sir, sorry for interruption. Please call them if they are here so they can show up.
Yeah, Bhavna, are you there? Bhavna?
No, let's go.
All right. The next name in the poster.
Sir, you can share that one. You can just share. Go and share one by one. I don't know they are here or not. Just share that one.
So Sanjay, if you have the files handy with you, why don't you share? Because I think there is some issue with my sharing.
Okay. Let me try. But
first for the poster category.
Okay. So you just try. I need some 2 minutes to delete some. Means there is, yeah. I have need to open that up. I am trying. So you just try. I am coming back within 1 minute.
I'm still trying.
All your secret files are getting displayed.
Not secret files, not secret. I can show my window. That's not an issue. So
is my screen?
Yeah. We see all the names now.
It's all the winners.
You can see my screen or not?
Yeah, your desktop. So the
are out. Hafta, be careful.
Thanks for the concern, Suresh.
yeah.
Yeah, I think I have it here.
It's already open on the left side.
Yeah.
Can you see the full screen?
Yeah. Perfect.
All right. So one of the name under the poster category is Bhavna. All right. The second name is Vinod Kumar, the best poster award. Vinod, are you there?
Sir, go to full screen.
Yes, sir. I am here.
All right. Congratulations.
Thank you, sir.
Go to full screen.
All right. Full screen. Sanjay?
Yeah. It's big enough.
Yeah.
All right.
So you're sharing. So it's okay. I'm not sharing.
Jyoti Sharma. Jyoti, are you there? Jyoti? Is Jyoti mute or just check?
Okay, she is not here. You just go to full screen.
All right.
Then, yeah.
Jyoti, congratulations. And the last name in poster category is Arjun Unnikrishnan. Arjun, are you around? All right. Congratulations, Arjun. Okay. The next category is oral presentation. Sanjay, did you share me the...
Yeah. Last mail. Last 3. Yes, right.
Okay, I'll just announce the name here. Sanjay, please double check it. Huh?
Sure.
So the first name in oral category is Urvashi Bothra.
Sir, there is one last Jibon is not there actually. So 2 from PhD and another 1 from PDF.
Yeah.
So I gave PDF. No full is there. No full. Yeah. Onuj, Urvashi and no full.
So yeah. Urvashi, are you there? Urvashi?
Oh, no.
Okay. Congratulations, Urvashi.
Next is no full. So
next is Anuj Chabra.
Oh, sorry.
Anuj?
Yes, sir.
Are you there?
Yes, sir.
Can you show up? Can you show up? Or your video issues? Fine. Yeah. Thank you. Yeah.
Congratulations, Anuj.
Thank you, sir.
And Sanjay.
Under PDF category, Dr. Noful. Yeah. Right.
Okay. Naufal Jassim.
Are you here?
Naufal, are you around? All right. Congratulations, Naufal. Okay, congratulations to all the participants. Sanjay, I'll hand it over to you.
So some concluding remarks, and then I'll take it over for vote of thanks.
Please.
Have something. So this is your two jobs. One is that announcement, and another is some concluding remarks. So then I'll take it over.
Yeah, I mean, this was a very,
Just stop sharing. So it's done. So
it will stop sharing my screen. Yeah, so I will give all the credits rather to the students community, especially the task force working day and night behind some of the key people like Sanjay, Monica, Sean, who has really worked hard to deliver all of these talks, the poster presentation and the oral presentations in a very streamlined manner. I was actually wondering about the timing, that whether the timing will be maintained in each session or not, or it may be spill over from one to the other. But I observed that it was very nicely maintained and done very accurately. Sanjay, I was actually missing the actual symposium which we were supposed to conduct in Feb or March. That would have been a different experience. But this virtual symposium is another experience, and it has been done very nicely. Congratulations to all of you. Great work, Sanjay, and the team. Thank you. Sanjay.
Yeah, so now it's your turn. So then my time. So it's time to vote of thanks. So in general, I would like to thank all of you. Then I'll go to one by one. So I would like to thanks our sponsors. Actually, during Real Simpy, we did that. Actually, Real Simpy just one day before, due to pandemic, we did that. Actually, that was urgent. We have to do that on. So then we resumed. So thanks to all the sponsors. And now coming into part virtual Simpy. So first of all, thanks to Professor K.G. Suresh and Professor Aptabalom. Last day itself, they are having some power issues and our website got out. And so I informed our organizers and they quickly back up. So it's very nice. And actually it's so that power issues in this virtual platform, power issues are the main things. So it's a very thing. So another things happened morning. So I saw, so I am hosting from a village, actually it's called Bana. So it's far from 2 hours far from our airport, Damdam airport. So this village, they are good internet connectivity is very good. Also morning itself, my father told that our home that there is a power, some issues are there. So he informed that I quickly resolved and come back to here for day 2 starting. So thanks to our family members for their cooperation, and my father just informed that backup, so that power things are not working. So that one thing. So then I will come to all the speakers. I would like to thank all the speakers and session chairs. All the speakers are very nice talk, and session chairs for their nice contribution. And also there are things, so oral evaluation, another thing, so quick things, I just send them message, please drop quickly, so they did on time. So thanks to all for cooperation and that quickness. So all the other presenters, oral, poster presenters, thanks to all the oral and poster presenters for their nice talks and contributed. So it's a compact, so it's a team effort. The team is not only about the virtual team, those who are working behind, it's a team. All session chairs, speakers, participants. So if their participants is not there, so there is nothing, right? So I want to thanks to all the participants, those who are contributed, all the attended, all. I would like to thanks all of them. So next I will go to that to introduce our team, virtual team and also real team. So Monica, can you share the screen? You have that slides, right?
Yes, yes. Wait.
So please share the screen. I think you have that latest on. Otherwise, I can quickly share our team. And those who are here, please on your video. The volunteers who are here, please on your video. So yeah. So first of all, that left side and our right side, Professor KG Suresh and Professor Aptabalon, our faculty coordinator. So they both supported and gave me that opportunity to lead the team. Actually, they give me opportunity, means I practice my exercise, my skill. Also, I got that opportunity. They have trust on me that I can do this. So they give up to me sometimes. So it's thanks to both of them. And so they are like coach and I was the captain of this team, kind of things. It's what. So then I will go to the Mr. Ishantawari. Actually, he is absent here, but due to he got tested positive, that's why he is not here. He is very active member. Actually, he is the ex-general secretary of RSAP. He supported very well from beginning. So unfortunately, he is not here. So next I will go to actually second column. They are all in virtual platform. They help. They work very nicely. Miss Proggayan. So Progganama, thanks to Progga. Miss Monica Jawale, Dr. Siri, Mr. Shangshatabde. You can see always he is taking some screenshot, all those things. So thanks to Mr. Shangshatabde. He will take again a screenshot after this. And also Mr. Bikash, Dr. Shidi Shekhar, so all are in this virtual platform. You can't see, but they are in cohort. Sometimes they are working behind. So they have contributed very well. So it looks smooth for them actually. It's a great team effort. So Mr. S. Sushant Sharma, Mr. Monish also here in virtual from backing. So Mr. Where God? Please share.
Red card.
क्या होगा? So Mr. Kishore Mondol and Miss Dipomala. So they are in real field, but due to some emergency, they are not here maybe. So that's okay. So actually the SYMPHY preparation has started almost 1 year ago, like November, maybe like that. Yeah. So after 1 year, so due to COVID, 6-month gap was there. So finally we understood that the situation looks like, so we will, if we organize in real SYMPHY later, so then we will lose the set of people. Basically not our speakers, they can come up, but our oral presenter like PhD students, they are getting out, means they are PDF, going to be PDF, and whoever they prepared actually that kind of slides, so their effort will go to vain. Actually, that won't be used for after 1 year. That's how we actually, our organizing committee, Professor KG Suresh, Professor, I discussed and we planned together that we will go for the virtual SYMPHY. So it's it looks okay at the end, and also yeah. So thanks to all of them, all the members, all the faculty coordinators. So with this, I conclude my vote of thanks. So thanks to all. So if I miss personally someone, so take it from that all. So next we will have photo session. So next go to photo session. Please stop the sharing. So Mr. Samshaptab, are you here? Yeah.
Yeah.
So thanks. You won the video. So this time I'll take 2 photos. I'll go from there to so actually here I have on backup I have, so I can show. So actually it's my backup. So can you see the backup? So from this my iPad, so it's give me more things. So that's post. You can see that yes, Bashar, that's me actually. I am going from here and there. So this laptop, it's actually overloaded automatically. So sometimes I am checking from there itself. Sometimes I responded 2-3 sessions from there itself. Session chat knows I am there. So that's Sanjay. So that's a backup actually. So yeah. So Anybody?
So who is going to take the photo?
Yeah, Shangsaptab and Monica, can you take an other whoever is having good internet? Prabha, you are having good internet, maybe it looks nice. So take it some photo. One photo, then tell me, then I will go to that window. I will
Request Anjay, request everybody to turn the video on.
Yeah. So I request all of you to turn the video, please. It's almost end. Sri Parvati.
It is almost only.
So Yajbachar will not on. He will on after some time. Asif, can you on your video? You would like to participate?
Mine is on.
I don't know. Asif is facing some issues or he won't on that photo. I don't know. Let's go ahead.
Okay, I'm taking.
Monica? Done?
Yes, I have taken it.
Yeah, just wait. I'll go there.
Done?
Yeah.
No, not done.
Yeah, there's a special background.
Yes.
Over.
So yeah, so our photo session is over. So next I'll play some our IITB video, and with that we'll conclude. So if our HOD sir want to say something, please come up. Just some concluding remarks, please.
Yeah, in fact, I don't want to add anything more than what Aftab mentioned. I fully agree with him that I think this virtual thing was probably better than the real physical thing which we were planning. Really great work, Sanjay and your team. I really don't know. I don't have words to express my kind of gratitude to the whole activity that you people have taken. I wish that the next batches also will continue with the same kind of spirit. Thank you, Abhi. Thank you.
Sanjay,
Yeah.
the high tea will be due.
What?
The high tea will be due.
I didn't get.
HOD
Okay. Yeah. I got it. Yeah. So the thing is, I'll play some on video of IIT Bombay. Just wait for 2-3 minutes. Means that video will play that time. Then we will end together.
Hello. Actually, I want to say something.
Yes.
Hello.
Sure. Go ahead. Yeah.
Today is Sanjay's birthday also, so let's wish him a very happy birthday.
Happy birthday, Sanjay.
Very happy birthday, Sanjay.
Thanks to all.
Happy
Actually,
birthday,
that
Sanjay.
wishes is coming over message, but I am unable to reply to anyone. I got busy here. Yeah. So now I will reply to all. So first replying to you. So thanks to all of you for wishing me.
We'll do post birthday celebrations. You come here.
So on the SYMPHY video first. Yeah. Now it's on. So let's. So last video or campus awards. Yeah. This is our last video. So please tell me that it's a video and it's working or not when it's going. Is it visible? No, right?
Yeah, it's coming.
Not yet.
Just play now.
So let me try again. It's coming?
वो सबकी पसंदीदा शहर।
Yes.
Thanks.
एक सुकून था उस शहर में, धड़ मची है इस पहर में। वो खुला मैदान, वो सुनहरी शाम।
Is it possible to increase volume?
वो सबकी पसंद।
Yeah. Sure.
रास्ते फिर बुलाती है।
Huh?
No, this is not department. It's the institute. Right or not? She's coming. ये कहाँ पे है?
Audio is not there, Sanjay.
Audio I didn't give. So campus is actually waiting for us. We will back very soon. So with this, we are concluding this session. Yeah.
Thank you very much. Thank you.
Thank you. Thank you.
Bye.
Thank you.
Thank you very much.
Thanks, everyone.
Thanks to all.
Thank you.